Check one. Check one. Check one. Right. Good evening, everybody. Today, good evening is going to be a very long evening. I would tell it is the longest night maybe in your life. It is your physics night. Maybe the day that all of you all were waiting, the night that all of you were waiting, it's today. We are going to complete 4 lessons in physics fully, and towards the end, I'm going to teach you all some surprising techniques on how to approach any physics question and answer any physics question. I didn't post it in any of the posters. In the agenda I have mentioned towards the end, there's going to be something important, right? So we can start off. Zoom is full, 1000. YouTube more than 250 are there. At the beginning, if I tell about the agenda, we'll be first finishing the heat lesson, and somewhere around 10 you will get your dinner break, and then I'll be doing electromagnetism according to the tute is already posted in the channel. According to the tute, what is there first is electromagnetism, but according to the timing, what we'll be doing is first heat. First we'll be doing the heat section, that is the second section, and then I'll be going to the electromagnetism part, right? And then you'll be having something called the talent show, right, where your own friends and students will be performing a small talent show part just to remove the sleepiness. Somewhere around 12:15 will be coming across the talent show according to the timing, according to the agenda. Maybe there can be small changes, and towards the end there is a surprising session, and there is a what you call a physics part, how to answer any question in physics, right? Throughout the day we are going to work, throughout the night we are going to work, right? Don't be lazy. All of your comments sat here means you have something here inside you. Something is telling you to do something tonight, get something tonight, add something to your marks. So if you are in that mood, keep up that mode until the end. Don't let your focus, don't let your mood to change on the way. Until the end, work on this. You're going to work for your marks. You're going to keep up your enthusiasm. You're going to keep up your focus level until the end, right? We do so many things to keep up your focus, but from your end, you have to try to keep up your focus until the end. Don't think of anything unnecessary until the end. Focus onto this. Guaranteed you will have at least 20 marks in your final exam. Tonight, we are fighting for minimum of 20 marks. That's the plan. Hurry. Right. From your end, what I want is, if you have the tute printed, yes, superb. Otherwise, have the PDF of the tute nearby. Have the PDF of the tute nearby, and try to have some writing book or maybe some what you call papers, A4 papers, sorry, nattang foolscap sheet, sorry, something where we can write some important notes. I'll be telling and going. If you feel something is important, you write it and give. All right. So get ready with those material and give me a thumbs up. Additional material, maybe a book or pen. The pen, however necessary, no man. You. Harined. Right. Ready now? Ready? Yes. Perfect. I'll start the session without talking much. I'll start the session. First, we are going to talk about heat lesson. This is your part 2 book first lesson. Grade 11 part 2 book first lesson. That is your 11th lesson. Heat lesson. Heat lesson. Very important physics lesson. Different questions can be asked. When you know the heat lesson thoroughly, you can do some questions from heat changes in chemical reaction section as well. That is your 10th lesson. Heat changes associated with chemical reaction. Even that questions you can do if you know heat properly. Hurry. Listen. Now I want you 100% focus onto this. No any other focus. 100% focus onto this. Tonight we are going to put this lesson fully into the mind. Again, we don't have time to separately sit and study this. It's a wastage. Tonight, we study, we memorize, we revise, put all those things into the mind. On. Listen. Heat. Under heat lamai. First we need to learn about temperature. First we need to learn about temperature. What is temperature? How temperature is defined? Usually in physics question, they don't ask you the definitions. What is temperature? What is heat? They don't usually ask. But if you refer the recent past papers, some places they are asking you the definition. Or based on the definition, they are asking you the question. For example, instead of asking what is the acceleration of this vehicle, sometimes they ask you what is the change of velocity per unit time. What do you mean by change of velocity per unit time? It's acceleration. So if you know the definition of acceleration, change of velocity per unit time, if you know that definition only, you can answer that question. So remember, some places in physics, you need to know the definition. Right. What is temperature? Onna listen. What is temperature? Temperature is the measure of mean kinetic energy. Measure of mean kinetic energy possessed by the particles of a substance. Possessed by the particles of a substance. When memorizing, don't memorize full sentences. Don't memorize full essays. Our brain is not having the capacity to memorize full essays, full sentence, especially in the last 1 month for the exam. So don't try to do that. Memorize special points. Later when you go to the exam using your English, literature, grammar knowledge, you can expand and write. Right. What is temperature? Temperature is the measure of mean kinetic energy possessed by the particles of a substance. Mean kinetic energy possessed by the particles of a substance. What do you mean by that? What do you mean by that? Temperature is the mean kinetic energy of the particles in a substance. That means now let's take, you are going to make tea. When you are making tea, first you take the mutti and put water into this. This is initial stage. Still I have not switched on the cooker. This is the initial stage. At the initial stage, temperature of the water is low. Most probably it's in the room temperature. So temperature is low. Still I have not switched on the cooker. And if you look at the water, water is very calm. It's very calm. It's very calm and quiet. No any big motions. It's very calm and quiet. But after you switch on the cooker, which means after you heat it for some time, guaranteed the temperature will increase. And now, if you look at the water, will the water be still calm and quiet? No. Just think after about 10 minutes. Now the water will be dancing up and down. Now the water is dancing. Now the water is, there you go, dancing. Initially calm and quiet, now dancing. Y'all tell me, something is dancing means its kinetic energy is high, low. Something is dancing means kinetic energy high, low. Patta high. Something dancing means it's at a motion, then kinetic energy high. Initially, what is calm and quiet? Kiani? What can you tell about the kinetic energy? High the low, calm and quiet. High the low, low. Kinetic energy is low. Which means, can you see, Initially temperature low, kinetic energy low. But after some time when you heat it, temperature high, kinetic energy high. Which means, can you see, when temperature is low, kinetic energy is low. When temperature is high, kinetic energy also become high. What kinetic energy? The kinetic energy of the particles. Inside this, I have water particles. Water particles only dancing. So water particles kinetic energy is high here. Initially, kinetic energy of water particles low. Towards the end, kinetic energy of water particles are high, which means I can tell temperature is measure of kinetic energy of the particles. Low temperature, low kinetic energy, the particles. High temperature, high kinetic energy, the particles. So temperature is the measure of kinetic energy. If we take kinetic energy, each and every water particle will have different kinetic energies. Each and every water particles will have different kinetic energy. Different values will be there. As they have different values, we try to figure out average kinetic energy value. Tell me another name for average. Tell me another name for average. Mean. So we try to figure out the mean kinetic energy. They try to figure out the mean kinetic energy. So putting everything together, what is temperature? Temperature is the measure of mean kinetic energy of the particles of a substance. Temperature is the measure of mean kinetic energy of the particles. Sorry, temperature is the measure of mean kinetic energy of the particles. If the temperature is low, kinetic energy of the particles are low. If the temperature high, kinetic energy of the particles are high. Got it? Got it? Yes. Yes. Hari, eh? Right. Perfect. Perfect. Hari, YouTube people. So can't we join Zoom? Zoom is full. Hari, perfect. I'll continue. So now we know temperature. Temperature is the measure of mean kinetic energy. How do we measure temperature? How do we measure temperature? These are baby things, no lamai. Temperature is measured using thermometer. Thermometer. If you take thermometer, there are three types of thermometers. What are the three types of thermometer? Mercury glass thermometer. You call it glass mercury thermometer. Mercury glass thermometer. Alcohol glass thermometer. Alcohol glass thermometer. Alcohol glass thermometer. Or you call it glass alcohol thermometer. And finally, digital thermometer. Digital thermometer. Go open the mouth and tell. Now itself memorize it. Put to the mind. What are the three types of thermometers? Mercury glass thermometer, alcohol glass thermometer, digital thermometer. Mercury glass thermometer made of glass. Inside the bulb, what is there? Mercury is there. Why mercury is there? Mercury shows uniform expansion over a broad range of temperature. Mercury is a good conductor of heat and its boiling point is very high. It shows uniform expansion over a broad range of temperature. It shows uniform expansion. Expansion is very uniform. It can conduct heat well. Its boiling point is very high. Again, one more time. What are the reasons why mercury is used? It shows uniform expansion over a broad range of temperature. It's a good conductor of heat. It can transfer the heat very fast and its boiling point is very high. If the mercury starts boiling, can you measure temperature? No, you can't measure temperature. So its boiling point is very high. Next, glass alcohol thermometer. Glass alcohol thermometer. What is there inside the bulb? Alcohol is there. Alcohol is there. What alcohol is there? Ethanol. Ethanol. What is the color of ethanol? What is the color of ethanol? It is colorless. No color. Then if it is colorless, how do we record the temperature? How do we measure and record the temperature? Is it observable? No. Therefore, what they do, they put red color into ethanol. They put red color into ethanol. They put red color into ethanol, the alcohol. Okay. What are the reason alcohol is used? Again, you can tell the same thing. It shows uniform expansion. It shows uniform expansion over a broad range of temperature. This one's melting point is very low. Very less melting point is there, which means it will turn into a solid at a very low temperature. That is what you mean by melting point is low. No? Think. Melting point is very low. If the melting point is very low, it turns into a solid at a very low temperature. Harinelamai, inside this liquid should remain as a liquid or should turn into a solid? It should remain as a liquid. If it turns into a solid, how are you going to measure the temperature? So this one's melting point is very low, which means for a very low temperature, it remains as a liquid. For a very low temperature, it can remain as a liquid. Mercury boiling point is high. To a very high temperature, it can remain as a liquid. Alcohol melting point is low. So for a very low temperature, it can remain as a liquid. Now tell me, out of these two thermometers, which thermometer is more suitable to be used in a very cold environment? Listen and answer. Which thermometer is very efficient, very good to be used in a very cold environment? Alcohol. Its melting point is very low. So to a very low temperature, you can use. Which one can be used for a very high temperature? High temperature usage? Mercury you can use for a high temperature usage. Other than that, thermometer, digital thermometer is there. Other than that, digital thermometer is there. I have given most of the things in the tune. I told you, if you think I am telling something important, Dingala make a sketch and keep. I can't give the full time for you to look and write. There are some places I have added for you to write fully. But other than that, additional things, you all Dingala put a sketch later on. Tomorrow, 4 o'clock, now this finishes. ඊට පස්සේ take a nap. Now tonight, physics night indala, you study everything. Tomorrow whole day sleeping, I think that is useless there. You cover up your 4 to 6 hours of sleep. Again, tomorrow start working. Maybe during that time, whatever the sketch you made, if you want it in a more understandable way, you write it in a proper way and keep. Hurry. Later you can write it like that and keep. Hurry. Next. Scales used in temperature measurements. Scales in temperature measurements. That means scales that we have in thermometer. We know, Nalamai, there are 3 scales that are used in thermometers. What are the 3 scales we use? Celsius, meva baba things, and Celsius, Fahrenheit, Kelvin. What are the 3 scales we used in temperature measurement? Celsius, Fahrenheit, Kelvin. Celsius, Fahrenheit, Kelvin. First going to Celsius. How Celsius scale is formed? Listen, how Celsius scale is formed? Lamai, to form a temperature scale, you need two fixed points. To form a temperature scale, you need two fixed points. A lower fixed point and an upper fixed point. Open the mouth and tell. A lower fixed point and an upper fixed point. Now, when you are forming the Celsius scale, lower fixed point is there, upper fixed point is there. Lower fixed point is taken as the melting point of ice at 1 atmospheric pressure. Lower fixed point is taken as the melting point of ice at 1 atmospheric pressure. Melting point of ice. Let's take you have solid ice. It turns into liquid at a certain temperature. That is melting point of ice. What ice? What do you mean by 1 atm? 1 atm is 1 atmospheric pressure. A unit used to measure pressure is atmosphere. Pascal is there, atmosphere is there, bars are there. So like that, 1 unit is atmosphere. So at 1 atmospheric pressure, what is the melting point of ice? That is taken as lower fixed point. Now, why we are defining the pressure here? Now, can't I tell just the melting point of ice without the pressure value? Why? Melting point, boiling point depends on pressure. Again, I repeat, melting point, boiling point depends on the pressure. If pressure changes, melting point, boiling point will change. Again, one more time. If pressure changes, melting point, boiling point will change. That's why I'm defining the melting point. Melting point of ice at 1 atmospheric pressure. That is given the value 0 degrees Celsius. It's given the value 0 degrees Celsius. The person who made the Celsius scale, maybe he likes 0, he gave it 0. He took lower fixed point as melting point of ice at 1 atmospheric pressure. He gave a value for that 0 degrees Celsius. He gave a value for that 0 degrees Celsius. Now coming to the upper fixed point. Upper fixed point is taken as the 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 boiling point of water. Boiling point of water again at 1 atmospheric pressure. By 1 atmospheric pressure, because boiling point also depends on the pressure. Boiling point of water at 1 atmospheric pressure. It is given the value 100 degrees Celsius. So lower fixed point 0 degrees Celsius, melting point of ice at 1 atmospheric pressure. Upper fixed point is 100 degrees Celsius, that is the boiling point of water at 1 atmospheric pressure. The gap between them is divided into equal divisions. Gap is divided into equal divisions. Then how much of divisions are there? 0 to 100. 100 divisions are there. Nalamai, Celsius scale is ready. 0 to 100 divisions are there. Celsius scale is ready. Sorry, that is Celsius scale. What's the unit? Degrees Celsius. That's the unit. Even unknown. Degrees Celsius unit. Now coming to Fahrenheit scale. Fahrenheit scale is also made using the same logic like Celsius scale. Lower fixed point is there, upper fixed point is there, upper fixed point is there. Here also lower fixed point is taken as the melting point of ice at 1 atmospheric pressure, and it is given the value 32 degrees Fahrenheit. The fellow who made Fahrenheit scale, he likes 32. He gave 32 for the lower fixed point. The person who made Celsius scale, he likes 0. So he gave 0 for the lower fixed point. Now tell me, these values are given based on a proper method or based on the wish of people? Based on a proper method or based on wish of people? Wish of people. Wish of people. Alright. So this was given 32 degrees Fahrenheit. Now coming to the upper fixed point. Upper fixed point also same logic is used. Upper fixed point is taken again as the boiling point of water. Boiling point of water at 1 atmospheric pressure. Boiling point of water at 1 atmospheric pressure. And it is given the value 212 degrees Fahrenheit. It is given the value 212 degrees. I don't know what kind of person is this. Fellow likes 32 and 212. I have never seen a person in my life who likes values like this. Just think 32, 200. Make a lassana. 0, 100. Maruine. 32, 212. I don't know what kind of person is this. In between divisions are there. In between the gap is there. Gap is divided into equal divisions. Gap is divided into equal divisions. Dingala calculate and tell me how many divisions are there. 32 to 212, how many divisions are there? And 32 to 180. 180 divisions. HRI Fahrenheit scale is ready. What's the unit? Degrees Fahrenheit. Degrees Fahrenheit. That's the unit. Degrees Fahrenheit. Capital F, here also capital Z. This symbol is degrees with the degrees you write. I know you know, but I know some of you don't know. And I'm telling degrees Fahrenheit and degrees Celsius. Next, going to Kelvin scale. Kelvin scale. Introduced by Lord Kelvin. Who made the Kelvin scale? Lord Kelvin. He made the Kelvin scale. His name is Lord Kelvin. Name is Lord Kelvin, right? He didn't make like Celsius scale and Fahrenheit scale. Celsius scale and Fahrenheit scale are like made from the wish of people. No? Is it standard? No, that's not that standard. So he didn't make, Kelvin didn't make based on wish. He made based on correct physics. He made the scale based on the definition of temperature. What is temperature? Temperature is the measure of mean kinetic energy possessed by the particles of a substance. That is temperature. Temperature is the measure of mean kinetic energy possessed by the particles of a substance. That is temperature. He made the scale based on the definition. Now, you all tell me, if I reduce the temperature, what will happen to the kinetic energy of the particles? It will also reduce. And let's say I reduce temperature, kinetic energy reduce, and goes to the lowest value. Go tell me, what's the lowest kinetic energy value? Minimum kinetic energy value? 0 joules. That's the lowest. Now, can we go to negative numbers? Or can I write minus 30, 20, minus 20 joules? Have you ever written minus 20 joules? No. So remember, lowest kinetic energy is 0 joules. So if kinetic energy has a lowest value, tell me, does temperature also have lowest value? Yes or no? If kinetic energy have low value, lowest value, minimum value, then does temperature also have lowest value? Yes. Why? Both are interconnected. Temperature is the measure of kinetic energy. So if kinetic energy has the lowest value, temperature will also have very low value. That lowest value of temperature is considered as absolute zero, the real zero. It's the lowest temperature any object can attain in this universe. I can use the word universe. It's the lowest temperature any object can attain. Lord Kelvin gave a value for that. He told absolute zero. He told the lowest temperature any object can attain is 0 Kelvin. Okay, Nevi? 0 Kelvin. Now tell me, what is the lowest temperature any object can attain? 0 Kelvin. Do I have negative values in Kelvin scale? No, because lowest temperature is 0 Kelvin. No negative value. From there, he started building his scale. See, nicely using physics he is making. From 0 Kelvin, that's the lowest temperature. That's the lowest temperature. He started making the scale. Now, how to make the scale? 0 Kelvin. Next is 1 Kelvin. Next is 2 Kelvin. He made it. Next is 3 Kelvin. There should be a definition to tell 0 to 1 is what? 1 to 2 is what? There should be a definition. How did he define? 0 to 1 Kelvin. How many Kelvins are gone? 1 Kelvin is gone. That is equal to 1 degree Celsius. 0 to 1 Kelvin. 1 Kelvin is gone. That is equal to 1 degree Celsius. Now we already have a definition for Celsius. No? What is Celsius scale? We already know though. Using that, now you can increase. Now tell me 1 Kelvin to 2 Kelvin. How many Kelvins are gone? How many Kelvins are gone? 1 Kelvin is gone. That is again equal to 1 degree Celsius. 2 Kelvin to 3 Kelvin. How many Kelvins are gone? 1 Kelvin gone. That is equal to 1 degree Celsius. This Kelvin doesn't have a definition. Celsius has a definition. So 0 to 1, you increase by 1 degree Celsius. 1 to 2, you increase by again 1 degree Celsius. 2 to 3, you increase by again 1 degree Celsius. Aim 1 degree Celsius by Celsius, when you keep on increasing, you can go to a very high value. So by 1 degree Celsius by 1 degree Celsius, you keep increasing the scale. You increase the scale by 1 degree Celsius by 1 degree Celsius. 1 degree Celsius is equal to 1 Kelvin temperature increment. So like that, when you keep on increasing, you will come to very high temperature. And you all tell me, do we have a maximum temperature? A minimum temperature is there. Do we have anything called maximum temperature? No, there's no maximum temperature. Harini, think in terms of kinetic energy. Do we have maximum kinetic energy in this universe? We don't have maximum kinetic energy. We have only minimum kinetic energy. Maximum kinetic energy is not existing. If maximum kinetic energy is not existing, then maximum temperature is also not existing. Okay, so there's no maximum temperature. You can keep on going. The scale keep on going. Minimum is 0. 0, 1, 2, 3, 4. You keep on increasing and you can keep on going. Now, we know minimum temperature in this universe is 0 Kelvin. That is equal to how much of temperature in Celsius scale? Remember, 0 Kelvin is equal to minus 273 degrees Celsius. But actually the real value is minus 273.15. But in your syllabus, we ignore the part 0.15. We ignore the part 0.15 and rewrite minus 273 degrees Celsius. So remember, 0 Kelvin is equal to minus 273 degrees Celsius. Now tell me, what is the lowest temperature in this universe in Celsius scale? What's the lowest temperature in this universe in Celsius scale? Minus 273 degrees Celsius. Can there be any temperature below this? Can I ever write a temperature like this, minus 300 degrees Celsius? Can I write? If you write like this, you are going against the laws of physics. Physics is telling lowest kinetic energy is 0. That 0 is 0 Kelvin. That is minus 273 degrees Celsius. You can't go below this. So can we write something called minus 300 degrees Celsius? No, we can't write that. So lowest temperature is minus 273 degrees Celsius. Okay. Now, let's take, you have the temperature in Celsius scale. How do we convert it into Kelvin scale? You have the temperature in Celsius scale. How do we convert to Kelvin scale? You add 273. Celsius to Kelvin, you add 273. For example, we'll take 10 degrees Celsius. 10 degrees Celsius. We'll convert it into Kelvin scale. What you do to this 10 degrees Celsius, you add 273. Then how much do we get? 283 Kelvin. Your turn, your turn, your turn. 100 degrees Celsius. Convert it into Kelvin. Convert it into Kelvin. Perfect. You add 273, which means you get 373 Kelvin. 200 you add. Adding gives us the Kelvin value. Ehenang tell me, be careful now. Minus 273 degrees Celsius. Minus 273 degrees Celsius. Convert it into Kelvin. Now maths. Minus 273 I have given in Celsius scale. Celsius to Kelvin you add 273. Add 273 minus 273 plus 273 how much? 0. 0 Kelvin. Hari Nelamai. This is what I wrote before. 0 Kelvin is minus 273. 0 Kelvin is minus 273. Now the opposite. Now the opposite. Now the opposite. Celsius to Kelvin you add. Ehenang tell me. Kelvin to Celsius. Kelvin to Celsius. What you do? Kelvin to Celsius. What you do? The opposite. You subtract 270. Celsius to Kelvin you add. Kelvin to Celsius you subtract. For example, let's take 500 Kelvin. Convert it into Celsius. 500 Kelvin converted into Celsius. What you do? Subtract 273. Subtract 273. If I subtract 273, I will be getting 227 degrees Celsius. 227 degrees Celsius. Got it? Another one will work with 100 Kelvin. 100 Kelvin work. Be careful with minus and pluses. 100 Kelvin work. 100 Kelvin minus 273. 100 minus 273, we end up with a negative value. Minus 173 degrees Celsius. Minus 173 degrees Celsius. So remember, Celsius to Kelvin you add. Celsius to Kelvin you add. Kelvin to Celsius you subtract. Now I know it's a bit confusing. Memorize it like this. In theory class, I have told you all to memorize in a way. Have you memorized? C to K, C to K. In alphabetic order, C comes first, K comes next. A, B, C. C comes first. After that only K comes. C comes first, low. K comes next, high. C comes first, low. K comes next, high. Low to high. Low to high, what you do? Add or subtract? Low to high, what you do? Add. So you add 270. Now there's no logic like that. But somehow we have to memorize, no lamai. Memorizing part, whatever the way we want, we can memorize. There's no proper method for that. So memorize it with the logics that you can put there. What's the logic we can put there? C is small, K is big. Alphabetical order, C is small, K is big. So C to K, small to big, you add. Eto big to small, you subtract. Simply put it to the mind like that. Small to big, you add. Big to small, you subtract. Alright? Hurry, you know. Take your heat section. That's the second part in the tube. Temperature is the measure of the mean kinetic energy possessed by the particles that form an object. Measuring temperature, glass mercury thermometer, glass alcohol thermometer, digital thermometer. Temperature scales. Celsius scale. Lower fixed point, melting point of ice at 1 atm pressure, it's taken as 0 degrees Celsius. Upper fixed point is boiling point of water at 1 atmosphere pressure, that is 100 degrees Celsius. Scale divided into 100 division. Fahrenheit scale, lower fixed point is melting point of ice at 1 atm pressure, that is 32. Upper fixed point, that 212 degrees. Fahrenheit scale is divided into 180 degrees. Kelvin scale. Now out of these three scale, which one is the SI unit? Which one is the SI unit? Kelvin scale. SI is Kelvin. Kelvin is the SI unit. Minimum temperature is absolute 0. Temperature difference equal to 1 Kelvin is chosen to be equal to a temperature difference of 1 degree Celsius. Temperature difference 1 Kelvin is 1 degree Celsius. See, that is how the scale is made. That is how the scale is made. See, 1 Kelvin to 2 Kelvin. What's the temperature difference in Kelvin? What's the temperature difference in Kelvin? All of you, what's the temperature difference in Kelvin? 1 Kelvin. That is equal to how much in Celsius? That is equal to how much in Celsius? 1 degree Celsius. 2 Kelvin to 3 Kelvin, what's the temperature difference in Kelvin? This is a bit hard to understand. Put your concentration and listen. 2 Kelvin to 3 Kelvin, what's the temperature difference in Kelvin? 1 Kelvin. What is the temperature difference in Celsius? 1 degree Celsius. So 1 Kelvin difference is taken as 1 degree Celsius. 1 Kelvin difference is taken as 1 degree Celsius difference. Difference, I'm not talking about the temperature. Now don't get confused with, I thought 0 Kelvin is minus 273. This 0 Kelvin is not difference. That's the temperature. 0 Kelvin temperature is minus 273 degrees Celsius temperature. Here I am talking about difference. 2 to 3 difference is 1 Kelvin, that is 1 degree Celsius. 2 to 3 difference is 1 Kelvin, that is 1 degree Celsius. Hurry. Those who find it a bit difficult to understand, I know it's a tough section. Those who find it a bit difficult to understand, answer me this. Tell me 2 Kelvin in Celsius. Convert 2 Kelvin to Celsius. 2 Kelvin temperature is how much Celsius? K to C, K to C, K to C. K to C, K to C, K to C. What you do? Subtract 2 Kelvin. You subtract 273. 2 wala 273 kiyam kiyat thina? Minus 271 degrees Celsius. Tell me 3 Kelvin Celsius. Tell me 3 Kelvin Celsius. Minus 270 degrees Celsius. Minus 271 to minus 270. What's the difference? No math, say. Minus 271 to minus 270. What's the difference? 1 degree Celsius. Here, 2 Kelvin to 3 Kelvin. What's the difference? 1 Kelvin. 2 Kelvin to 3 Kelvin. Difference is 1 Kelvin. Minus 271 degrees Celsius to minus 270 degrees Celsius. Difference is 1 degree Celsius. This difference, both are equal. Not the temperature. Here temperature 2 Kelvin, here temperature minus 271 degrees Celsius. Here temperature 3 Kelvin, here temperature minus 270. Temperatures are not equal. Differences are equal. 1 Kelvin of a difference is there, 1 degree Celsius of a difference is there, both are equal. Understood that? Okay, that's my tough part. I know confusions. So temperature difference equal to 1 Kelvin is supposed to be equal to a temperature difference equal to 1 degree Celsius. Celsius to Kelvin, you add 273. Kelvin to Celsius, you subtract 273. Sorry. Next part. That's it, the initial part. Now moving to the second part of heat lesson. With the previous one locked in your brain, now moving to the second part of heat lesson. Right. Thermal equilibrium. Thermal equilibrium. What is this thermal equilibrium? On a Lamai, let's take, you have an object at a very high temperature. and another object at a low temperature. High temperature object, low temperature object. This is high temperature, this is low temperature, which means we have a difference in the temperature. There is a difference in the temperature. When there is difference in the temperature from high temperature region, to low temperature region, heat begins to flow. From high temperature region to low temperature region, heat begins to flow. From hot object to cool object, heat will flow. Now think, when heat goes from the hot object, what will happen to the temperature of the hot object? Increase the decrease the? Decrease ne, practically think. When hot object releases the heat, when hot object gives off the heat, its temperature decrease. So this one's temperature will decrease. When heat comes to the cool object, what will happen to its temperature? Its temperature will increase. So basically, hot object will cool down, cool object will get hot. Agree? Hot object will cool down, cool object will get hot. So slowly here temperature decrease, here temperature increase. Now for example, let's take initial here temperature is 10 degrees Celsius, here temperature is 0 degrees Celsius. When heat is transferring like that, 10 degrees Celsius will start reducing on the sea. 10 degrees Celsius become 9 degrees Celsius. Meanwhile, heat is coming here, 0 degrees Celsius will increase, 0 become 1 degree Celsius. Furthermore, 9 become 8 degrees Celsius, 1 become 2 degrees Celsius. 8 becomes 7 degrees Celsius, 2 become 3 degrees Celsius. 7 becomes 6 degrees Celsius, 3 become 4 degrees Celsius. Now, 6 become 5 degrees Celsius, 4 become again 5 degrees Celsius. This side temperature decreased, came to 5. This side temperature increased, came to 5. Both the sides 5, 5. Both the sides 5, 5. Both the sides 5, 5. Now tell me, can heat transfer? Both the sides 5, 5. Can heat transfer? No. Even if heat transfers, where to where can the heat transfer? From this 5 to this 5, from this 5 to that 5. No. Heat can't transfer anywhere. Before heat transferred, now heat can't transfer. Why? Both the sides temperatures are equal. This condition is called as thermal equilibrium. So remember, heat will transfer from a hot object to cool object until the two objects gain thermal equilibrium, which means both the sides temperatures are equal. After thermal equilibrium, can the heat transfer? No. Remember, in physics, the word equilibrium means two parties are at the same stage. Force equilibrium. What is force equilibrium? Both the sides forces are equal. Moment equilibrium. What do you mean by moment equilibrium? Both the sides moments are equal. Now think thermal equilibrium. Both the sides temperatures are equal. Understood? Hurry. Perfect. That is thermal equilibrium. Next. Heat capacity. Understand the points. Later we can elaborate and write the definition. Heat capacity. What is heat capacity? Amount of heat required to increase the temperature of an object to increase the temperature of an object by 1 unit. By 1 unit is heat capacity. What is heat capacity? Amount of heat energy required to increase the temperature of a substance or an object by 1 unit. Let's take, I have a substance, I have an object. This object is at 25 degrees Celsius. I want to increase its temperature. I want to bring the temperature to 26 degrees Celsius. 25 to 26, what's the increment here? 1 degree Celsius. Increment is 1 degree Celsius. Tell me that increment in Kelvin. Don't make mistake. Tell me 25 to 26 increment 1 degree Celsius. That increment in Kelvin, that is also equal to 1 Kelvin increment. Increments are equal. We already know that. So 25 degrees Celsius to 26 degrees Celsius. Increment is 1 degree Celsius. That is also equal to 1 Kelvin of increment. That means there is a unit increment. Unit increment. Unit increment. Unit means 1. Unit increment is there. For this to happen, I need to supply heat energy. I need to supply heat energy. How much of heat energy I supply? That is heat capacity. How much of heat energy I supply? That is heat capacity. Amount of heat required to increase the temperature of a substance by 1 unit. Make sense? No? How much of heat energy required to increase the temperature of a substance by 1 unit. Here, how much of heat you supply to increase the temperature. That is its heat capacity. Its heat capacity. Remember, heat capacity depends on two factors. Heat capacity depends on two factors. What are the two factors? One, the substance. Different substances have different heat capacity levels. Some substance, they absorb lot of heat energy to increase the temperature. Some substance, just a little amount of heat is enough to increase the temperature. Some lot of heat you need to supply to increase temperature. Some just a little is enough to increase temperature. So it depends on the substance. Number two, it depends on the mass. Chuti mass, chuti heat is enough. Big mass, lot of heat is needed. Hari? Hari? Right. Heat capacity. Next. මේක දුන්නේ නැහැ ළමයි. What's the symbol we use for heat capacity? There's a symbol for heat capacity. Heat capacity is symbolized as capital C. Keep that in mind. Symbol for heat capacity is capital C. And what's the unit for heat capacity? What's the unit? Joules per degree Celsius or joules per Kelvin. 2 units are there. Joules per degree Celsius or joules per Kelvin. Out of these two, which one is SI unit? Celsius one, the Kelvin one. Always remember Kelvin is SI. Yeah? Always Kelvin is SI. K is SI. Alright. So now going to next part. Specific heat capacity. Specific heat capacity. Specific heat capacity. Specific heat capacity is symbolized as simple C. Simple C. Heat capacity, capital C. Specific heat capacity, simple C. What is specific heat capacity? We'll memorize point by point. What is specific heat capacity? Amount of heat energy required. Amount of heat energy required. Amount of heat energy required to increase the temperature of a unit mass of a substance. To increase the temperature of a unit mass of a substance by 1 degree Celsius. Specific heat capacity. Amount of heat energy required to increase the temperature of a unit mass of a substance by 1 degree Celsius. Let's take, I have a substance. Amount of heat required to increase the temperature of unit mass. What do you mean by unit mass? What do you mean by unit mass? What do you mean by unit mass? Unit means, remember, one. Unit means always one. So unit mass means 1 kilogram mass. So now mass is defined. Previously, is the mass defined? No, previous heat capacity part, mass was not defined. I took any substance of, any mass. Here, mass is defined. What's the mass? 1 kilogram. Unit mass is defined. Let's say this is at 25 degrees Celsius. I want to increase the temperature and bring it to 26 degrees Celsius. Mass won't change, same 1 kilogram mass. Now tell me, what's the increment in Celsius scale? What's the increment in Celsius scale? 1 degree Celsius. It is equal to how much in Kelvin scale? Again 1 Kelvin increment. For this to happen, I need to supply heat. For this to happen, I need to supply heat. How much of heat I supply? Specific capacity. How much of heat I supply? Specific capacity. Hurry. Looking at both, tell me, what's the difference here? What I have additionally added here compared to the previous one? Heat capacity ekatai, specific heat capacity ekatai. What's the difference from what I have additionally added? Mass. Their mass was not defined. Here mass is defined. That's it. There you take any substance of any mass. Here you take any substance of 1 kilogram mass. Now tell me, will the mass affect specific heat capacity? Now mass is defined. Will the mass affect specific heat capacity? Will it affect? No. Previously, mass was affecting. Why? Mass was not defined. I didn't tell the mass. Now, mass is told 1 kilogram mass. Will it affect? No. Mass is always 1 kilogram. It will not affect. Again, I repeat, it will not affect specific heat capacity. I am telling this is 1 kilogram. I think again you can't tell, no, sir, this is 2 kilogram. After I tell for 1 kilogram, we are defining this. You can't change the mass. So will the mass affect? Do any effect there? No. Mass won't affect. Always mass won't affect. Here, heat capacity mass will affect. Remember with the reason, physics is that. We don't go to memorize. Here mass will affect. Why? Mass is not defined. I'm not telling any mass. If I tell a mass, then mass won't affect. Here I'm not telling a mass. Mass will affect. Here I'm telling. This is 1 kilogram, I'm telling. So I think you can't tell, no, sir, this is for 2 kilogram, this is for 5 kilo. I can't bad. I think what by the bad. Hurry. So mass won't affect. So remember, specific heat capacity, mass is not affecting. Mass is not affecting. Mass is not affecting in specific heat capacity. Now only what will affect? Mass is not affecting. Now only what will affect in specific heat capacity? The nature of the substance. Only substance will create an effect. Only substance will create an effect. Only substance. What's the unit? 2 units are there. Joules per kilogram per degree Celsius. Or joules per kilogram per Kelvin. 2 units, joules per kilogram per degree Celsius, joules per kilogram per Kelvin. Now again see the difference there in here. There, a kilogram part is not there. I'm not defining. Now, kilogram part is there. I'm defining. That's the difference. What is SI? What is the SI one? Second one. This is SI. So now we have done heat capacity. We have done specific heat capacity. There is a relationship between heat capacity, that is capital C, and specific heat capacity. There's a relationship between heat capacity and specific heat capacity. What's the relationship? Heat capacity is equal to mass multiplied by specific heat capacity. Heat capacity is equal to mass into specific heat capacity. If I give it symbolically, heat capacity is symbolized as capital C, capital C, capital C is equal to mass is simple M multiplied by specific heat. Specific heat is symbolized by simple C. Specific heat is symbolized by simple C multiplied by simple C. Capital C equal MC. Harine, check with the units for the validity of this equation. What's the unit of heat capacity? Let's take joules per joules per Kelvin. SI unit value. What is the unit of specific heat capacity? Joules per kilogram per Kelvin. Ehenan, tell me, to remove this per kilogram, kg to the power -1, I should multiply it by what? To remove per kilogram and come to this unit. To remove per kilogram and come to this unit, I need to multiply by what? Mathematically, kilograms. So when I multiply kilograms, this kilogram per kilogram cancel off. Joules per Kelvin will come. Again, what's the relationship? Capital C, heat capacity equal mass into simple C, specific heat capacity. Hurry, understand physics and learn. Don't memorize. There's nothing to memorize. Understand and learn. Hurry. Hurry. Finally, how do you calculate heat change? How to calculate heat change? This one anybody knows. There's an equation we use to calculate heat change. Q, that is heat change, is equal to mass multiplied by specific heat multiplied by theta. What is theta? Temperature change. Heat change is equal to mass into specific heat capacity into temperature change. This is heat change. This is mass. This is specific heat capacity. This is temperature change. What is temperature change means? Temperature නෙවෙයි. Temperature change. What is temperature change means? What is temperature change means? Let's take, you are making tea. Initially, the temperature is 30 degrees Celsius for this water. When you heat it, which means when it is dancing, now the temperature is 100 degrees Celsius for this water. Ehenan, tell me what's the temperature change here? What's the change? 70 degrees Celsius. How did you get 70 degrees Celsius? 30 minus 100. Sorry, 100 minus 30. That is final temperature minus initial temperature. Final temperature minus initial temperature. So temperature change is found out by subtracting the final temperature by initial temperature. Tf minus Ti. What? Tf minus Ti. That gives a temperature change. Got it? That's it. Second part of heat is also done. Calculation part is done. Perfect. No? I'm fully caught with some kind of a flame continuous there. Thermal equilibrium means two objects at the same temperature, so no heat flows between them. If a hot object and a cold object are placed together, heat flows from hot to cold. After some time, both become same temperature. At that point, they are thermal equilibrium. Heat capacity, capital C, the amount of heat required to increase the temperature of an object by 1 unit is known as heat capacity of that object. Unit joules per degree Celsius or joules per Kelvin. Joules per Kelvin is the SI. Depends on substance and mass. Specific heat capacity, the amount of heat required to increase the temperature of unit mass of a given substance by 1 degree is known as specific heat capacity. Unit joules per kilogram per degree Celsius or joules per kilogram per Kelvin. SI is Kelvin part. Depends on only substance. Relationship, capital C equal MC. Find the quantity, Q equals MC theta. Before I go to the next part, emphasize on whatever I did until now. I'll give you all 30 seconds until I take my charger and come. Ready? Emphasize on whatever we did until now. Harane. Harane. 1 hour gone. Are you feeling anything down? Yeah. Good luck. 1 hour gone. We have 1000 Zoom, 700 plus YouTube. Currently 1700 joining live in one single session. Hurry. Meanwhile, I wanted to remind about our final seminars. This time I'm doing the final seminars a bit early and finishing. Next week, 19th, to continuously we have final seminars going on. We are going to discuss 50 MCQs in the seminar, plus 50 MCQs for home with the MCQ review book. Structured essay. Target was to do 4 questions in the class, 4 question home. Essay, 4 question in the class, 4 question home. Hema target paper kind of a book bundle made. Separate MCQ booklet is there. Only MCQ booklet is 51 pages. Hema we have made. It will be happening 19th at Kandy, number 0. 20th at Bandaravela, Ideal Institute. 21st at Hatton, BKW Hall. 22nd, nothing. 23rd at Colombo. Colombo, only one place I'm doing at University of Colombo, medical faculty, the main auditorium there. 24th at Nigambu, IMS Institute. 25th, no. 26th at Gaul, Principia Institute. 29th at Kalmone. And Colombo physical seminar is live streamed online as well. Registrations are already going on. So many people are trying to break us down. The first day when we launched our website, with happiness, I am telling, the first day when we started our bookings and all, right? There was a separate gang who wanted to put our website down. Within 2 hours, sent us a cyber attack, right? Now those fellows' IP address are all taken and we have passed the case into cybercrime unit together with CID. They are working on that. 2 hours to break us down. I had a time period where, not very long, 4 years 4-5 years when I called institute whether I can do any classes there, my reply was no. Now I'm very happy because when we start a registration, within 2 hours there are people to break us down. My people. Our registration didn't stop. Now still registrations are going on. You can check our WhatsApp channel. Not in the website. website we ourselves have closed it and kept. We are redeveloping it. Meanwhile, registrations are going manually using a separate method. You can check that. Hurry. Come to the next part. Next, change of state. Change of state. මේවා මේ simple things නේ ළමයි change of state කියන්නේ. State කියන්නේ physical state eh? Change of state are simple things no. What are the three states we have? Solid is there, liquid is there, and gas state is there. Okay, we can convert solid state into liquid state. How to convert solid state into liquid state? You heat it. We can convert liquid state into gas state. How to convert liquid to gas? Again, you heat it. Can we do it reverse? Yes, you can. Gas can be converted to liquid. You condense it. You cool it down. Liquid can be converted into solid. Again, you cool it down. So the states can be changed from one state to another. You can change, right? First, solid to liquid. Solid to liquid is what you call melting. Solid to liquid is what you call melting. Solid to liquid is melting. Liquid to gas. Liquid to gas is what you call. There are two words we use for that: boiling or evaporation. Evaporation. Different definitions are there. I'll give you the definition separately. Gas to liquid is called condensation. Liquid to solid is called freezing. They were simple things. An important point. Important point. Melting point. Melting point. Melting point. What is melting point? First of all, what is melting? Melting is converting a solid into liquid. Converting a solid into liquid is melting. Then what is melting point? There is a constant temperature at which a solid that is being heated turns into liquid. There is a constant temperature at which a solid that is being heated turns into liquid. That temperature is called melting point. You all tell me, constant temperature can the temperature ever change? Can the temperature ever change? No, definition is telling it's a constant temperature. That temperature can't change. But that melting point depends on pressure. It depends on pressure. Can you remember at the beginning of this section I told you? Melting point depends on pressure. When Celsius scale was defined, they defined the melting point of ice at 1 atm pressure. Why? If pressure changes, melting point will also change. So melting point depends on the pressure. Hurry. Next, freezing point. There's a point called freezing point by definition. What is freezing point? What is freezing? A liquid turning into solid. Freezing. What is freezing point? There is a constant temperature at which a liquid that is being cooled. That is being cooled. A liquid that is being cooled. That is being cooled turns into solid. There is a constant temperature at which a liquid that is being cooled turns into solid. Now we all tell me, what is cooling? Supplying heat, releasing, removing heat. Cooling is supplying heat, removing heat. Removing heat. So there is a constant temperature at which a liquid that is releasing heat, that is being cooled down, turns into solid. That temperature is what you call freezing point. Constant temperature at which a liquid that is being cooled turns into solid. That is freezing. Remember, this melting point and freezing point are equal in value. Melting point and freezing point are equal in value. By definition, they are different. Melting point is temperature at which a solid that is being heated turns into liquid. Freezing point is temperature at which a liquid that is being cooled turns into solid. But they are equal in values. Melting point of ice. Melting point of ice is 0 degrees Celsius at 1 atm pressure. Same way, freezing point of water. Freezing point of water is also 0 degrees Celsius. At 0 degrees Celsius, ice that is being heated turns into liquid. At 0 degrees Celsius, liquid water that is being cooled turns into solid. So they are equal in values. Next, boiling point. Boiling point. What is boiling point? Now, what is boiling? A liquid turning into gas. Liquid to gas is boiling. Now, what is boiling point? There is a constant temperature at which a liquid that is being heated turns into gas. There is a constant temperature at which a liquid that is being heated turns into gas. On that temperature is called boiling point. This also depends on pressure. If pressure changes, boiling point will change. Okay? Huh? Change of state of matter. Melting point. Melting point is the temperature at which a solid changes into liquid when heated. For a given substance, melting point depends on pressure. Freezing point. The freezing point is the temperature at which a liquid changes into solid when cooled. For a given substance, freezing point also depends on pressure. Boiling point. Boiling point is the temperature at which a liquid changes into vapor by forming bubbles throughout the liquid. Ar monada me bubbles part kiyanne? Later on, when I am teaching vaporization, I will teach you. Boiling point of a substance depends on pressure, and it is usually stated as 1 atmospheric pressure. Right. Next, latent heat. Next section, there you go. Latent heat. Latent heat. What is latent heat? Now listen very carefully. Yeah? Again, a bit of a confusing point we are coming across. So listen very, very carefully. What is latent heat? Now let's take a substance is changing its state by absorbing heat. For example, a solid state substance is changing the state into liquid state. State changes occurring. State changes occurring. State changes occurring. During the state change, there is a certain amount of heat you supply. There is a certain amount of heat you supply. And the solid, it will turn into liquid. You all tell me, a solid turns into liquid at what temperature? At what point? At the melting point. Don't tell 0. 0 is only for water. Tell melting point. A solid turns into liquid at the melting point. So now I have a solid at its melting point. It is going to turn into liquid at the same temperature. During this time, there is a certain amount of heat you supply. The amount of heat you supply during this change in state is called as latent heat. Then what is latent heat? The amount of heat required or the amount of heat absorbed by a substance during the change in the state. During the change in the state. During change in state, will the temperature change? Can the temperature change? Go tell me melting point. Can it ever change? It's a constant temperature. It can't change. Can the boiling point change? No. So you all tell me, during change in state, can temperature change? No. Temperature does not change. Does not change. During melting, melting point is a constant temperature. Until all the ice melt and finish, temperature won't change. A melting point of ice is 0 degrees Celsius at 1 atmospheric pressure. So if you are melting ice, until all the ice melt and finish, temperature will be 0 degrees Celsius. Why? Melting is taking place. Boiling. Boiling is a constant temperature. Can that constant temperature ever change? When you are boiling water, until all the water boils and finishes, the temperature in that water will be 100. So remember, melting point, boiling point, state changing temperatures are constant temperature. Can the temperature ever change? No. So during a state change, can the temperature change? No. Even though temperature is not changing, the state is changing. Solid is turning into liquid, or maybe liquid is turning into gas. State is changing. So temperature is not changing, temperature is not changing, but the state is changing. And during that time, a certain amount of heat is being absorbed. Harini, if you're turning a solid ice into liquid water, you have to heat it. You have to supply heat. It will absorb a certain amount of heat. So it is taking some heat. It is absorbing a certain amount of heat. How much of heat it absorbs? Latent heat. Then everything together. What is latent heat? The amount of heat energy required for a substance to change the state without changing the temperature. Again, I repeat, the amount of heat required for a substance to change the state is changing, without the changing temperature. Temperature is not changing, it is constant. Temperature won't increase, temperature won't decrease, without changing the state. That is latent heat. That is latent heat. Sorry? Got it? Right. One more time. What is latent heat? I was taking the YouTube. Some fellows are there. I know නිකන් අර YouTube එකට නිකන් ඇවිල්ලා නිකන් messages දාගෙන යනවා. ඒක නිකන් check කරා දැන් time out දාගෙන යනවා. හරිනේ? Latent heat. Again, what is latent heat? The amount of heat energy required, the amount of heat energy absorbed by a substance or required by a substance to change the state. State is changing without the change in the temperature. Without the change in the temperature. That is latent heat. That is latent heat. Remember, there are two types of latent heat. Two types of latent heat. What are the two types of latent heat? What are the two types of latent heat? One, latent heat of fusion. Latent heat of fusion. Two, latent heat of vaporization. Two types of latent heat of fusion, latent heat of vaporization. I will teach fusion, you all are going to tell me about vaporization. I will teach fusion, you are going to tell me about vaporization. First going to latent heat of fusion. What is fusion? What do you mean by fusion? A solid substance turning into liquid. A solid turning into liquid. That means, can you see? State is changing, state is changing. State is changing. Y'all tell me, solid to liquid state change happens at what point? Melting point, the boiling point? Melting point. Y'all tell me that melting point is a variable temperature, the constant temperature? Constant temperature. Will the temperature change until the solid melt and finishes? Will the temperature change until the solid melt and finishes? No. But for this to happen, you have to supply some amount of heat. You have to supply some amount of heat. How much of heat you supply? Latent heat of fusion. How much of heat you supply? Latent heat of fusion. So putting everything together, what is latent heat of fusion? The amount of heat energy required for a solid substance at the melting point to turn into liquid without change in the temperature is latent heat of fusion. Again, one more time. The amount of heat required for a solid substance at the melting point to turn into liquid without change in temperature, latent heat of fusion. One more time, follow my words. The amount of heat required, how much of heat you are getting for a solid substance at the melting point to turning into liquid without change in temperature. Temperature is not changing. Latent heat of fusion. Okay. With that logic, you all try to build up the definition for latent heat of vaporization. What is vaporization? What state to what state? What state to what state? Liquid to gas. Liquid to gas. Liquid turning into gas. That is vaporization. Liquid turns into gas at what point? Liquid to gas, boiling point. So this is happening at boiling point. Constant temperature, the variable temperature, the constant temperature. So can the temperature change? No. But is the state changing? Yes. But for this to happen, you have to supply some heat. The amount of heat you supply is latent heat of vaporization. So put them into a nice definition. What is latent heat of vaporization? The amount of heat energy required for a liquid substance at the boiling point to turn into gas at the same temperature is latent heat of fusion, latent heat of vaporization. One more time, what is latent heat of vaporization? The amount of heat energy required for a liquid substance at the boiling point to turn into gas without change in temperature, latent heat of vaporization. So simply put it in mind, heat energy required for a solid to convert to liquid at the melting point without change in temperature, fusion. Heat energy required for a liquid to turn into gas at the boiling point without change in temperature, vaporization. Got it? Okay. Yes, yes. Okay. Hot. Now going one more step ahead. Now going one more step ahead. Latent heat of fusion done. Now going to specific latent heat of fusion. Specific latent heat of fusion. Remember, the moment you hear the word specific, that means it is defined for 1 kilogram. The word specific means defined for 1 kilogram. Then what is specific latent heat of fusion? Now what is latent heat of fusion? Let's take, you have a solid, it is turning into liquid. Now solid's mass is defined. Specific. Specific yani solid's mass is 1 kilogram. So 1 kilogram of solid is going to turn into 1 kilogram of liquid. Solid turns into liquid at the melting point. It's a constant temperature. Temperature is not changing. During this time, you have to supply a certain amount of heat. That heat is defined as specific latent heat of fusion. Then what is specific latent heat of fusion? The amount of heat required for a unit mass of solid substance at the melting point to turn into liquid at the same temperature. Specific latent heat of fusion. Again, look at the definition. The amount of heat energy required for a unit mass of solid substance at the melting point to turn into liquid at the same temperature. What's the additional word I have added in the definition? What's the additional new word I have added? Unit mass. Previously, mass was not defined. So remember, physics is not hard. Some logics are there. The word specific means unit mass. Before also. Heat capacity, specific heat capacity. Heat capacity is generally defined. Specific heat capacity is defined for unit mass. Latent heat of fusion, specific latent heat of fusion. Latent heat of fusion is generally defined. Specific latent heat of fusion is defined for unit mass. So here you define for unit mass 1 kilogram mass. Tell me, now think and tell me. Does specific latent heat of fusion depend on mass? If you understood physics, you can answer this. This is not there in the textbook. Does specific latent heat of fusion depend on mass? Mass is defined. Does it depend on mass? No. The moment I tell specific, I'm defining the mass. When I define the mass, I'm telling unit mass. After I tell unit mass, can you come and tell, no sir, that is 10 kilogram, that is when I define the mass 1 kilogram, that is 1 kilogram, you can't change it. So does it depend on the mass? No, it doesn't depend on the mass. Hurry. Now come to the definition of next part. Specific latent heat of vaporization. If you understood everything, you can tell me all the things about specific latent heat of vaporization. What is latent heat of vaporization? A liquid turning into gas. Liquid turns into gas at what temperature? Boiling point nilamai. This is a constant temperature. Temperature does not change. But for this to happen, you have to supply heat. And now tell me, specific yanni, you are defining for how much of mass? Unit mass, 1 kilogram mass. 1 kilogram mass. What's the definition of specific latent heat of vaporization? The amount of heat energy required for a unit mass of liquid substance to be at the boiling point to be turned into gas at the same temperature. The amount of heat required for a unit mass of liquid substance at the boiling point to be turned into gas at the same temperature. Correct? Yeah, unit mass means always 1 kilogram. That's how we take. Correct? Latent heat. The heat absorbed by the system without changing its temperature. And that word is important. Without changing the temperature, while the change of state is taking place. Temperature not changing, temperature not changing, but state is changing, is known as latent heat. Fusion is the change of solid into liquid. The heat absorbed during melting without temperature change is latent heat of fusion. At the boiling point, a liquid changes into vapor by absorbing heat without temperature. This is called latent heat of vaporization. Specific latent heat of fusion. The amount of heat required to change the state of a unit mass of a solid substance at the melting point into liquid state is known as specific latent heat of fusion. What should be the unit without looking at it? The specific latent heat of fusion, what should be the unit? Heat, latent heat. Heat is joules. Specific Q1, it is defined for how much of mass? 1 kilogram mass per kilogram. Or in balloon, joules per kilogram. Joules per kilogram. Specific latent heat of vaporization. The amount of heat required to change the state of a unit mass of a solid substance. What have we got? Typing error is there. The amount of heat required to change the state of a unit mass of a liquid substance. Liquid substance ne cut it me. Liquid substance cut it me. Liquid substance at its boiling point into gas state is known as specific latent heat of vaporization of that substance. Unit is again joules per kilogram. Joules per kilogram. Now coming to Vaporization. 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 Right. Vaporization. What is vaporization? A liquid turning into gas. A liquid to gas is vaporization. Vaporization can take place in two ways. One, boiling. Two, evaporation. Evaporation. Vaporization can take place in two ways as boiling and evaporation. What is boiling? If vaporization take place at the boiling point, that is boiling. If vaporization, that is liquid to gas, is taking place at the boiling point, you call it boiling. Then what is evaporation? What is evaporation? If vaporization take place at a temperature less than the boiling point, that is evaporation. Now you'll ask me, sir, can vaporization take place at a temperature less than boiling point? Can liquid turn into gas at a temperature less than boiling point? Yes, can. That is why I am teaching. If can't, I won't teach, no? It can, believe me. You can. You can turn liquid to gas at a temperature less than the boiling point. Right? So if the vaporization take place at the boiling point temperature, that is boiling, at a temperature less than the boiling point, that is evaporation. That is evaporation. Huh. One more point. Boiling take place from the bottom of the liquid. From the bottom of the liquid itself, liquid will turn into gas and goes out. From the bottom, from inside the liquid, it turns into gas and goes out. So one big observation during boiling is you can see bubbles are formed. Bubble formation is an observation you can see. Bubbles are formed during boiling. Bubbles are formed. Now during evaporation, vaporization take place at the surface. The surface particles will break the bond. Surface particles will break the bond and directly go to the atmosphere. Surface particles break the bond and directly goes to the atmosphere. That is evaporation. So remember, boiling take place from the bottom of the vessel. You can see bubbles are formed. Evaporation take place at the surface, no bubble formation, directly the surface particles will diffuse into the atmosphere. What are the example? Boiling. Let's say you are making tea, you boil the water. You can see water, bubbles are formed and bubbles releases. Vaporization take place from the bottom there. So when you are making tea, you are boiling water. Now if you take seawater evaporating. Seawater evaporating. That is evaporation. Now, during seawater evaporation, have you all seen any bubble formation inside the sea? Does the sea forms the bubble and go up? Does the sea comes into the boiling point and boil? There are no boiling. Sea doesn't boil. If sea boils, we can't go and swim there. We can't go and play there. If sea boils, it will come to 100 degrees Celsius. No. Without coming to 100 degrees Celsius, without forming bubbles from the bottom, directly the water evaporates. So we tell seawater evaporates. Water in the cooker boils. And now you all tell me, when we sweat, that water will vaporize and go. That is what? Boiling the evaporation. Sweat is boiling the evaporation. Evaporation. Why do we boil? Do we come to 100 degrees Celsius and our sweat goes up? That is evaporation. We put dress outside for it to dry up. That is boiling, the evaporation. Evaporation. Dress doesn't boil, no. Do we tell my t-shirt is boiling 100 degrees Celsius? Dress doesn't boil. The water in the dress will evaporate. So now understood the difference between boiling and evaporation? Yes? Yes, clear. Yes. Hot. Hot. Evaporation and vaporization. Evaporation and vaporization are processes in which liquid changes into gas. Vaporization occurs in two ways, that is boiling and evaporation. Vaporization occurs two ways, boiling and evaporation. Boiling occurs at the boiling point and take place throughout the liquid with bubble formation. Evaporation occurs below the boiling point and only at the surface of the liquid. No bubbles are formed. Next part of the lesson. Next part of the lesson. Next part of the lesson. Thermal expansion. Thermal expansion. What is thermal expansion? A chuti object turning into a big object due to heat. Thermal expansion. Now, I don't tell a small toy car, when you heat it, it will become a very big giant car. A small increase in the size will take place. A small expansion will take place. That is thermal expansion. So when you heat any object, that object's size, that is dimension, increases by absorbing heat. That is thermal expansion. Remember, thermal expansion can take place in solids. Solids can expand. Solids can expand. Solids can expand. Thermal expansion can take place in liquid. Liquids can expand. Thermal expansion can take place in gas. Gases also can expand. Right? Using solid expansion, we can do some applications. What are the applications of solid thermal expansion? What are the applications of solid thermal expansion? Number one, if you take railway tracks, between the track lines, there is a small gap placed. Between the track lines, they will keep a small gap. Why? No enough iron in Sri Lanka, so that they keep some gap there. Nah. That is because during daytime, these railway tracks will absorb the heat and expand. During daytime, it absorbs the heat and expand. So for it to expand, we need to leave some gap. Then only it can easily expand. It can come closer. So during daytime, it absorbs the heat and expand. During daytime, it absorbs the heat and expand, comes closer. During night time, it will cool down. When it cools down, it contracts. Daytime, it absorbs the heat and expand. During night time, it cool down. When it cools down, it contracts. So for it to expand and contract, we need to leave gap. So gaps in between railway track. Gaps in between railway track. Those are given in the tube. Gaps in between railway track. Next, fitting iron rim in wooden cartwheel. Fitting iron rim in wooden cartwheel. Next, if you look at street wires are hung a bit loose. Why they hang it a little bit loose? During daytime, it will absorb the heat, expand, it will become loose. During night time, it will contract and become straight. So street wires hanging loose. Next, bimetallic stripe. What is bimetallic stripe? Two metals of different expansivity are riveted together, are fixed together. They have different expansivity. When you heat it, they have different expansivity. Now, for example, let's take the bottom one expands more, Meanwhile, the top one expands less. So when I heat the full stripe, bottom expands more, top expands less, the whole stripe will bend. Bottom expands more, top expands less, the whole stripe will bend. Bimetallic stripe. Where bimetallic stripes are used? In electric iron, electric oven, bimetallic stripes are used to control the heat. Next, liquid expansion. Where liquid expansion is used mainly when making thermometer. What thermometer? Digital thermometer. Digital. Alcohol and mercury thermometer. Alcohol mercury thermometer works based on the principle of liquid expansion. Additionally, remember gases also can expand. There is no any practical usage of this, but remember gases also can expand. Thermal expansion, solid expansion, gaps in the railway track, inserting iron rim to a wooden cart wheel, electricity cables fixing loosely by metallic stripe. Liquid expansion, alcohol mercury thermometer. Also remember gases can expand. Last part of the lesson. Last part of the lesson. Almost 2 hours. Now we are completing our first 2 hours. Out of how many hours? 8 to 4 that side 4, this side 4. Out of 8 hours, first 4 hours is almost getting complete. 6 hours to move. Go. 6 hours to go. Hurry. Right. Last part. Heat transfer. What is heat transfer? I was already talking. Heat energy flows from a hot substance to a cool substance. From a substance that is at a high temperature to a substance that is at a low temperature, heat energy flows. That is heat transfer. Heat transfer occurs in 3 ways. There are 3 methods of heat transfer. What are the 3 methods of heat transfer? Conduction, conduction, convection, convection, and finally radiation. Conduction, convection, radiation. Conduction. What is this conduction? In conduction, conduction take place in solids. Conduction take place in solids. What happens in conduction? If you take solid, particles are tightly packed. Let's take you heat. Let's take you heat. You supply heat at this corner. When you heat, temperature increase. Go tell me, in the temperature increases, what happens to the kinetic energy? When the temperature increases, kinetic energy increases. When kinetic energy increases, this particle begin to vibrate, knocks on the other, that vibrate, knocks on the other, that vibrate, knocks on the other. One by one they knock and finally comes up to there. Now the final particle is also vibrating. Vibration is what? Kinetic energy. Kinetic energy is what? High temperature. Which means, can you see, the heat from here has transferred up to there. That is heat transfer through conduction. Only occurs through what? Solid. Why? Particles are tightly packed. If particles are very far, can they knock and transfer the heat? Only take place in solids. Only in solid. Out of metals and non-metals, who are good conductors? That is, they are from grade 6. Metals are good conductors. Why? Because metals, other than the atomic particles they have free electrons. They have free electrons as well. So not only atomic particles help in conduction, also the free electron, they are also particles. Free electron also help in conduction. So metals are good conductors of heat because they have atomic particles plus free electrons. Again I repeat, they have atomic particles plus free electrons. Convection. Convection. Convection take place only in liquids and gas. What happens in convection? What happens in convection? Now let's take This is a gas layer. These are gas layers. Gases, liquids, they are formed as layers. Layer by layer arrangement is there. These are gas layers. First layer, second layer, third layer. These are gas layers. Now let's take, you supply heat to the bottom layer. When you supply heat to the bottom layer get heated. So you all tell me, when a layer get heated, what will happen to that layer? It will expand. So the bottom layer expand. When it expands, its volume increase. When volume increases, what happens to the density? Increase the decrease, the mathematical tell me. When volume increase, what happens to the density? Density decrease. How? Density equal mass over volume nilamai. When the denominator increases, final value will decrease. So density will decrease. Now the bottom layer density has decreased. It has absorbed the heat. It has absorbed the heat. After absorbing heat, its density has decreased. So now it is low dense, therefore it goes up. Low dense layer goes up. Second layer is high dense compared to the first layer. So high dense layer comes down. It gets heated, it goes up. Third layer comes down. It get heated, it goes up. Again first layer get heated, goes up. Second layer get heated, goes up. Third layer get heated, goes up. Again first layer goes up. Second layer goes up. Layer by layer they get heated and goes up. Due to that, heat will start flowing upwards. Heat starts flowing upward. This is what? Convection. Layer by layer they get heated, goes up. Heat flows upward. Okay, and remember in convection, there is a direction in which heat flows. Heat only flows what direction? Upward direction. No sideways, no downwards, nothing. Heat layer get heated, it goes up. Goes up now, heat only travels upward. Okay, now can this happen in solids? Practically think and tell me. Understand physics and learn, don't memorize. Can this take place in solid? Nanny, solids particles are tightly packed. Can a layer absorb heat and go up? Can layers flow in a solid? No. If the layers can't flow, can convection take place in solid? So remember, convection only take place in liquids and gas, because liquids and gas can flow. Layers can go. There are two applications of convection. One, sea breeze, and two, land breeze. Sea breeze and land breeze. First going to sea breeze. Sea breeze and land breeze. Make a land. This, that is the sea. Now it is daytime. And sun is there. Right. Sun is also there. Sun is also there. Now during daytime, land, sea, everything get heated. But which one get heated the most? Out of land and sea, which one get heated the most? Land. Daytime, land get heated the most. Just think, 12 o'clock, not night. Physics night, never. Not night 12 o'clock. Daytime 12 o'clock. Can you walk in rocks without wearing slippers? Nanny, aye. Very hot. But we can walk in the sea. We can walk in the water. Why? During daytime, land get heated faster. Land get heated more compared to the sea. Aye? That's because specific heat capacity of land is low. Specific heat capacity of sea, that is water, is high. Water has the highest specific heat capacity, 4,200 joules per kilogram per degree Celsius. Highest can be. It has kind of a high specific heat capacity, 4,200 joules per kilogram per degree Celsius. Very high specific heat capacity. Very high specific heat capacity means what? Lot of heat is needed to increase the temperature. Lot of heat is needed. Lot of heat is needed to increase the temperature. Now you can't increase its temperature easily. It's a very good coolant. You can even put it in vehicle radiators. Land is not like that. Specific heat capacity low. Less heat is needed to increase the temperature. So land get heated faster. As the land get heated, the air layer above land get heated. So you all tell me, when the air layer above land get heated, when the air layer above land get heated, when the air layer above land get heated, what will happen? Its density, its volume increase, density decrease. Then it goes up. Then it goes up. On Ivalan, it get heated. When it get heated, air layer, dongala, it goes up. Now air layer went up. Do we have anything here? Do we have anything here? No, there is a gap. There is a gap formed. There is a gap formed there. To fill that gap, air from the sea will flow to the land. Air from sea flows to the land. From sea, it comes to the land. You call it sea breeze. You call it sea breeze. Hurry. This is due to convection. Due to convection only air layer goes up. This is due to convection. Sea breeze. එතකොට land breeze කියන්නේ land breeze occurs at night time. Land breeze occurs at night time. Rather than now, during our physics night, land breeze is occurring night time. I'll only draw the moon. I will not draw any stars because all the stars are here. I'll not draw any stars here. Hurry. So moon is there. Onnala my land. Onnala my land. And the sea. And the sea. Now during night time, things become cool. During night time, things become cool. Right? Land become cool, sea become cool, but which one cools down faster? What cools down faster? What cools faster? Again land, not sea, not water. Land cools faster. Keep that in mind. Always land is faster. Land get heated faster, land get cooled down faster. Why? Again, same logic. Its specific heat capacity is low. If the specific heat capacity is low, it needs less heat to increase temperature. Same way, it has to release less heat to decrease temperature. So remember, specific heat capacity low now, it gets heated also faster, it cools down also faster. So during night time, land is cool. Comparatively, sea is hot. Now I don't tell sea is boiling at night time. Sea is also cool at night time, but compared to land, sea is somewhat hot. If you want, I have told this to theory class students. If you are planning to go to beach, then keeping 1 month for the exam. After the exam, you'll be going on trips. No, trip pack plan. If you are going to go to sea, you are planning to go for a beach. Try to go early morning. Why? One thing, no one is there. You are free. And early morning, you might think seawater is cool. Nah. Seawater is hot. Believe me, if you want, go and see. Seawater is hot at night time. Early morning when you go night time, you can't go no. Early morning කිව්වම 3-4 වගේ go, it will be somewhat hot. Right? So do it and see after the O-level. After the O-level, if you are planning to go to any beach. So however, during night time, land is cool, sea is hot. Now sea is hot. Sea is hot. Now think, there are air layers above the sea. There are air layers above the sea. There are air layers above the sea. You all think, Now you all think. Sea is hot. Then what will happen to these air layers? Air layers also get heated. When it gets heated, its volume increase, density decrease. It goes up. It goes up. During night time, sea is hot, air layer above the sea get heated. When it gets heated, air layer goes up. Once the air layer goes up, here you have a gap. To fill that gap, air from land will blow to the sea. Air from land blow to the sea. You call it what? Land breeze. Land breeze. Remember, during night time, wind flow is towards the sea. During daytime, wind flow is towards the land. If you fly a kite during daytime, kite will be flying that way towards the land. If you fly a kite at night time, kite will be flying in that direction. Okay. And y'all tell me, usually fishermen go to the sea at what time? Daytime, the night time. Fishermen go to the sea at what time? Daytime, the night time. Night time. Why? Family problems. Oh, that's because during night time, wind is blowing to the sea. So they just need to put their boat into the sea. Wind is flowing towards the sea, no? Wind is flowing towards the sea, no? Wind will push the boat and take. Wind will directly push the boat and take it to the sea. And they return during daytime. Can come during daytime. They return during daytime. Right? Huh? That is sea breeze and land breeze. Those are applications of convection. Ne? Sea breeze, land breeze. Finally, go. Radiation. Radiation. Now see, conduction take place in solid. Convection take place in liquids and gas. Then both of them need a medium. Radiation do not need a medium. Medium is not necessary. Medium is not necessary. What's the best example for radiation? Heat from sun reaching the earth. Heat from sun reaching the earth. Example for radiation. Another example, let's say you have fire. I'll give point A, point B, point C. Let's say you're keeping hand at A, B, C, A, B, C. Where you feel the highest heat, A, the B, the C, the. Where you will feel the maximum heat, B. Why? Due to what heat transfer? Due to what heat transfer? Hey, Lama, I am teaching radiation doesn't mean all my question answers become radiation. That radiation. Lama, you think. Here to here, what is there? Air is there. Heat is flowing upward. Upward is what? Upward is what? Convection. This is due to convection. Upward is due to convection. But still, if you keep the hand sideways, sideways also you will get heat. Sideways heat heat sideways also you get heat. That is due to what? Is it conduction? Surely no. Is it convection? Convection is upward. Sideways is due to radiation. Sideways is radiation. Finally, dark, rough surfaces absorb a lot of radiated heat. Light, polished substances reflect a lot of radiated heat. Dark, rough absorb, light, polish, reflect. Heat transfer. Conduction, convection, radiation. Conduction only in solid. Metals are good conductors. Convection only in liquids and gas. Heat flows upward by convectional current. Sea breeze I have given. Land breeze given. Radiation do not require a medium. Heat from sun to the earth. Heat from fire transferring sideways. Dark rough surface absorb. Light and polished surface reflect. Ta-da! What's the time? Sorry. 10:10. We have come to the break time. This is your dinner break. According to our plan, 10 to 10:30 p.m. you have the dinner break. Take your dinner. Don't eat lot. After that, you will feel sleepy. Eat to what you need and come back, and then we'll continue. 10:30 we are starting electromagnetism. Right? Check one. Check one. Hurry, right. Henang, heat lesson is done. I hope you all had a short break as well. Just confirm me, is audio, video, is all the dios perfect? Put a thumbs up. Yes. All good. All perfect. Hurry, right. Henang will start our second stage work. Heat is done. Second stage is electromagnetism. Second part, electromagnetism. This will go until about 12, 10, 12, 15. At 12:15, you will have the talent show. Hurry. Right. එහෙනම් electromagnetism, electromagnetic induction section. Electromagnetism, electromagnetism and electromagnetic induction. Electromagnetism, electromagnetic induction. On listen, ne? Electromagnetism, electromagnetic induction. In this lesson, you learn about 4 things. Number 1, we learn about magnetic effect of current carrying conductor. Magnetic effect of current carrying conductor. That's the first section. Second section, force acting in a current carrying conductor placed in magnetic field. In simple terms, you call it electromagnetism. Third section, electromagnetic induction. Third, we learn about induction. And finally, we learn about transform. Those are the 4 sections that we have to cover under this section. Nothing big. Every section is interconnected. Each section is interconnected one by one. They are connected. Right. Starting with the first one, magnetic effect of current carrying conductor. Magnetic diago effect of current carrying conductor. Magnetic effect of current carrying conductor. What is this magnetic effect of current carrying conductor telling us? Very simple. Theory is very, very simple. What is magnetic effect of current carrying conductor telling us? Let's take, you have a conductor carrying current. A conductor carrying current. For example, there is a, let's take, wire in which current is flowing. A conductor carrying current. When you have a conductor carrying current around the conductor, you call it in the vicinity of the conductor. Around the conductor, in the vicinity of the conductor, there will be a magnetic field. Actually, the correct symbol for magnetic field is capital B. That's the correct symbol. That's the correct symbol for magnetic field. But I will use M so that it's easy for you to understand. But remember, the correct symbol is capital B. So remember, when current flows through a conductor, around the conductor there will be a magnetic field. That is our first theory. Magnetic effect of current carrying conductor. Harini, around a current carrying conductor, there is magnetic field. Really, it is there, right? Around any current carrying conductor, there is a magnetic field. Now, for example, if you take this charger, the charger wire, let's take current is flowing through this. Let's say current is flowing through this. I am sending current through this. When current flows through this, around this conductor, that is what you call as vicinity of the conductor. Around this conductor, there will be a magnetic field. Really, there will be. Believe me, really, there will be a magnetic field. We have never thought of that. Really, it is like that, right? When I connect it to the plug point and when I send current through this, there will be a magnetic field around it. Any wires that you have in the house, when you send current through that wire, around that wire, there will be a magnetic field. Not a large magnetic field, a minute magnetic field will be there, depending on the amount of current that flows. A minute magnetic field will be there, but however, there is a magnetic field around the conductor. Now, there is a method to find out the direction of this magnetic field. Direction of the magnetic field. You can find out the direction of magnetic field. Now here, I have drawn it in that direction. There's a method to find out. What is the method? There are two rules to find the direction of magnetic field. There are two rules to find the direction of magnetic field. What are the two rules? One, Maxwell's corkscrew rule. And two, right hand grip rule. Maxwell's corkscrew rule and right hand grip rule. I'll teach Maxwell's corkscrew rule, but don't use it. In theory classes, I have told the theory students, don't use it. It's a bit hard, it's a bit confusing. Use the right hand grip rule, but just know what is Maxwell's corkscrew rule and what is that. That point you know, but don't go to use it. What is Maxwell's corkscrew rule telling? What is a corkscrew? Corkscrew is a device like this. A handle is there, a screw is there, usually used to open bottles with wooden lid. There are bottles with wooden lid, no wine bottle same. If you want to open, you keep the corkscrew on top, you rotate it downwards. When it goes down, you hold it, take it out. That's the use of a corkscrew. Why that is coming here? Using this corkscrew, you can find the direction of magnetic field when you know the direction of current. How? You send the tip of the corkscrew. You send the tip of the corkscrew towards the direction of current. You send the tip of the corkscrew towards the direction of current. When you send the tip of the corkscrew towards the direction of current, there will be a certain direction in which you rotate the corkscrew. The direction of rotation of the corkscrew is the direction of magnetic field. Is the direction of magnetic field. Now, if I want to send the corkscrew down, I should rotate it anti-clockwise. That is the direction of magnetic field. Simply, it's like this. Now, let's take, you have a bottle. I'll bring another bottle. Hurry. Bottle. This lid. I want to send the lid downwards. I want to send the lid downwards. I want to send the lid downwards. If I want to send the lid downwards, I have to rotate it in a certain direction. This direction I have to rotate. Harin, this direction I rotate. That direction I rotate. What is that? Clockwise direction. So if I want to send it down, I need to rotate it clockwise. I want to send it down. That's the direction of current. I rotate it clockwise. That's the direction of magnetic field. You all think and tell me. If the current is flowing upward, If the current is flowing upward, now I have to bring the corkscrew up. Now I should bring the corkscrew up. Now think and tell me, if I want to bring the corkscrew up, which direction I should rotate it? Now which direction I should rotate? Anti-clockwise I need to rotate. I have to rotate it anti-clockwise. Then that's the direction of magnetic field. That's the direction of magnetic field. That's the direction of magnetic field. Alright. So what is Maxwell's corkscrew rule telling? You point the tip of the corkscrew towards the direction of current. Then direction of rotation of the handle gives us the direction of the magnetic field. But don't think about corkscrew, think about a bottle lid. If you want to send the bottle lid down, you rotate it clockwise. If you want to bring the bottle lid up, you rotate it anti-clockwise. Down, current flow, clockwise, magnetic field. Up, current flow, anti-clockwise, magnetic field. But even though I tell like this, don't use this in the exam. Some fellows don't know which direction you have to rotate it to rotate a lid to bring down and bring up. No? Some fellows have a confusion in that. Downward, clockwise, anti-clockwise, just think. Suddenly when you start thinking, suddenly we go off. Can't think. Again, those are things that we do without our consciousness. No? Oh, yeah, do we think and open a bottle lid? Bottle lid is there. I need to open it. Then I have to rotate it. And do we think and do that? Nanny. Oh, yeah, you start opening it and you start drinking the water, talking all the gossips with your friend. We don't realize that. So it's hard to think. Now, if you are a person who realizes, Hari, come on, use Maxwell corkscrew rule. Otherwise, don't use Maxwell corkscrew rule in practical scenarios. But just know the rule. Then what's the rule you're going to use? Right hand grip rule. What is right hand grip rule telling us? Okanang lazy lamai. Applying that is lazy. Easy. Now let's take, you have a conductor where the current flows in that direction. Now what you do? You take the conductor on your right hand, your eating hand. You take the conductor on your right hand such that thumb points the direction of current. Now, for example, here current is flowing in that direction. You take the conductor on your right hand such that thumb points the direction of current. When thumb points the direction of current, your other four fingers will point the direction of magnetic field. Thumb points the direction of current, current is that direction. Other four finger will show the direction of magnetic field. So here current is flowing in that direction. Other four fingers are this way. This way is what way? That way is what way? Mehemaini. This is the direction. That's the direction of magnetic field. That's the direction of magnetic field. Alright? Easy, compared to that, this is easy. Alright? Now, marking magnetic field like this, is it standard? No. Marking magnetic field like this, is it standard? No. For that, we use symbols. There are two symbols we use. There are two symbols we use when marking directions like this, 3D direction. If we need to mark a line coming out of the board, we use the symbol circle and a dot. Circle and a dot means line is coming out. If you see this symbol, you should know that something is coming out of the board there. If we need to mark something going into the board, we show circle and a cross. Circle and a cross is for in. Circle and a dot is for out. Now look at this. Current is flowing that direction. Conductor is like this. Now you all tell me. From top, my fingers are coming out. Can you see that? From top, fingers are coming out. From top, it is circle and a dot. From bottom, it's going in. From bottom, it's going in. In kiyanne circle and a cross. Got it? How to mark the magnetic field direction? From top out, bottom in. Right? That's it. Right hand grip rule. That's it. Magnetic effect of current flowing conductor. That's it, the first part. Over the mind, dangle hiti. Right? Clear? Now going to the second part. Force acting in a current carrying conductor placed in magnetic field. Force acting in a current carrying conductor placed in magnetic field. Writing the heading, very long heading. Force acting in a current carrying conductor placed in magnetic field. Force acting in a current carrying conductor placed in magnetic field. What is this? Leave the heading aside. Think like this. Listen, this is actually an integrated version of our first theory. This second theory is kind of an integrated version of our first theory. Now, what is first theory telling us? When you have a current carrying conductor, in the vicinity of the conductor, what is acting? Magnetic field is acting. If you have a current carrying conductor, current carrying conductor, in the vicinity of the conductor, around the conductor, a magnetic field is acting. That means I can tell a current carrying conductor, a current carrying conductor is just like a magnet. I can tell current carrying conductor is just like a magnet. Around a magnet also, what will be acting? Magnetic field will be acting. Around a conductor, current carrying conductor also I have magnetic field. Around a magnet also I have magnetic field. Around current carrying conductor also magnetic field. Around a magnet also magnetic field. I can tell current carrying conductor is just like a magnet. Just like a magnet. Agree? Agree? Understand the logic there. Current carrying conductor, around it you have magnetic field. Magnet, around it you have magnetic field. That means current carrying conductor is just like a magnet. It's just like a magnet. Now, let's take, you have a magnet. You already have a magnet. You're going to bring another magnet closer to this magnet. You're going to bring another magnet closer. You're going to bring another magnet closer. Now you all tell me, north and south, opposite poles are coming closer. When opposite poles come closer, what will happen? They will attract, which means I can tell there will be an attraction force. Let's take same poles are coming closer. If same poles come closer, what will happen? They will repel. That means there will be a repulsion force. Then I can tell when two magnets are brought closer, there will be either an attraction force or a repulsion force. Again, I repeat, when two magnets are brought closer, there will be either an attraction force or a repulsion force. What will be there? A repulsion force. Then I can tell when two magnets are brought closer, there will be a force. Agree? When two magnets are brought closer, there will be a force. Agree? When two magnets are brought closer, there will be a force. Yes. Maybe baba things from grade 6, I think you have. Same poles repel, opposite pole attract, which means between two magnets there will be a force. Maybe baba things. Now, using this, I can integrate another point. Now the final theory. What we know, around a current carrying conductor, there is a magnetic field, which means current carrying conductor is just like a magnet. And now we know when two magnets are brought closer, there will be a force acting. See, current carrying conductor is just like a magnet, point number one. When two magnets are brought closer, there will be a force acting. Now integrate both together. Then I can tell When a current carrying conductor is brought closer to another magnet means what? Another magnetic field. When it is brought closer to a magnetic field, another magnetic field, there will be a force acting. Harini, how? Current carrying conductor is just like a magnet. When a magnet is brought closer to another magnet, a force will be acting. Then of course I can tell, when a current carrying conductor is brought closer to another magnet, force will be acting. Agree? Yes. That is our second theory. That is our second theory. When a current carrying conductor is brought closer to a magnetic field, a force will be acting. Or I can tell, when a current carrying conductor is placed in magnetic field, a force will be acting. Now read the heading. That is what the heading tells. That is what the heading tells. Look at the heading. Force acting in a current carrying conductor placed in magnetic field. Force will be acting. A force will be acting in a current carrying conductor placed in magnetic field. Okay? That's the second theory. Now listen. The magnitude of force. එකටත් කලින් චූටි point is there. එකටත් කලින් චූටි point is there. Now we know when a current carrying conductor is placed in magnetic field, a force will be acting. When current carrying conductor is placed in magnetic field, a force will be acting. But under one condition, there is a condition for this. What is the condition? For the force to act, current direction, magnetic field direction, both should be perpendicular to each other. Only when the current direction and magnetic field direction are perpendicular to each other, a force will be acting. And the produced force is also going to act perpendicular to the other two factors. The produced force will also act perpendicular to the other two factors, which means all three factors are going to be perpendicular to each other. Current is perpendicular to the magnetic field is perpendicular to the force is perpendicular to the current. All three factors are going to be perpendicular to each other. So remember that condition. Current carrying conductor, when kept in magnetic field, it will produce force, but for that both should be perpendicular. Okay. Right. We go to the dude. We didn't read anything. Take the starting part of the dude now. Electromagnetism and magnetic induction. Electromagnetic induction. Magnetic effect of electric current. Around a current carrying conductor, there is a magnetic field. Two rules are there: Maxwell's corkscrew rule, right hand grip rule. Force acting on a current carrying conductor placed in magnetic field. When a current carrying conductor is placed perpendicularly in a magnetic field, there will be a force acting perpendicularly. Next point. Listen. The magnitude of the force produced depends on three factors. Magnitude of the force depends on three factors. What are the three factors? Number one, amount of current. Magnitude of force depends on amount of current. If you send large current, force is also large. If you send low current, less current, force is also less. Number two, strength of the magnetic field. Strength of magnetic field. If you use a stronger magnet, force is high. If you use a weaker magnet, force is low. Finally, length of the conductor. Usually what they do is, They don't use straight conductors like this. They take the conductor and make a coil and use it. In applications of this, they make a coil from that. So instead of length of the conductor, you can tell number of turns in the conductor. Number of turns in the conductor. Number of turns in the conductor. If the number of turns are more, magnitude of force is more. If number of turns are less, magnitude of the force is less. Again, one more time, open the mouth and tell. What are the three factors that affect the magnitude of force generated here? Amount of current, strength of magnetic field, length of the conductor. Next, direction. The direction of the force. Direction of the force depends on two factors. What are the two factors? Direction of current, direction of current, and direction of magnetic field. Direction of magnetic field. So according to the question you answer, magnitude of force depends on three factors: amount of current, strength of magnetic field, length of the conductor, or the number of turns in the coil. Number of turns in the coil. Direction of the force depends on two factors: direction of current, direction of magnetic field. Okay. Simply remember like this. Now, what is the theory telling? When a current carrying conductor is placed in magnetic field, a force is generated. That is the theory telling. Now think reverse. The magnitude of the force will depend on what? Either current flow, amount of current flow, or the magnetic field. Additionally, the length of the conductor. So force depends on current flow, magnetic field, length. Direction. Direction of force depends on direction of current, direction of magnetic field. Is there anything else to depend on? No. Those are the two factors going to affect you. So amount depends on amount of current, amount of magnetic field, length of the conductor. Eka vitarai you have to memorize separately. Direction of force depends on direction of current, direction of magnetic. Okay. Next, if you know the direction of current and the direction of magnetic field, can you find the direction of force? If you know the direction of current, direction of magnetic field, can you find the direction of force? Yes. What's the rule we apply for this? Fleming's left hand rule. You know the direction of current, direction of magnetic field. If you want to find the direction of force, Lamai, the rule that we apply is Fleming's left hand rule. What is Fleming's left hand rule telling us? You take your left hand, not the eating hand, the other hand, left hand. You take your left hand, you take your left hand, you take your left hand, and you know the direction of current, direction of magnetic field, no? Which means we can adjust them. You adjust your index finger to the direction of magnetic field. You adjust your index finger to the direction of magnetic field. You adjust your middle finger to the direction of current, such that index and middle are perpendicular to each other. You adjust the index and the middle such that they are perpendicular to each other. Index is magnetic field, middle is current flow. Now you open your thumb. Don't go to adjust the thumb. Open your thumb. Thumb will show the direction of force. It shows the direction of force. Index to the direction of magnetic field, middle to the direction of current. Adjust them. After making the adjustment, open the thumb. Thumb will show the direction of magnetic field. Direction of force. For example, we'll do some questions. For example, let's take magnetic field is in that direction. Current flow is out of the boot. Circle and a dot means what? Out. I will write it in a side and key. Circle and a cross is in. Magnetic field is that direction. Current flow is out of the boot. We'll apply Fleming's left-hand rule and find the direction of the force on. Work with me, yeah, work with me. Oh, no, nikang inde pa. Now work with me. Take your left hand. First, adjust your index. Always adjust your index. Magnetic field you adjust first. Magnetic field is that direction. Then index finger should be that direction. Do to the screen. Magnetic field is that direction. Index that direction. Current is coming out of the boot. Current is coming out of the boot, which means your middle finger should be out of the boot. Yes, we are normal human being. When we open our middle finger, automatically it is out. Nothing to adjust. But see that those are perpendicular. Cheese photo. You keep both of them perpendicular. Right? Index to that direction, middle to that direction. Now you adjusted both. Now you open your thumb. No adjustment to the thumb. Now you open your thumb. Thumb will show the direction of force. Force is which way? Upwards. Force is upwards. That's the direction of force. On second one. Let's take magnetic field that direction. Current is going into the boot. Will apply. Will apply. Magnetic field that direction. Index that direction. Current is going into the boot. Current is going into the boot. Into the circle and across is in. Which means middle finger should be in. Yes, we are normal human being. When we open our middle finger, automatically it goes in. Automatically it is in. Now open the thumb. Where is thumb pointing? Thumb is pointing upward. Thumb is pointing upward. Make Q-text nevi. Once upon a time, 2 months ago, kept the hand on the car door and closed it. And then there is a blood clot there. Q-text nevi. So magnetic field is that direction, current flow is that direction, force is upwards. Force is upwards. Force is upwards. Third one, have a bit different. Let's take magnetic field that direction, current in, work with me now. Magnetic field that direction, current in. Magnetic field that direction, index is that direction, current is into the boot. Open your middle finger. If you are a normal human being, your middle finger will be automatically pointing out. It should be out the in. So you have to rotate it. You have to adjust it to in. Always rotate it from down. Mehima adjust it. Down you adjust. From top you can't adjust. We can't do that. Some fellows do that. I don't know how you can do. If you can do, go to youth with talent. This way you can't turn. Balamai. Bear. You can't. C-A-N-T. Can't. You rotate it downwards. Rotate it downwards. See, this way can. Stretch the hand and do. In the class, sometimes you may not be able to stretch it. Now you can stretch at home. Stretch the hand and do. Stretch it and do. From down you can rotate. From top you can't. So from down you rotate. In. Force is where? Force is where? Down. Force is down. Got it? Find the direction force. Got it? Yes. Yes. Perfect. What are the applications of electromagnetism? This section. What are the applications? What are the applications? What are the applications? Two applications are there. This is used in DC current motor. This method is used in DC current motor and it is used in loudspeaker. DC current motor and loudspeaker works based on this principle. Motor and loudspeaker works based on this principle. Hurry. Force acting on a current carrying conductor placed in magnetic field. When a current carrying conductor, these things we read. Yeah. When a current carrying conductor is placed perpendicularly in magnetic field, there will be a force acting perpendicular. Direction of force depends on two factors: direction of magnetic field, direction of current. Magnitude of force depends on amount of current, strength of magnetic field, length of the conductor. That is number of turns in the coil. To find the direction of force, we use Fleming's left-hand rule. Now in this diagram, this is the diagram given in a textbook. Letter B. Letter B means magnetic field. Letter B means magnetic field. Application, loudspeaker, DC current motor. Those are the applications. Next, electromagnetic induction. Electromagnetic induction. Induction is the opposite theory of electromagnetism. Now, what we learned until now is electromagnetism. AK opposite. Electromagnetism's opposite theory is electromagnetic induction. What is electromagnetic induction telling us? What is electromagnetic induction telling us? On the C. Now, what is electromagnetism telling our previous one? What is electromagnetism telling? When you have a current carrying conductor placed in magnetic field, what will be acting? A force will be acting. That is electromagnetism telling previous one. Current carrying conductor placed in magnetic field, force will be acting. Previous one. Now it's the opposite. Now it's the opposite theory. What is the opposite? On the C. If you give a force is given before force is produced. If you give a force to a conductor placed in magnetic field is also there. Now tell me, what will be produced? Force is there, magnetic field is there. What will be produced now? What will be produced? Current will be produced. Before current is there, magnetic field is there, force is produced. Now force is there, magnetic field is there, automatically current will be produced. That is electromagnetic induction. But one condition, force and the magnetic field should be perpendicular. Only when force and the magnetic field are perpendicular, a current will be produced. Produced current is also going to be perpendicular to the other two factors. Same logic. Current and the magnetic field should be perpendicular. Sorry, force and the magnetic field should be perpendicular. Force and the magnetic field should be perpendicular. Then a current is produced. Produced current is also going to be perpendicular. Ehang put everything into one single sentence and tell me what is electromagnetic induction? When a conductor placed in magnetic field is given force, current is produced. One more time, what is electromagnetic induction? When a conductor placed in magnetic field is given force, a current is produced. Simply put it in the mind. When conductor placed in magnetic field is given force, a current is produced. But one condition, force, magnetic field should be perpendicular. Then only a current is generated. Okay. Again, one more time. What is electromagnetic induction telling? When a conductor placed in magnetic field is given force, a current is produced. But some words here will be changing. Some words here will be changing. What are the words will be changing? One, force word will be changing. Now, Lamai, when you give force to an object, what will happen to that object? It will be at rest there, it will start moving there. It will be at rest there, it will be moving there. It will be moving. It will be at motion. When you give force to an object, that object begins to move. Now here, when you give force to a conductor, that conductor also will be at motion. Then I can tell, instead of telling force is given, I can tell conductor set in motion. Instead of telling force is given, we can tell conductor set in motion. Why? When you need to set the conductor in motion, what you need to give? If you want to set a conductor in motion, if you want something to move, what you need to apply there? Force. Now, for example, this pen. If I want it to move, what I should apply? Force. So here the same. If I want to set the conductor at motion, I need to apply force. So instead of telling force is applied, I can tell conductor set in motion. So putting that into our definition, what is electromagnetic induction? When a conductor placed in magnetic field is set in motion perpendicularly, a current is produced. When a conductor placed in magnetic field is set in motion perpendicularly, a current is produced. Okay? Another word we have to change. Now, even though we tell current is produced, it's not actually the current that is produced. What is produced there is an electromagnetic force. Sorry, electromotive force. Even though you tell a current is produced, it's not the current that is produced. What is produced is an electromotive force. A EMF is only produced. What is EMF? EMF is something like voltage. EMF will make electrons to flow. It's like voltage, it will make electrons to flow. Now you all tell me, if electron flows in opposite direction, what will be flowing? If electron flows in a certain direction, opposite direction will be current will be flowing. So we don't tell current is produced. Instead of telling current is produced, what we tell? A EMF is produced. Electromotive force is produced. So now putting everything into words. What is electromagnetic induction? When a conductor placed in magnetic field is set in motion perpendicularly, a electromotive force is generated. Again, one more time. What is electromagnetic induction? When a conductor placed in magnetic field is set in motion perpendicularly, an electromotive force is generated. Go open the mouth and tell, what is electromagnetic induction? When a conductor placed in magnetic field is set in motion perpendicularly, an electromotive force is generated. But for this to happen, two conditions are there. One, force and the magnetic field should be perpendicular. The other point, now we are setting the conductor in motion. You can't set it in just a normal motion. The motion should be a relative motion. What kind of motion should be there between the conductor and the magnet? A relative motion. Now, relative motion is actually a very big concept. In theory classes, I have told it using a story. Separate stories used there. I can't tell that full story. Simply relative motion is something like this. Let's take, you have two objects. During a certain motion, if the distance between the objects change, if the distance between the objects change, we tell there is a relative motion. If distance changes, there is a relative motion. If the distance doesn't change, there is no relative motion. Distance changes, relative motion is there. Distance is not changing, relative motion is not there. Now, what is induction theory telling us? For a current to be produced in a conductor that is moving in a magnetic field, that motion should be a relative motion, it seems. Only when there is a relative motion between the conductor and the magnetic field, a current will be produced. If there is no relative motion, no current is produced. Now, for example, see, let's take, this is the magnet, this is the conductor. Conductor is placed in magnetic field. Conductor is placed in magnetic field. If I move the conductor or if I move the magnetic field, there is a motion. There is a motion. Motion can, there is a force. Guaranteed there is a magnetic field. What is produced? Current is produced. So magnet is there, conductor is there. If there is a motion, current will be produced. But what kind of a motion should be there? Relative motion. What is relative motion? Distance between them should change. If the distance doesn't change, no relative motion, no current. Now look at this. Conductor is there, magnetic field is there. Look at this motion. Magnetic field. This is a magnet. Magnet has a magnetic field. Look at this motion. Can you see between them distance is changing? Can you see between them the distance is changing? Can you see between them the distance changed? Conductor is there, magnetic field is there. Look at this. Can you see distance is changing between them? Distance is changing now. Is there a relative motion? Distance is changing now. Is there a relative motion? Yes. If there is a relative motion, a current will be produced. Now look at this. Again, see. Can you see between them, distance is changing? If the distance is changing, there is a relative motion. If there is a relative motion, there is a current produced. Now look at this. Conductor, magnetic field. Magnetic field can a magnet. It is there, this is there. That is there, this is there. Is the distance changing? No. If distance is not changing, is there a relative motion? No. No relative motion. Now, is there any current produced here? Is there any EMF produced here? Now look at this. Is the distance changing? Yes. Then is there a relative motion? Yes. Then is there a current produced? Yes. This. You can see? You can see? Is the distance between them changing? Between these two, is the distance changing? No change in the distance. Now, is there relative motion? No relative motion. No relative motion. Now, is a current produced there? No current is produced. So, keep in mind, for a current to be produced, there should be a relative motion between the conductor and the magnet, which means relative to one, the other should be moving. Between them, the distance should be changing. Only if the distance changes, there is a relative motion, there is a current produced. If the distance doesn't change, there is no relative motion. No relative motion now, no current is produced. Got it? Yes? Yes. Alright. Alright. Now, magnitude of current. Magnitude of current. Magnitude of current produced. That's the EMF generated. EMF generated. Its magnitude depends on three factors. What are the three factors? You all can guess and tell now. That is why I'm telling you all, don't memorize physics. Understand physics. Now, what is electromagnetic induction telling? When you give a force to a conductor placed in magnetic field, current is produced. Force kya what? Set in motion. Now think. Magnitude of current should depend on what? Should depend on the force, should depend on the magnetic field. But are we telling the force directly? No. Instead of force, what we are telling? Set in motion. Tell me in terms of motion. If motion is fast, current is high. If motion is slow, current is low. Then I can tell the produced current, the produced EMF depends on the speed of the motion. Speed is high, fast, then current is high. Speed is low, slow, current is low. So one factor that affects the amount of current produced is the speed of motion. Speed of motion. That is what you mean by the force there. Second factor, directly you can tell. Second factor, don't memorize, understand and tell me. Second factor, magnetic field. Second factor is magnetic field. If magnetic field is high, current is high. If magnetic field is low, current is low. Additionally, one more factor is there. Length of the conductor. Usually we don't use conductor, what we use? Coil. If it is coil, what we tell then? Number of turns in the coil. Number of turns in coil. So three factors affect the amount of EMF generated, speed of motion of the conductor, the strength of the magnetic field there, and number of turns in the coil. Okay. Now go to electromagnetic induction. If a conductor placed in magnetic field is set in motion perpendicularly, then an electromotive force EMF is generated. Factors affecting the induced EMF, what are the three factors? Magnitude of force, that is the speed of motion, strength of magnetic field, and number of turns in the coil. Next, now we know when a force is given to a conductor placed in magnetic field, a current is produced, that we know. The next question is, if you know the direction of force and the direction of magnetic field, can we find the direction of current? If you know the direction of force and the direction of magnetic field, can you find the direction of current? Yes. What's the rule we use for that? What's the rule we use for that? That is Fleming's right hand rule. Fleming's right hand rule. Fleming's left hand rule is used for the previous one. Now it is Fleming's right hand. Hari nilamai. Previous one's opposite is this. If this is the opposite rule should be used. No? Previous one we use Fleming's left hand rule. Now we use Fleming's right hand rule. What is Fleming's right hand rule telling us? You take your right hand. You take your right hand. Haridu. You take your right hand. You know the direction of force, you know the direction of magnetic field. You point your thumb to the direction of force and your index finger to the direction of magnetic field such that both are perpendicular to each other. And then you just open your middle finger. No any adjustment. You open your middle finger will show the direction of current. So is that a ring? Ring nevi. That's the nails in the finger. Right? You'll have to see it as nails in the finger. Right? Uh, so you open the thumb to the direction of force, adjust the thumb to the direction of force, adjust the index finger to the direction of magnetic field, then open your middle finger will show the direction of current. So here you adjust the force, you adjust the magnetic field, just open the middle finger will show the direction of current. We'll do some questions. Let's take, you have the magnetic field in that direction, force in that direction. Yeah, force in that direction. Force in that direction. We'll try to find the direction of current now. We'll try to find the direction of current. On all of you take your right hand. First, always adjust your index. First, always adjust your magnetic field. Take your index finger. Index finger shows the direction of magnetic field. Magnetic field, that direction. Adjust the index to that direction. Thumb points the direction of force. Force is upwards. Force is upward. Open the thumb upward. Adjust it upward. Now open your middle finger. Maybe you can't see. Open your middle finger. No any adjustments with middle finger. Just open your middle finger. Where is middle finger showing? Into the board, the out of the board. Into the board, the out of the board. Into the board. Into the board. This is in, out. Maybe this is in. Into the board. Into the board can a circle and a cross. That's the direction of current. Circle and cross. That's the direction of current. Okay. Another one. Now your turn. Second one. Magnetic field that direction. Force is that direction. Find the direction of current. In the out. In the out. Out. How to do? Take your right hand, eating hand, point your magnetic field that direction, then index is that direction. Force is upward, your thumb is upward. Now open the middle finger. Middle finger is pointing out, middle finger is pointing out, then your current is out. Current is out. Circle and a dot. Another one. Think and do this. Think and do. Always adjust your index first, magnetic field first. Magnetic field is up, index is up. Point the index up. Force is that direction. Force is that direction. Then force is that direction. Now open your middle. You may not able to see. Middle is in. My middle is in. In. Circle and across. Sorry. Current is in. Middle is in. Current is in. Another one. Current. Magnetic field that direction. Index is that direction. Force is acting down. Now see, when I open the thumb, I'm a normal human being. My thumb is up. But force is down. I have to rotate it. I have to turn it down. Which direction I turn it? From inside. Outside bala, my make a bear. You can't bring it down. Straight hand, you can't do that. Straight hand, you bring it down like this. See, straight hand, you can't turn it like that. No bad. Straight hand, from inside you rotate. From inside you rotate. So again, see, magnetic that direction. Force is down. Force is down. Now you open your thumb. Now you open your middle finger. Middle finger is pointing out. Middle finger is pointing out. Pointing out. Middle finger out. Understood now how to find the direction of the current? Yes. Yes. Perfect. Good. Honda lamai. Hurry. What are the applications of this? What are the applications of electromagnetic induction? What are the applications of electromagnetic induction? 3 applications are there. 1, AC current dynamo. Now in theory classes, we went very deeply inside. We learned how a dynamo works, how the internal parts work. Now in one night session, we can't go that deep and explain. Today full night, I have to teach on this one. I am targeting on what will mainly come for the exam and teach. Now, once when I teach the previous one and the application, using the previous knowledge, you can find out how AC current dynamo works. Without our fundamentals, I'm building and going on here, this lesson. So AC current dynamo, moving coil microphone, MCQ questions say make a important. What are the application where moving coil microphone and bicycle dynamo. Bicycle dynamo. Those are the 3 applications. Now tell me previous one. Electromagnetism, what are the applications? DC current motor and loudspeaker. Here, electromagnetic induction, what are the applications? AC current dynamo, moving coil microphone, bicycle dynamo. Remember where what you said. Electromagnetism, one more time tell me. Electromagnetism, previous one. DC current motor, loudspeaker. Here, electromagnetic induction, 3 application. AC current dynamo, moving coil microphone, bicycle dynamo. Alright. And remembering the rules in this lesson is a bit hard. Remembering what rule for what. Remember it like this. In this lesson, we learned three theories. No? We learned three theories. First one is first one is magnetic effect of current carrying conductor. Magnetic effect of current carrying conductor. What you do here? You know the direction of current, you find the direction of magnetic field. What's the rule you use? Or I told you don't take Maxwell's corkscrew rule, use right hand grip rule. Right hand grip rule. Second, electromagnetism. Electromagnetism. This is where we learn about force acting in a current carrying conductor placed in magnetic field. What we learn here? You know the direction of current, you know the direction of magnetic field, you find the direction of force. What's the rule we use? See, I started with right, no? Now I should go to left. Second one is left. Fleming's left hand rule. Last one, just now we did. Electromagnetic induction. Electromagnetic, there you go. Induction. What we learn in electromagnetic induction? You have a force, you have a magnetic field, you find direction of current. Previous one was left, no? Now you go with right. Fleming's right hand rule. Fleming's right hand rule. So look at the order. First one, magnetic effect of current, right hand grip rule. Second, electromagnetism, Fleming's left hand rule. Next, electromagnetic induction, Fleming's right hand rule. So can you see a pattern there? Right hand grip rule, left hand, right hand. Right, left, right. That's the order. Right, left, right, left, right. Here, magnetic effect. Next, electromagnetism, current you know, magnetic field you know, force you find. Next, electromagnetic induction. Force you know, magnetic field you know, current you find. Got it? So nothing to memorize there, right? Yes. This is not included in your tune, so if you want, take a screenshot or something and keep, may be useful. Right. To find the direction, Fleming's right hand rule is used. Fleming's right hand rule, thumb points the direction of force, index points the direction of magnetic field, then middle finger will give the direction of current. Application AC current dynamo, moving coil microphone, bicycle dynamo. Last part of the lesson. Last part of the lesson. Make a part important. This last part of the lesson is very important. Now, if you are continuously joining on our MCQ night session, now those are very new now, listen. Every day night we are doing MCQ night session. Last 2 days again I couldn't do. Every day night we are doing MCQ night session where we discuss 10 MCQ past paper questions. Now, if you have seen all the past paper questions that we have discussed until now, everywhere there was a question about what? Transform. Such an important section we are going to start now. Listen very carefully. Make a part important. Eh? Transform. Listen, ne? Right. What is a transformer? Transformer is a device that can change the voltage. Transformer is a device that can change the voltage. Change the voltage means either it can increase the voltage or it can decrease the voltage. So transformers can either increase voltage or it can either decrease voltage, which means we can tell there are two types of transformer. There are two types of transformer. What are the two types of transformers we have? One, step up transformer. Two, step down transformer. What are the two types of transformers we have? Step up transformer, step down transformer. Step up transformer. Step up transformer will increase the voltage. It is used to increase voltage. You give a voltage, step up will increase that voltage. Step down transformer. Step down transformers will decrease the voltage. Now opposite. It will decrease the voltage. Harane down kyanne decreasing, up kyanne increasing, step up will increase, down kyanne decreasing, step down will decrease. Now, I will teach deeply about step up. Same thing in opposite way will come for step down. Onna listen, ne? Onna listen. Any transformer you take has two coils. Any transformer you take, it has two coils in it. One is the primary coil, the other is the secondary coil. Two coils are there, primary coil, secondary coil. To the primary coil only you give the input. From the secondary coil only you get the output. If we take step up transformer, see there are two coils. Primary coil, secondary coil. Primary coil, secondary coil. To the primary coil you give your input. That is your primary coil. To that you give your input. To that you give your input. From the secondary coil, from the secondary coil, you get your output. That is your secondary coil. In between the two coils, there is a soft iron core. A soft iron core is there. We represent it symbolically using two lines. These two lines means soft iron between the two coils. Again, I repeat, these two lines means soft iron between the two coils. If I show real pictures of transformer, you can see that soft iron. Have you all seen when you remove any electrical devices, this kind of small parts, mega chuti parts are there. Those are transformers. In that surrounding, you have the soft iron. Or around the coil, you have the soft iron. Around the soft iron only, they will wrap the coil. Around the soft iron only, they will wrap the coil. Around the soft iron only, they will wrap the coil. See, coil is wrapped around the soft iron. So there should be soft iron. It acts as the medium there. It acts as the medium there. So you have the soft iron. That is what is represented using two lines. Now look at the step-up transform. What is step-up transformer doing? Increasing the voltage. Now look at the primary coil and the secondary coil. Can you see number of turns in the primary coil? Number of turns in the primary coil. We symbolically represent it as NP. Number of turns in primary coil. NP. Number of turns in primary coil is represented as NP. Operating system is loading. Number of turns in the primary coil is called NP. This is the secondary coil. Secondary coil also has certain number of turns. Number of turns in the secondary coil is called NS. Number of turns in primary coil NP, number of turns in secondary coil NS. Out of these two, which one is high here in step-up transformer? NP, NS, which one is high? Who has lot of turns? Secondary has lot of turns. Secondary has lot of turns. Which means, can you see number of turns are increasing from primary to the secondary? Number of turns are increasing from primary to the secondary. That is step-up transformer. Therefore, voltage will also increase. The voltage that you give to the primary coil is called Vp. Voltage you get from the secondary coil is called Vs. Vp is the input voltage, Vs is the output voltage. On output voltage is greater than the input voltage. Harini, you input small voltage, but you get a large voltage. You give small voltage, you get a large voltage. That is step-up transformer, increases the voltage. Vp less, Vs high. Np less, Ns high. Step-up transformer. Now with those logic, come to step-down transformer. Step-down transformer. It is also a transformer, which means it will also have two coils. One coil is primary coil. The other coil is secondary coil. In between, you have soft iron. That is your primary coil. There you go. That is your primary coil. That is where you give your input. This is your secondary coil. Secondary coil. That is where you will get your output. Now look at the number of turns in primary coil and number of turns in secondary coil. Number of turns in primary, number of turns in secondary. Now, whose number of turns are high? Now, primary number of turns are high, secondary number of turns are low. Which means, can you see number of turns are decreasing? As the number of turns are decreasing, voltage is also decreasing. If I compare voltage in primary, voltage in secondary, which one is greater here? Primary is greater, secondary is less. Primary you give high voltage, secondary you get low voltage. Okay? Got it? Yes? Those are the two transformers. Next, what we have is equations in transformer. Equations in transformer. Theory people, we have recently done this and finished. Equations in transformer. There are two equations under transformer section. What are the two equations? Number of turns in primary coil divided by number of turns in secondary coil is equal to voltage in primary coil divided by voltage in secondary coil. NP over N is equal Vp over Vs. Number of turns in primary divided by number of turns in secondary equal voltage in primary divided by voltage in secondary. NP over N is equal Vp over Vs. Okay, that's the first equation. Another equation is there. Second equation. I'll tell you how the second equation came as it. Now, in a transformer lamai, the power you give as the input and the power you get as the output, both are equal. Input power, output power in a transformer is equal. Why? Transformer can't produce any power. It doesn't have the technology or a method to produce power. And transformer can't destroy any power. It can't produce power, it can't destroy power. Lamayo, production of power is done where? In power station. Only in power station you can produce power. Hydropower station, wind power station, coal power station, all those power station only produces power. So here no production in power is happening, which means input power, output power, both are equal. In any transformer, it's the same logic. Step up transformer, step down transformer, in both the places, input power and output power are equal. Input power and output power are equal. I'll write it like this. Power input, P input. Power output, P output. Both are equal. Now, y'all using your power and energy of electric appliances knowledge, tell me, what's the equation we have for power of an electric appliance? How do we calculate the power of an electric appliance? Power is equal to voltage multiplied by current. Power of an electrical appliance, power is equal to voltage into current. Now, instead of writing power input, I can tell voltage input, natham VI kilodam, voltage input multiplied by current input. Agree? Instead of writing power input, I can write voltage input multiplied by current input. Instead of writing power output, I can write voltage output multiplied by current output. Agree? Now, power input, power output are equal now. Voltage into current input, voltage into current output, both are also going to be equal. Now, one more step I can go. Input is given to what coil? Primary coil. Input is given to the primary coil. Then I can tell voltage into current input is voltage in the primary coil multiplied by current in the primary coil. I.e. input is given to the primary coil. So instead of telling input, I can write primary coil. Voltage in primary coil multiplied by current in primary coil. Output is obtained from where? Output is obtained from secondary coil. So instead of writing voltage into current output, I can tell voltage in secondary coil multiplied by current in secondary coil. Now tell me VPIP, VSIS, what can you tell? Both are equal. Why they are equal? Because input power, output power are equal. Therefore, VPIP, VSIS will be automatically become equal. That is your second equation. That's the second equation. All these things in theory we have done. Right? NP of N is equal to VP over Vs. Second, VPIP equal VSIS. Voltage into current input, that is primary coils. Voltage into current output, that is secondary coils. Both their values are equal. Got it? Yes? Yes. One more point is there I want to give. Ekata calling. Here we have something to write. Transformer කියලා there is a big box kept. I want you all to write those things in that transformer section. මේ ටික ඔක්කොම වගේ balance the space and write. What I'll do is first I'll keep this part of the board. Then I'll show you all the equation. Hurry. Dingala write it there. Done. Shall I shift down? Okay. Harne. Right. Next part. Listen, next part. Now, in a transformer, your power input and the power output are equal. That is because power is a constant. Power is not created, power is not destroyed. Your power input, power output are equal. Power input, power output are equal. Onna listen, which means power remains a constant. Power is constant. Now we know in an electrical appliance, the equation for power is power equal voltage into current. Now see, in step-up transformer, voltage is increased. In a step-up transformer, voltage is increased. Now mathematically think, voltage is increased. But the final answer, power should remain constant. Power can't change, power can't increase, power can't decrease. Voltage is increased, power should not change now, but should happen to the current. Mathematically think, increase the decrease. Voltage into current gives us power. Voltage is increasing, but final answer, power should not change now. What should happen to the current? Current should decrease. Current should decrease. Current should decrease. So remember, in a step-up transformer, even though the voltage is increased, current will decrease. Voltage increase, current decreases. So it's the actual logic in a transformer is this. It doesn't produce any voltage. It doesn't destroy any voltage. It just adjusts the current and the voltage there. Maybe it will increase the voltage but decrease the current, or increase the current and decrease the voltage. That is what a transformer does. No any production of voltage, no any destruction of voltage. Okay, so final power remains a constant. So in a step-up transformer, yes, voltage is increased, but automatically current flow is decreased. Thereby power is remaining constant. Okay. Ehena, using that logic, tell me for step-down transform. Step-down transform. Step-down transform. Power is a constant. Power is equal to voltage into current. In step-down transformer, voltage is decreased. Voltage is decreased. Voltage decreased. Now what happens to the current? To give the final answer constant. What happens to the current? Current will increase. So remember, in step-down transformer, current increase. Maybe I'll write it somewhere here. current increase. In step-up transformer, current decrease. Current decrease. Okay, got it? Yes. With that, one more point. මේ වන theory class වල හොඳටම කරලා තියෙන්නේ. One more point. Now look at step-up transformer. What is step-up transformer doing? It is decreasing the current. Current flow is decreased. Current flow decrease කියන්නේ your input current is high. Lot of input current is given. Output current is low. Just a little amount of output current comes. Now for example, let's take your input current is 50 ampere. Your output current is just about 20 ampere. That is what we call decreasing current. So step-up transformer will decrease the current. If your input current is this much, output current is less than that. Sorry. With that, one more point. Resistance of a conductor. Resistance of a conductor. Resistance of a conductor depends on three factors. What are the three factors? One, length of the conductor. Two, cross-sectional area of the conductor. What do you mean by cross-sectional area? This area, that is cross-sectional area. And material of the conductor. Material of the conductor. How do they affect? When the length of the conductor increases, resistance will increase. Current flow will decrease. When the cross-sectional area increase, resistance decrease, current flow increase. Opposite connection. Area increase, resistance decrease, current flow increase. When the material changes, resistance will change. This is grade 10 work. Length increase, resistance increase, current flow decrease. Cross-sectional area increase, resistance decrease, current flow increase. Cross-sectional area increase, resistance decrease, current flow increase. What I am interested is this part. Cross-sectional area increase, resistance decrease, current flow increase. On that part is what I am interested. That is very important part. Using the logic, come to this. See, in a step-up transformer, current is decreased. Your input current is high, output current is low. Now, out of primary and secondary coil, which coil is handling a large current here? Big current is handled by which coil? Primary coil. i.e., current is decreased. Primary coil input current is high, secondary coil output current is low. So, in a step-up transformer, primary coil is handling a large current. One question. As it is handling a large current, through that coil, a big current tries to flow. When large current tries to flow, that coil can get heated. Why? Due to its resistance. Possible then? If a large current tries to flow through that coil can get heated. Possible. Due to resistance. If it gets heated, there will be heat energy released. Heat will get released out. You all tell me, heat getting released, is it something good or bad? It is bad. It's a loss. We are supplying electrical energy. We don't want it to be converted into some useless energy and released out. We want all those electricity outside, not as heat. We don't expect heat from a transformer. We are not going to fry eggs on a transformer. We don't need heat. So we don't want that heat loss there. Ehenang tell me, we should try to increase the heat loss, decrease the heat loss there. We should try to decrease the heat loss. How to decrease the heat loss? How to decrease the heat loss? To decrease the heat loss, you should decrease the resistance. How to decrease the resistance? What you do to the area, cross-sectional area. Cross-sectional area you have to increase. So remember, in step-up transformer, primary coil's cross-sectional area is increased. Thereby you reduce the resistance. Thereby you increase current flow. And thereby you decrease the heat loss. So keep in mind, in step-up transformer, primary coil's cross-sectional area is increased. Think logically. When the cross-sectional area increases, resistance will decrease. When resistance decreases, heat loss will decrease. Then current flow will automatically increase. So in a step-up transformer, primary coil's thickness is increased. That is what you mean by area, cross-sectional area is increased. Its thickness is increased. Thereby, the resistance is decreased. Thereby, heat loss is decreased. Thereby, it can handle large current. Keep that point in mind. Keep that point in mind. They'll ask in the exam, in step-up transformer, which coil is made thick? Which coil is made thick? I'll just write that, thank you. Which coil is made thick? Primary coil is made thick. It is made thick. Now come to step down. Use the same logic. What will step down transformer do? Increase the current. Increase the current කියන්නේ your current it is increasing. And let's say you give 20 ampere as input current, it will increase. Maybe 50 ampere will come as the output current. Now tell me, Hena, out of primary and secondary coil, in which coil large current is flowing? Out of primary, secondary, which coil now large current is flowing? Now large current is in secondary coil. So secondary coil, current flow is high. As the current flow is high there, due to the resistance of the coil can get heated. If it gets heated, there will be a heat loss. Is it good or bad? Bad. You have to try to increase the heat loss or decrease the heat loss. Decrease the heat loss. How to decrease the heat loss? You decrease the resistance. How to decrease the resistance? You increase the cross-sectional area, which means you make the secondary coil there. You make the secondary coil there thick. You make the secondary coil there thick. Thereby you increase the cross-sectional area, decrease the resistance. Got it? Got it? Right? Now they'll ask in the exam why it is made thick. Why it is made thick? To reduce the heat loss. Right? Simply remember like this. In step-up transformer, primary coil is made thick. In step-down transformer, secondary coil is made thick. Simply, Chuti fellow is thick. Keep in mind like that. Chuti fellow is thick. In step-up transformer, Chuti fellow is primary coil. Hari Chuti boy, thick. In step-down transformer, Chuti fellow is secondary coil. Chuti boy. Keep in mind like that. I told you, summer you have to keep the things in mind. That's it. In step-up transformer, Chuti fellow is thick. In step-up transformer, primary coil is thick. In step-down transformer, secondary coil is thick. Shorter one, thick. Chuti fellow thick. Hari. Can you all mention that also? This is thick, current decrease, current increase. Didn't you all mention that? Okay. Right. We'll do some questions. Equation part choti questions will do. Two equations are there. NP of NS equal VP over VS, VPIP equal VSIS. We'll do about two questions. We'll take inner transform. Number of turns in primary coil is equal to 50. Number of turns in secondary coil is equal to 500. And voltage in primary coil is equal to 20 volt. Roman 1. What is the type of transformer? What is the type of transformer? Roman 2. Calculate the voltage in secondary coil. Dingala work. Send me the answers. Okay. Right. In a transformer, number of turns in primary coil is 50, number of turns in secondary coil is 500, and voltage in primary coil is 20 volt. What is the type of transformer? That is how they ask questions. What is the type of transformer? Check. Number of turns in primary 50, secondary 500 kya number of turns are increasing. Number of turns are increasing and guaranteed what type of transformer? Step up. Guaranteed step up transformer. Calculate the voltage in the secondary coil. Now what's the equation you apply? Number of turns in primary you know, number of turns in secondary you know. Voltage in primary you know, voltage in secondary they are asking. Apply the equation. Number of turns in primary over number of turns in secondary is equal to voltage in primary over voltage in secondary. Number of turns in primary 50, number of turns in secondary 500. Voltage in primary 20 volt, voltage in secondary they are asking. Some fellows can't subject no. එහෙම කීකේ ඉන්න බෑ ළමයි. Now a part එක you if you don't know how to subject, now you practice that. Now you make it out. Don't keep on telling I don't know how to subject, therefore if I get a question like that I'll skip. එහෙම කියන්න එපා ළමයි. Now take the responsibility. 1 month for the exam. You can't fix your mind that if you don't know this, in case if it comes to the exam, I will skip. Nah, that kind of a mindset you can't have. Don't come into that kind of a mindset. Don't fall into that kind of a category. If you don't know something, you will study that somehow and go and do that question. Come to that mindset. Skipping mindset is not the correct mindset. So now subject it. Voltage, if I subject, it comes on top. Vs comes on top. 20 volt will remain the same. Denominator 500 goes to the top, multiplied by 500. Numerator 50 goes down, divided by 50. So if I do the math there, Vs is equal to, once when I write all these things, someone make a හොඳට බලන් ඉඳලා watching the whole video ඕක බලන් ඉඳලා අන්තිමට මේ part එක විතරක් screenshot එකක් කරන් ඒකට that fellow will make a separate meme for me. Look at the time that people have to tell something about someone else. ඒ වෙලාව මට දුන්නා නම් I will use something some good thing. I slept only for last 24 hours වල මම නිදාගෙන තියෙන්නේ පැය 3යි. Only 3 hours I have slept. So if anyone is having extra time to create a meme for someone and put it ඒ time එක මට දුන්නා නම් මම නිදා ගන්නවා ඒ වෙලාවේ. මේක අරන් ෆොටෝ එකක් ගන්න දානවා. Why you doing like this? Directly yes we can find out. Yes you can find out. But when teaching we have to teach properly these things. Teaching is not the place for us to show our colors. We teachers can dingala by looking we can tell this is the answer කියලා. But teaching is not the place for the teachers to show the colors. It's the place where we make the children think. So thinking process එකේ මේක කියන්න ඕනේ. Right? අපිට දන්න techniques ටික we tell you, but that technique you should be able to use. No? Teaching is not an easy job. It's not the place for the teachers to show colors. 1 0 1 0 cancel off. 500 cancel off, only 100 is there. 100 into 2 how much? 200. 200 voltage. Got it? Got it? 12 past. Past. Still Zoom is full 1000. YouTube 600 plus. Still. This is my first physics night that has completed to keep 1000 students until this moment. I hope you all are getting something from this, right? I hope you all are getting something from this. Keep it up. Keep up the spirit. But I know it's a bit sleepy now. You feel a bit down now, right? Lesson is completed. Full lesson is completed. Transformer in a lesson is completed. But still, we are all human. We might fall, down a bit. So to raise you all up, we are shifting a little bit of physics into something else. Some of my students, they'll be doing some performances to you all. Appreciate them. Right? Appreciate them. Maybe they will come across connection issues, some issues maybe on the way because this online thing. But see that all of you all appreciate them, and maybe you all can give some cheers from your side, right? Ehena, with this I will go off the screen, and screen is for Krisha and Saliha. Y'all can take over.
Thank you, sir. Hello, boys and girls. Before we dive into the talent, let me introduce the people keeping the system equilibrium. My name is Keshavanathan Krishayani, passed out student of Sir King's Perory, and Saliha Aslam, an interactive class student of Sir King's Perory. And tonight, we are the central forces. And I want to give a special and huge thanks for our Sir King's Perory for being the force behind this event. Actually, they say an object at rest stays rest, but not tonight. Tonight, you are the exception to Newton's first law. We are going to be in constant motion until 4 a.m. Alright, everyone, our brains are currently in state of static friction, meaning we are stuck. To move into dynamic friction and keep our atoms vibrating, we pause the lecture for a moment and dive into the entertainment mood. where a students show up their talents. Over to you, Shaliha.
Thank you, Krisha, and I'm honored to be one of your co-announcers. To keep our energy levels high and to avoid that midnight sleepiness, our sir has planned this special segment. So now everyone's eyes away from equations and formulas for a moment and look at your screen. Now let's begin our talent show with a beautiful musical performance. We welcome Angelica and her brother will be singing the melodious Tamil song Vasigara and Munbeva.
Hi everyone, this is Angelisha. I'm here with my brother to give y'all a small performance. Hope y'all enjoy it. அடைமழை வரும் அது நனைவோமே குளிர் காய்ச்சலோடு சிநேகம் ஒரு போர்வைக்குள் இரு தூக்கம் குழு குழு பொய்கள் சொல்லி என்னை வெல்வாய் அது தெரிந்தும் கூட அன்பே மனமதையேதான் எதிர்பார்க்கும் எங்கேயும் போகாமல் தினம் வீட்டில் வேண்டும் சில சமயம் விளையாட்டாய் உன்னாடைக்குள்ளே நான் வேண்டும் வசீகரா என் நெஞ்சினிக்க உன் பொன்மடியில் தூங்கினால் போதும் அதே கணம் என் கண்ணுறங்கா முன் ஜென்மங்களின் ஏக்கங்கள் தீரும் நான் நேசிப்பதும் சுவாசிப்பதும் உந்தயவால் தானே ஏங்குகிறேன் ஏங்குகிறேன் உன் நினைவால் தானேனோ பூவைத்தாய் மனம் பூவை கோர் பூவைத்தாய் மணப்பூ வைத்து பூவைக்குள் நீ வைத்தாய் உயிரே தேன்மலை தேக்குக்கு நீதான் உந்தன் தோள்களில் இடம் தரலாமா நான் சாயும் தோள் மேல் வேறாரும் சாய்ந்தாலே தகுமா செம்பொலை சேரும் கலந்தது போலே கலந்தவள்தான் முன்பே வா என் அன்பே வா ஊனே வா உயிரே வா முன்பே வா என் அன்பே வா பூ பூவாய் பூ பூவா நானா கேட்டேன் என்னை நானே நான் நீயா நெஞ்சம் சொன்னதே. Thank you.
You have a fantastic voice, Angelica. Thanks for singing for us. Now we'll come out of Vasigara vibe. Next up, we have Meroni. She'll be singing Kadepoma. Since we have been talking about electric field, conduction, radiations for hours and hours, Meroni is here to ask a better question, Kadepoma. Shall we talk? Meroni, now the platform is yours.
Thank you. Hi guys, I'm Meroni. Thank you so much, Sir Perory, for giving me this opportunity. Today I'm gonna sing one of my favorite songs called Kade Puma. Hope you all enjoyed. Dirana, diranam, dirana. திரணா திரணம் திரணா தனனம் 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 தன தரிணின தானானா தனனம் 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 தன தரிணின தானனா. நேற்று நான் உன்னை பார்த்த பார்வை வேறு, நீங்காத எண்ணமாக ஆனாய் என்று. உன்னோடு நானும் போன தூரம் யாவும் நெஞ்சிலே ரீங்கார நினைவுகளாக அலையை இங்கே மிஞ்சிதே. நூலருந்த பட்டம் போல உன்னை சுற்றி நானும் ஆட, கைகள் நீட்டி நீயும் பிடிக்க காத்திருக்கிறேன். இதற்கெல்லாம் அர்த்தங்கள் என்ன கேட்க வேண்டும் உன்னை. காலம் கை கூடினார் கதை போமா கதை போமா கதை போமா ஒன்றாக நீயும் நானும் கதை போமா கதை போமா கதை போமா. நீ பேச பேச காயமாறுமே. அதிகாலை வந்தால் அழகாய் என் வானில் நீ அணையாத சூரியன் ஆகிறாய். நெடுநேரம் காய்ந்து கதகதப்பு தந்தவுடன் நிலவாயுரு மாறி நிற்கிறாய். உன்னை என்று பார்த்ததும் என்னை நானே கேட்கிறேன். வைரம் ஒன்றை கையில் வைத்து எங்கு தேடி அலைந்தாயோ. உண்மை என்று தெரிந்துமே நெஞ்சம் சொல்ல தயங்குதே. கைகள் கோர்த்து பேசினாலே தைரியங்கள் தோன்றுமே. கதை போமா கதை போமா கதை போமா ஒன்றாக நீயும் நானும் கதை போமா கதை போமா கதை போமா. நீ பேச பேச காயமாறுமே. Thank you so much.
That was really beautiful, Maruni. Up next, we have Danuli, who will be singing the song Sayara. We welcome you, Danuli.
Hey guys, I'm Danali from Gaul. So today I'm going to sing the song Sayara. Hope you'll enjoy it. तेरी सांसों के सांस में आँखें झुका के सुने मुझे तो मैं तेरे दिल की आवाज़ में हूँ। वो सुना है तू है रागा आगे कुछ नहीं मुझ में तो आधा तो मैंने ढूंढी होते न तू भी मैं तेरे सपने तू मेरा वादा हाय मैं मर भी जाऊं जो तुझको ना पाऊं बातों में तेरी मैं रातें बिताऊं धड़का पे लम्हा लम्हा बेनाम तेरा है, तुझको ही गाऊं मैं, तुझको पुकारूं। सैयारा तू तो बदला नहीं है, मौसम सा रूठ हुआ है। सैयारा तू तो बदला नहीं है, मौसम सा रूठ हुआ है। सैयारा 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 सैयारा। Hope you enjoyed my song. Thank you for listening.
Wow, this was an amazing performance. Thanks for sharing your talent. Next up, we have Pranisha Diagaraj. She is the title winner of Voice Team Sri Lanka, and today she is with us to sing Unakena Venum Sollu. Honestly, if you ask any students in this session, what do you want or Unakena Venum, the answer is probably A pass marks. But for next few minutes, all of us want to hear this song. Now it's your turn, Pranisha.
Hello everyone, I'm Pranisha Tyagaraja. I'm very proud to say that I'm also a Perory Sir's old student. For all the students who are here, I would like to wish you all the very best for your OL examinations. Let's enjoy the song. உனக்கென்ன வேணும் சொல்லு, உலகத்தை காட்டச் சொல்லு, புது இடம் புது வேகம் தேடி போவோமே. பிடித்ததை வாங்கச் சொல்லு, வெறுப்பதை நீங்கச் சொல்லு, புது வெள்ளம் புது ஆறு நீட்டி பார்ப்போமே. இருவரின் பகலிரவு, ஒரு வெயில் ஒரு நிலவு, தெரிந்தது தெரியாது போனோமே. உலகென்னும் பரமபதம், விழுந்த பின் உயர்வு வரும், நினைந்ததை நினையாது சேர்க்க போனோமே. ஒரு வெள்ளை கொலுசு போல இந்த பூமி சினங்கம் மேல, அழியாத வைரம் போல அந்த வானம் மிதங்கும் மேல. ஒரு வெள்ளை கொலுசு போல இந்த பூமி சினங்கம் மேல, அழியாத வைரம் போல அந்த வானம் மிதங்கும் மேல. கலங்கிடக்கூடாதென்று தினம் தினம் இரவு வந்து தூங்கச் சொல்லியதே. எனக்கென உன்னை தந்து, உனக்கென கண்ணை தந்து, அதன் வழி எனது கனா காணச் சொல்லியதே. நீ இடம் பிடித்தாலும் போகின்றேனோ, கொள்கின்றேன். உனக்கென்ன வேணும் சொல்லு, உலகத்தை காட்டச் சொல்லு, புது மேகம் தேடி போவோமே. பிடித்ததை வாங்கச் சொல்லு, வெறுப்பதை நீங்கச் சொல்லு, புது வெள்ளம் புது ஆறு நீட்டி பார்ப்போமே. Thank you so much for the opportunity, sir.
That was graceful, and thank you, Pranisha. And finally, as we come to the end of this talent show, I extend my sincere gratitude to Sir King's Perory for organizing this wonderful physics night and encouraging our talents. And my heartfelt gratitude to all the performers for their wonderful performance and my co-announcer Krisha. And I would like to acknowledge that we experienced a few technical issues during the program. However, with everyone's cooperation, we did our best to ensure the smooth conduct of today's event. Once again, thank you all. And over to you, sir.
Thanks to all the performers and the organizers there. You have done a really good job. I was just sitting and watching that, right? Uh, I would like to tell that I was not involved in most of things. I just asked for a rehearsal. HRI, yeah. Just before the session, I just wanted a rehearsal. HRI, all these things they have organized and all those things they have made, and all have done a really good job. And all those who sang also, super voice you all have. Um, you all have a very good future as well. Right? God bless you all. Harry? Right. So now sleepiness should have gone. Again, thanks to all those students who help the other students to get out of their sleep. Now 2 sections are done. One special event is also done. Another special event is there. Another about 2 small chuty events are there. Other than that, now we have 2 more lessons also to finish. One is power and energy of electrical appliances. Second one is Newton's laws of motion. At the end, I'll be teaching you all how to answer any question in physics, right? Those are the things that are remaining. And now we have started our next day as well, 16th. It is 16th January as well. 1 day is past. Hurry, right. Come back to the working mood now. Now settled? Now settle down? Yes. No sleep? Hurry, right. Next section, we have to start with power and energy of electrical appliances. Power and energy of electrical appliances. Right. Power and energy of electrical appliances. Under this, what you learn about? You learn about electrical appliances that you have. Maybe at home, maybe wherever you are. Electrical appliances that you have and how they work. Under this section, we have 2 subsections to learn. One, there are equations, calculations part. Second, how we get current electricity to our house. 2 sections. Starting off with the first one, equations under power and energy of electrical appliances. Equations under power and energy of electrical appliances. First, we already discussed power of an electrical appliance, P. Power of an electrical appliance is equal to voltage multiplied by current. First equation, power of an electrical appliance is equal to voltage multiplied by current. Second, energy of an electrical appliance. Energy of an electrical appliance is equal to power multiplied by the time it works. Energy is equal to power into time. Second equation. Third, a remade equation for energy. A remade equation for energy. How to remake? We already know energy is equal to power into time. And we know power is equal to voltage into current. Using the first equation and the second equation, I can integrate and write energy is equal to power into time. We already know power is equal to voltage into current. So instead of power, I can apply voltage into current. Instead of power, I put voltage into current. Time will remain the same. Time will remain the same. So third equation, energy is equal to voltage into current, that is power, multiplied by time. VI, third equation. Using them, we'll do questions. Question number 1. Calculate the power of an appliance with 3 volt with potential difference of 3 volt and current flow of 2 ampere. Simple question. Calculate the power of an appliance with potential difference 3 volt. Potential difference we know. And current flow 2 ampere. How to calculate the power? Power is equal to voltage into current. What's the voltage there? 3 volt. What's the current there? 2 ampere. So if I do the math, 3 into 2, how much? 6. Power, what's the unit of power? Watt. What's the unit of power? Watt. So you write as 6 watt. So remember, unit of power is watt. Unit of power, watt. Okay. Second question. We'll take it as a continuation. In the above appliance, calculate the energy consumed, that is electrical energy consumed during 1 hour. In the above appliance, calculate the energy consumed in 1 hour. You all give it a try. In the above appliance, calculate the energy consumed in 1 hour. 1 hour, what's the energy? Calculate. In the above appliance, calculate the energy consumed during 1 hour. Above appliance, we know the power. Power is 6 watt. Energy consumed in 1 hour. Time is given 1 hour. Remember, we never do physics question with hours unless and otherwise they ask us. That hour should be converted into the SI unit. Ko tell me what's the SI unit of time? Seconds. 1 hour kya how many seconds are there? 1 hour is 60 minutes multiplied by 60 seconds. How many seconds are there? 3600. 3600 seconds. Now do the math. Energy is equal to power into time. Energy is equal to 6 watt multiplied by 3600 seconds. So if I do the math there, 216,000, 21,600 unit comes as what? Joules. Energy is measured in joules. 21,600 joules. So your answer comes as joules. Unit is joules. Okay. Understood? Right. Next. Sometimes they will ask you to calculate the electrical energy in kilowatt hour. They will ask you to calculate the electrical energy in kilowatt hour. How do you calculate electrical energy in kilowatt hour? Listen, electrical energy in kilowatt hour is equal to power in watt, divided by 1000 multiplied by number of hours. Power in watt divided by 1000 multiplied by number of hours. You can calculate the power, you can calculate the electrical energy in kilowatt hour. Power in watt divided by 1000 multiplied by number of hours. I'll do a question and show you. On see, third one, Nathan. Calculate the electrical energy in kilowatt hour of an appliance with a power of 3000 watt working for 6 hours. Calculate the electrical energy in kilowatt hour of an appliance with a power of 3000 watt working for 6 hours. We'll calculate. How to calculate the electrical energy in kilowatt hour? Electrical energy in kilowatt hour is power in watt divided by 1000 multiplied by number of hours. What is the power in watt? 3000 watt. Divide by 1000 multiplied by number of hours. What is the number of hours here? 6 hours. So when I do the math there, I directly get the electrical energy in kilowatt hour. I'll directly get the electrical energy in kilowatt hour. So if I do the math, 3000 divided by 1000, 3 multiplied by 6, 18. 3 multiplied by 6, 18. So your answer is 18 kilowatt hour. Why? They are asking the electrical energy in kilowatt hour. So your answer will be 18 kilowatt hour. Again, you don't need to write it as joules. Make a joules navy. You're directly giving a kilowatt hour. Okay, so here the electrical energy is equal to 18 kilowatt hour. How did you do? Power in watt divided by 1000 multiplied by number of hours. Okay. Question. Kilowatt hour. Kilowatt hour is a unit used to measure energy or a unit used to measure power? Tell me answer. Kilowatt hour is the unit used to measure electrical energy. Then it is used to measure power. Energy the power. Energy. It's a unit used to measure energy, not power. Just because you are seeing kilowatt, I know some students start thinking that is power. Power never energy. Look at the question. I am defining kilowatt hour for energy. Kilowatt hour is a unit used to measure energy. Don't just reside on kilowatt and tell, oh, it is power. Nah. Kilowatt is multiplied by hour. What do you mean by kilowatt multiplied by hour? What do you mean by kilowatt multiplied by hour? Kilowatt is a unit for power. Hurry. Hour is a unit for time. So kilowatt hour has the quantity power and time together. Power and time together. Tell me, power and time together is what? Energy. So remember, kilowatt hour is a unit used to measure energy. Okay. Got it? Those who want to write, quickly write down or maybe take a screenshot 10 key. Previous one. and the previous one. PD means potential difference. Hurry. Now go to your tute. In the tute, power and energy of electrical appliance, a box is kept. I want you all to write all the equations there. Write all the equations I give. Maybe you can write it in 2 sides. Write the unit also nearby. Here also unit is joules. Here the unit is kilowatt hour. Okay. Right. Done. Now the past paper question based on all these questions. Right. We'll try to do this past paper question. On the theory is very simple. Ne? See how they are asking the past paper question. How they are asking the questions. Right. C part maybe. Only the B part. Only the B part. Only the B part. You all try to do it. Not clear. I'll write a screen sharing. This one. How to solve? See, check one. See, this we did a rapid revision as well. The time spent for boiling a quantity of water required to prepare 4 cups of tea using an electric kettle, which indicated that the power is 1000 watt. Those are important points. 1000 watt is 3 minutes. Time spent for boiling a quantity of water required to prepare 4 cups of tea. They are only preparing 4 cups of tea. To prepare 4 cups of tea, time taken to boil 3 cups by a kettle of power 1000 watt is 3 minutes. It seems right. Now, Roman 1, calculate the amount of electric energy spent here. What's the power? 1000 watt. What's the timing? 3 minutes. Right. Will work. Power 1000 watt, time 3 minutes. So you all tell me, can we do the question using minutes? No, we have to convert to seconds. Go tell me 3 minutes is how many seconds? How many seconds? 180 seconds. 180 seconds. Now they are asking the electrical energy. Now they are asking the electrical energy. How do you calculate the electrical energy? Electrical energy is equal to power into time. Electrical energy is equal to power is 1000 watt, 1000 watt multiplied by the time is 180 seconds. From there, the energy is equal to 180,000 joules. Got it? That is easy. 180,000 joules. Yes. Second question. What's the second question, Delhi? How much is the amount of electrical energy in kilowatt hour? Inside bracket, they have given something. 1 kilowatt hour is 3.6 into 10 to the power 6 joules. Now, using this hint, if you are doing the question, you can do it in a different way. Without the hint, you can do the question in a different way. How much is the amount of electrical energy in kilowatt hour? They have given a hint for us. 1 kilowatt hour is 3.6 into 10 to the power 6 joules. They have given a hint for us. So if we use the hint there, what is the hint they have given? What's the hint they have given? They have given us 1 kilowatt hour is 3.6 into 10 to the power 6 joules. Now, what are they asking? We already have calculated a certain amount of electrical energy, that is 180,000 joules. What is 180,000 joules in kilowatt hour? What is 180,000 joules in kilowatt hour? This one we have to calculate. 1 kilowatt hour is 3.6 into 10 to the power 6 joules. 180,000 joules is how much in kilowatt hour? How much in kilowatt hour? This one we don't know. I don't know. No, I'll just put a symbol for that. I'll put E. I know one relationship. 1 kilowatt hour is 3.6 into 10 to the power 6. They are asking us, 180,000 joules is how much? One relationship I know, one relationship I don't know. One I know, one I don't know. Mathematically, how to do this question? One relationship you know, one relationship you don't know. Now, how do you do the question mathematically? You divide the left side, you divide the right side, equalize both. Divide the left side, 1 kilowatt hour divided by energy. Divide the right side, 3.6 into 10 to the power 6 joules divided by 180,000 joules. Equalize it. That is how you do mathematical questions like this. One relationship you know, one relationship you don't know. Now, one side you divide, the other side you divide, you equalize both of those. You equalize both of those. Now, as this is in scientific notation, we'll convert this also in scientific notation. 180,000 joules. How can we write it in scientific notation? 180,000 joules. How do we convert it into scientific notation? In scientific notation, we have to jump zeros. We have to jump decimals. Initially, decimal is here. From there, I am jumping 1, 2, 3, 4, 5. 5 decimals front. When I jump 5 decimal front, I get 1.8 into 10 to the power 5 joules. Neither. I have to jump 5 decimals. 1, 2, 3, 4, 5. Then decimal will come here. 1.8 into 10 to the power 5 joules. So that is going to be 1.8 into 10 to the power 5 joules. So instead of writing 180,000 joules, I'll write 1.8 into 10 to the power 5, 10 to the power 5 joules. Now, maths. 10 to the power 5, 10 to the power 6 cancel off. Only 110 will be remaining there. Only 110 will be remaining there. This side 1 kilowatt hour divided by energy E is equal to 3.6, 1.8 will be cancelled off. 2 will be remaining there. 2 into 10, 20, 20 over 1 will be remaining. I have to subject energy. If I subject energy, energy goes on top. 1 goes up, 20 comes down. So energy is equal to, energy goes on top. 20 comes down, 1 goes up. 1 over 20. What? 1 over 20 kilowatt hour. 1 over 20 kilowatt hour is how much? 0.05 kilowatt hour. Hurry. Hurry. I am writing all the steps, but I have told you all, no need to write all the steps. You have to reduce the steps as much as possible. Now I can't show my colors here. But colors I can write energy is equal to 0.05 kilowatt hour. I can write. You can't understand. No? I am writing all the steps, how this goes, how that goes. I take. You don't need to write all the steps. You show your colors in the paper. Method jump කරන්න. Method. From here you jump to this answer. From here you jump to the final answer. Correct. Can we write 1 over 20? Usually my science and maths questions don't keep the final answer as a fraction unless and otherwise they told you to keep it as a fraction. Because fraction is not a final answer. Decimal is the final answer. Fraction means what? Divisible. You can still divide it. 1 over 20 means what? You are dividing 1 over 20. එහෙනම් keep the final answer as 0.05 kilowatt hour. Harne? Can we do it in the method I taught? What's the method I taught? Energy in kilowatt hour is power in watt divided by 1000 multiplied by number of hours. Can we do it in that way? Yes, we can. Try it. Try it. Habating here you don't need because they have given a hint here. Here they have given the hint. Hint is given. Hint is given. So using the hint only we are doing. Without the hint, let's take that bracket is not given. Ehenang how to do this? Ehenang how to do this? See, they have told 1000 watt working for 3 minutes. 1000 watt for 3 minutes. And can we calculate the energy in kilowatt hour? 1000 watt for 3 minutes. 1000 watt can a power in watt is there? 1000 watt. Time in minutes is there. Minutes is the problem. 3 minutes. Hurry. Now can we calculate the electrical energy directly in kilowatt hour without the hint? Yes. How? Electrical energy in kilowatt hour is equal to power in watt divided by 1000 multiplied by number of hours. What is the power in watt? 1000. Divide by again 1000. Multiplied by how many hours are there on 3 minutes? Tell me that in hours. Now you convert to hours. 3 minutes. Minutes how you convert to hours? Multiply by 60, the divide by 60. Divide by 60. So 3 divide by 60 hours. Hari nilamai. 3 minutes is equal to 3 over 60 hours. 3 over 60 hours. Now if I do the math, can I get the answer directly? Oh yes. 1000 cancel off. 3 divided by 60 is how much? 1 divided by 20. 3 divided by 60 is 1 divided by 20. How much is 1 divided by 20? One shot you get the answer 0.05 kilowatt hour. Actually speaking, without hint doing this question is more easy, isn't it? Or hint කියලා දීලා they have like troubled us. Without the hint doing this question is more easy. අර hint එක දාගෙන I know you all hate these kinds of big numbers, no? ඕක scientific notation එකේ ලියාගෙන some people what they do is they expand the numerator 3.6 into 10 to the power 6, no? Instead of writing the other one in scientific, ඕක expand කරන්න යනවා. ඕකත් expand කරලා cut off all the zeros. එහෙමත් යනවා. Actually hint is not needed. That's why I told you this paper making people are naughty fellows. Without the hint you can do the question more easy. Alright. If you want, take a screenshot of this also and keep. In case if the hint is not given, you can do the question like this. Hari ne? Hari. Right. Go to the last question. What's the last question telling? What's the last question telling? How much is the amount of electrical energy wasted? They are asking us a wastage. In kilowatt hour, if an amount of water required to prepare 8 cups of tea was boiled to prepare only 4 cups of tea. Understanding this question is very important. How much is the amount of electrical energy wasted? They are asking a certain wastage. If an amount of water required to prepare 8 cups of tea was boiled to prepare only 4 cups of tea, They are using electrical energy that you can use to prepare 8 cups of tea and preparing only 4 cups of tea, it seems. Using the energy for 8 cups, they are preparing only 4 cups, it seems. There is a wastage, no lamai. Now think like you are making tea, right? You are making tea. When you are making tea, let's take you are making tea for 4 people. To make tea for 4 people, you keep the water in the cooker, or let's take electrical kettle and boil it for, let's take 5 minutes. 5 minutes boiling is enough to make the tea for 4 people. What you're doing is you're keeping the water in the cooker, in the kettle. 4 people required tea. 4 people required water for the tea. You're keeping in the kettle and you forgot. You started listening to Sayyara song now. More scene. Now what happens? That water is boiling. Or 10 minutes wala boil when water, now it is boiling for half an hour. 10 minutes boiling water is boiling for half an hour. Can you see there is a wastage there? In half an hour, maybe you can make tea for 8 people. So for 8 people timing, it is boiling. But what is boiling? Only 4 people's cup of tea. That is the question asking. So water is boiling for 4 people's cup of tea, but it is boiling for 8 people's cup of tea. The time that is necessary, sorry, how much is the amount of electrical energy wastage in kilowatt hour? If an amount of water required to prepare 8 cups of tea was boiled to prepare 4 cups of tea. 8 cups of tea, that amount of energy is used to produce, to prepare only 4 cups of tea, it seems. How to do this question? We'll do like this. We'll calculate how much of electrical energy is used to prepare 8 cups of tea. We'll separately calculate that. How to calculate it? We already have amount of energy for 4 cups of tea. Whatever the calculation we did until now was for 4 cups of tea. So for 4 cups of tea, we have all the information. Using that, we can calculate the amount of electrical energy for 8 cups of tea. So we'll calculate the amount of electrical energy for 8 cups of tea separately. And they are asking how much is the wastage. No? We will find the electrical energy for 4 cups of tea. We have already found that. We'll find for 8 cups of tea. We'll find for 4 cups of tea. When we subtract that, can't you find the wastage? We'll find separate for 8 cups of tea. We'll find separately for 4 cups of tea. Can you subtract that? Can't you find the wastage? So we'll proceed like that. Electrical energy for 8 cups of tea. Electrical energy for 8 cups of tea. I'll write it as E8. Now we already know from the previous question, electrical energy for 4 cups of tea. 4 cups of tea, what is the electrical energy in kilowatt hour? We have done the calculation already, 0.05. See, this question is done for 4 cups of tea. For 4 cups of tea, I know 0.05 kilowatt hour. Henang, tell me 8 cups of tea is how much from this? What you do? This is for 4 cups of tea. Henang, to find 8 cups of tea, you multiply it by 2. Harine. For 4 cups of tea, the electrical energy is 0.05 now. 8 cups of tea, you multiply it by 2. So if I multiply it by 2, my electrical energy for 8 cups of tea become 0.1 kilowatt hour. That is for 8 cups of tea. And we already know electrical energy for 4 cups of tea. 4 cups of tea, what is the electrical energy? 0.05. 4 cups of tea. 4 cups of tea, we know the electrical energy 0.05 kilowatt hour. We know for 8 cups of tea. We know for 4 cups of tea. Can't we find the wastage of energy here? I'll write E-waste. What's the wastage here? 8 cups of tea energy minus your prepared 4 cups of tea energy gives us the wastage. 8 cups of tea energy is 0.1 kilowatt hour minus 4 cups of tea energy is 0.05 kilowatt hour. When I do the math there, I can find the wastage. How much? 0.1 minus 0.05. 0.1 minus 0.05, you get how much? 0.05. Neither. Subtract and see. 0.1 minus 0.05, you get 0.05 kilowatt hour. That's the waste. That's the waste. Are in element? This is the real energy you need to prepare 4 cups of tea. But this fellow made that same 4 cup of tea using this much of energy. Again, he has kept the kettle and forgot. So instead of using this much of energy, he is using this much of energy. So when you subtract that, you can find the waste. Got it? Can't we take the direct answer? Yes, you can. Just by that, that's the talent of you. That's what you should practice. Now I can't directly tell the answer. This is the answer. Another question understand, and then you will be confused. So this is the physics behind it. This is the maths behind it. Correct? Okay. Now is the toughest time period. Dragging this time is the toughest time period. Dragging until 12 is okay. Dragging 1, 2 is the toughest time period. After you pass the 2 o'clock, again you will get a freshness. Dragging this time is this is the toughest time period. After you drag this, you can break up to 4. Hari ne? Hari ne? Hari, right. That's how you do those questions. We wrote all the equations. So the equations are only this. Next new section. Under power and energy, next new section. How do we get electrical energy to our house? How do we get electrical energy to our house? To our house now, how do we get electrical energy? Electrical energy is produced in power station. Electrical energy is produced in power station. Power stations will produce the electrical energy. They will produce the hydropower station, wind power station, coal power station. They produce the electrical energy, and using step-up transformer, they increase the voltage to about 132 kilovolt or 220 kilowatt. In power stations, electrical energy is produced, and using step-up transformers, they increase the voltage to 132 kilovolt or 220 kilowatt. And then this transform that into national power grid. It's sent into national power grid. Now, what is national power grid? Now in Sri Lanka, different power stations are there. Nurachole coal power station is there. Hydro power stations are there. We have wind power station. All those power stations will produce electrical energy. After they produce the electrical energy, they will supply it to a center controlling unit. Or center controlling unit is the national power grid. Center controlling units, it's like the controlling station at the middle. So all those power stations produce the electrical energy, they send it to the center. So all those energy comes to the center. Center point is the national power. National power grid will only distribute it to the distribution subcenter. We won't receive directly the electrical energy from the power station. First it goes to the national power grid. From the national power grid, electrical energy goes into distribution subcenters. It goes to distribution subcenter. At distribution subcenter, they reduce the voltage. Usually they reduce the voltage to 33 kilovolt or 11 kilowatt. So now see, first power station produces the power. They increase the voltage and supply it to the national power grid. Why they increase the voltage? That can come as a question. Why they increase the voltage and set it? They produce and they increase the voltage and supply it to the national power grid. Why they increase the voltage? Only see. We already learned in a step-up transformer, When you increase the voltage, what happens to the current? When you increase the voltage, automatically what happens to the current? Current flow will decrease. Current flow will decrease. Now, at the power station, they are producing power and increasing the voltage and supplying. Tell me, when they increase the voltage, what happens to the current flow? Automatically decrease. They are trying to decrease the current and send. Why they are trying to decrease the current and send? Think now. If they try to send large current through those wires will get heated. If the wires get heated, there will be heat loss. Y'all tell me. Our electricity board should try to increase the loss or reduce the loss. Reduce the loss. So to reduce the loss, they should try to send less current. So to send less current, they use step-up transformer and increase the voltage. Why? Even though voltage is increased, current is decreased, is the power going to change? Even though voltage is increased, current is decreased, is the power going to change? Power remains a constant. So throughout the distribution, power remains constant, voltage is increased, current flow is decreased. That's why they use step-up transformer and increase the voltage and send to the national power grid. From the national power grid also to the distribution subcenters, it goes with a voltage of about 33 kilowatt, 11 kilowatt. Even here, high voltage is only sent. High voltage is only sent. High voltage comes there. From the distribution subcenter through distribution cable, listen, electricity comes into our nearby house. Distribution cable. Have you all seen in the roads? There are 3 wires like this going together. There will be 3 wires like that going together. That is distribution wire or the distribution cable. From the distribution wire or the distribution cable, another separate wire will come into your house. From there, a separate wire will come into your house. What is that called as? That is the service cable. That is the service cable or the service wire. This is distribution wire. This is distribution wire. That is a service cable. So from the distribution cable now comes into your service cable. Service cable. By the time current comes into the service cable, voltage is about 230 volt. Why? Our domestic electrical supply in Sri Lanka is 230 volt. So to our houses, 230 volt voltage of a potential difference is only given. So now current comes into the service cable. From the service cable, first current goes into overload circuit breaker. What is this overload circuit breaker? It is present outside your house. Outside the house, not about 1 kilometer away. Just outside. It goes to your overload circuit breaker. Just outside. Just outside, you can see a meter box. Normally we tell meter box. In the meter box, you have the electricity meter. Nearby that, you have the overload circuit breaker. It can be a fuse or it can be a switch. It's an overload circuit breaker. So first current goes into overload circuit breaker. What will overload circuit breaker do? In case if a current of more than 40 ampere comes. In case if current of more than 40 ampere comes, it automatically disconnects the current to your house. Sometimes it can happen. From the distribution wire through the service cable, more than 40 ampere current can suddenly come inside. If such a current comes inside, automatically it will disconnect. So overload circuit breaker works as a circuit breaker protection for 40 ampere or more than that current. Next, from the overload circuit breaker, Next, current goes into your electricity meter. Now goes into your electricity meter. Both overload circuit breaker and electric meter are present outside the house and it doesn't belong to the consumer. This doesn't belong to you. This unit doesn't belong to you. If there are any problems there, you can't go and repair that. You can't take an electrician repair that. You have to inform your electricity provider. If it is national electricity, if it is our electricity board, you have to tell the electricity board that's how you repair that. You can't go and repair that. You can't go and repair. This is not under your control. You can't go and repair. These two are not under your control. These two are those two are not under your control. Next, from electric meter, now the current comes inside your house. After electric meter, all the devices are yours. From electric meter, first current comes into the isolator. It comes into your isolator. Isolator කියන්නේ maybe in your trip switch box. ඕකට trip switch box කියන්නේ ඒකට කියන්නේ consumer unit කියලා. In your consumer unit, you can see so many these things. You can see so many switches. The first switch has kind of two parts together. Remember, two parts are there together. And then another switch is there with a button on top. And then there are so many small switches. It is divided. So this has double switch together. Next, a single one. Next, so many switches. On this double switch together is called your isolator. That is your isolator. That is your isolator. That's your isolator. From the isolator, next the current goes into residual current circuit breaker, RCCB. From RCCB, next the current goes into miniature circuit breaker, MCB. What is RCCB and MCB? What is RCCB and MCB? On the second one is RCCB. That is what we tell in our talkative language, the trip switch. Second one, this is what we tell in our talkative language, the trip switch. Okay, trip switch kiyanne RCCB. After that, the small switches are called as the MCB. What are their functions? Listen. Isolator, RCCB. Both can control live wire and neutral wire. Both isolator and RCCB both can control the live wire and your neutral wire. Both live and neutral they can control. So both are connected to them. As both are connected to them, you call them dual polar switches. What polar switches? Dual polar. When you put the isolator down, you're disconnecting both live and neutral there. If you put RCCB down, again you are disconnecting both live and neutral. It won't work with overload circuit breaker. Overload circuit breaker can only disconnect the live wire. Neutral is not connected to the overload circuit breaker. Only live you can disconnect, neutral you can't disconnect. Now tell me a difference between overload circuit breaker and isolator. Overload circuit breaker only can disconnect live wire. Isolator can disconnect both live and neutral wire. Here only one, here both live and neutral can disconnect. Keep that in mind. So here isolator, it can disconnect both live and neutral. RCCB also can disconnect both live and neutral. What's the function of isolator? Isolator acts as a protector for 30 ampere current. If a current more than 30 ampere comes, isolator will disconnect. It's a protector for 30 ampere entry. So inside your house also you have a protection unit. Overload circuit breaker is outside. Inside the house also you have protection, that is the 30 ampere protection by isolator. What will RCCB do? Let's take there is any current leakage to the metal casing of an electric appliance. For example, let's take oven. Oven has a metallic oven. If there is any current leakage to the metallic cover of the oven, when you go and touch it, maybe you get the shock. If you are earthed, maybe you'll get the shock. To avoid that, RCCB will work. So if there's any current leakage in the electrical appliances, if there's any current leakage in the electrical appliances, RCCB will give the protection. Other than that, fire protection is also given by RCCB. So RCCB can act against leakages, RCCB can act against fire. Right? If you try to drag a lot of current, sometimes the wires get heated and they will try to start fire. There can be fire starting. So fire protection, electrical leakage protection, both are given by RCCB. Fire protection, electrical leakage protection. Does it give us protection from lightning? No. So remember, RCCB gives us protection from electrical leak and fire. MCB. MCBs are this. Each one of these small unit is connected to each location in your house. Maybe this is connected to the hall. It will control all the switches in your hall. This is connected to your room. It controls all the switches in your room. This is connected to your, let's say, washroom. Controls every switches in your washroom. So each one of this single unit controls each one of the location in your house. That is MCB. From the MCB, now power is given to your switches, bulbs, all those things. Switch, bulb, all those connections are given from there. Okay. Should we memorize these names? Yes. In order you have to memorize. In order you have to memorize. One more time. Now itself will memorize. Power station. Power station will produce electricity. From there, using step-up transformer, they increase the voltage to 132 kilovolt or 220 kilovolt, and then they send it into national power grid. Why they increase the voltage? To decrease the current. Therefore, there won't be any heat loss. So now current comes into the national power grid. From national power grid, next the current goes into distribution subcenter. Distribution subcenter will decrease the voltage to 33 kilovolt or 11 kilovolt. And then they send it through distribution wire into the service cable. And finally current comes into your house. How much of voltage? 230 volt. First current enters overload circuit breaker, then electric meter. Does it belong to us? No, it doesn't belong to the consumer. It belongs to the electricity supplier. Next current goes into the isolator, RCCB, MCB. Isolator, dual polar switch. RCCB, dual polar switch. Both of them can disconnect both live and neutral. Overload circuit breaker can only disconnect live. Okay, clear? Yes. Hurry, right. Now going to the question. Going to the tute. Those parts are given. A is the distribution wire, B is the supply cable, from their outside overload circuit breaker, electric meter, and then you have the isolator. E is isolator, F is residual current circuit breaker, G is miniature circuit breaker, MCB, H is switches, plug socket, light, earth wire, all those things are there. If you want, you can quickly write this flow chart and key. Not a big time, quickly write the flow chart and key. හරිනේ. හරි. One more time, we'll put the effort and memorize it and keep. First, power station, 132 kilovolt to 220 kilovolt. Voltage is increased, current is decreased. Why? To reduce the heat loss. Then goes to the national power grid. From the national power grid, distribution subcenter, voltage reduces to 33 kilovolt, 11 kilowatt, and then through distribution wire into the service cable. Finally, 230 voltage current comes into our house. First, overload circuit breaker act as a protector for 40 ampere current. Only live wire is connected. From overload circuit breaker, electric meter, it records how much of electric energy we consume. Both of that belongs to the electricity provider, not to the consumer. From electricity meter, isolator, RCCB, MCB. Isolator, 30 ampere protection. RCCB, leakage fire protection. MCB controls the distribution inside your house and then to the switches and the bulbs. Hurry. 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 Right. That is power and energy of electrical appliance. That is power and energy of electrical appliance. Before going to the next part, a small this thing, another part is coming. Now, all this time, I am the one who tells you all to work, no? This is how you should work. I am the one who used to tell you all to work, no? This time, I am not going to tell you all. My last batch student is there. Miss Ashwika. She is from Jaffna. She is a person whom I observed working. Towards the end, during this time period, maximum effort she has put into this thing. I don't think Ashwika is a person who worked from the beginning. She will talk to you all. As I can remember, she is not a person who worked from the beginning. Towards the end, 9 A's from Jaffna. Recently, she visited my house also to talk to me and go. Ashwika will talk to you all how she worked in the last 1 month. Yes, Ashwika, over to you.
Yes, sir. Thank you. Hello, everyone. I'm Ashwika from last year's O-level batch. And I'm really happy to be here to share some study tips and motivations with you. First, let me fix something in your mind. I'm not a topper. I'm a very average student like you. I'm standing here as someone who cried a lot, failed a lot, and got very lowest marks. Yes, I got lowest marks. I had many negative thoughts about myself, but I didn't allow those thoughts to control me. That's the main thing. Okay? When I started my O levels, I was just like you. Earlier, I used to score 90s in science and maths until grade 9, but later my marks dropped suddenly. That made me feel pressure, right? I feel tired. Some friends left me. I expected too much from myself. Some teachers' opinions hurt me badly. At the end, I felt like a fool. But I never gave up. Instead, I decided to prove them who I am. That spirit changed my life, right? Everything was running in my mind like you. Time pressure, fear, stress. But until the last minute, I kept going. So my message to you is very simple. Don't focus on negativity. Focus on defeating it with positivity. People's opinions, comparisons, and pressure don't help you to grow, right? You only need your effort. Give your maximum. On results day, on that day, you will feel that pride inside your heart because I felt that. Remember this. Without sacrificing something, you cannot gain anything, guys. Even nature follows that rule, so you have to. This last 1 month is very important. Use it. Don't focus on anything else. Only focus on your studies, your goal. Your goal is big, 9 A's, or at least the best results you can give. Scrolling phones, chatting with friends, give small happiness for a few minutes. But think about the good results. That good results give you pride for a lifetime. So work hard for it. And I'd like to talk about two main subjects, maths and science. For maths, I felt very tensed at the end because of topics like percentage and sets. So to recover from that, I practiced a lot in last month. I did past papers from 2019 and also some Visakha College papers, Royal College papers, especially for maths I did. One question from Visakha College even came in my final exam, I remember. So that's how practice makes you better, right? And above science, I mainly followed King's Perory sir's advice, his time management tricks, rhythmic memorizing methods. When he asks you to tell that again with him, tell with him. So it will make you to memorize that easily. So follow him in science. Other than that, I did a lot of papers and asked a lot of doubts. That's the main thing. Asking doubts, clear them. And remember this, past papers are your key. If you use them properly, they can open the door called success. So practice a lot of past papers. Past papers are very, very important. And one more thing is, only do papers if you have a marking scheme or a teacher to guide you. Otherwise, it will confuse you and increase that stress level. For me, it happens. This last 1 month, stress can destroy everything. So revise the paper you already did in school and tuition and understand well. Understand them very well, okay? So don't go through the paper just like blah blah blah. Go through that very well, okay? And the main thing about technology, use technology to learn, not to escape from that stress, right? Don't waste time on reels, shorts, Instagram. Okay, so use it for study. When you walk into the exam hall, you should feel that fire. I'm ready, I'm going to give my best. Okay, for that stress-free state, you need to confident with your syllabus, so work for it. Don't let anything to disturb your focus, like family problems, financial problems, relationship problems. Those are very silly problems, guys. So your goal is big, so work hard for that. And don't say, akka, only 1 month is there, how is it possible? Like that, don't say like that. 1 month is more than enough if you start today. Open the book, put the phone down and start. Okay, don't waste your time. Please ask and clear your doubts before the exam day. Do many papers. If you don't clear your doubts now, they will come in the exam and laugh at you. So clear them and go to the exam. And the day before the exam, don't do new papers. Just revise your short notes, past papers, and what you already studied. And now I want to tell and I want to end with this. Work hard, work with King's Perory, sir. Don't get stressed. Handle the pressure very well. Practice well. Take rest and go and blast the exam. This year, I want to hear only one thing from King Sir. All the students of this batch got great results, Ashika. That's the thing I want to hear. I'm waiting to hear that. Thank you, juniors, for your time. All the best. Do well. And sir, thanks a lot for this opportunity. Thank you. Bye.
Thank you so much, Ashvika. Again, she is from Jaffna, attended my online class. She was there with me for about 6 to 7 months, I guess. From low to high, I observed in her. From lowest level to, you all know her result 9A. I observed in her. So as she told, it's not hard. 1 month is there. In 1 month, making a difference is not at all hard, not at all. It's on your hand whether you're going to make the difference or not. You put the effort, you study, you give your maximum, you fight for your result, you get your result. Right? That is on your hand. You can do that. If Ashvika can do, anybody can do. That's what I will tell. Right? We'll take a small break. Water plus washing the face, releasing the what do you call sleep and coming. Come at 2 a.m. 15 minutes break, 2 a.m. and we are going to work on Newton's law and some more things are there. Check one. Check one. Right. Last push. 2 o'clock past, now we think sleep will go. Final 2 hours. 6 hours are already done. Final 2 hours of push until 4 o'clock. Hurry. Right. And now it's the fire. And now our last part is the fire. Those are remaining until the end. That's the fire. That only builds your potential. Hurry. We did until power and energy of electrical appliances. Now going to Newton's laws of motion. Actually, with Newton's laws of motion, I'll be doing graphs of motion as well. But I'll be doing graphs of motion as well. Both I will do together. Newton's laws plus the graphs of motion. We touched it in a certain night session, graphs of motion, but fully we didn't touch. Hurry. Newton's laws of motion. Newton's laws of motion. There are 3 laws we know. Newton's first law, Newton's first law, Newton's second law, and Newton's third law. What is Newton's first law telling us? Newton's first law is telling us about 2 states of motion. One, it defines about object at rest, and it defines about object that are already moving. So it defines about 2 states of motion, object at rest, object that are already moving. What it is telling? Until an unbalanced force is applied, object at rest remains at rest. If an object is moving, it continuously moves with the same velocity. Until an unbalanced force is applied, object at rest remains at rest. If an object is moving, it continuously moves with the same velocity. That means object doesn't like to change their state of motion. Objects doesn't like to change their state of motion. If an object is at rest, it like to continuously be at rest. It doesn't like to change the state of the motion. If an object is already moving, it like to continuously move with that same velocity. No any objects in this universe like to change their state of motion, just like y'all. If you are sleeping, you like to continuously sleep. Or if you are doing something interesting, you like to continuously do that, unless and otherwise it is studying. So nothing in this universe like to change their state. Objects doesn't like to change their state of motion. Object at rest remains at rest. If an object is already moving, it moves with the same velocity. Until when? Until an unbalanced force is applied. Until an unbalanced force is applied. Until you apply an unbalanced force. Hurry, anything? Let's take this box. It will remain at rest. It is remaining at rest. So what it likes to do? It likes to continuously remain at rest. Until when? Until I go and apply an unbalanced force. The moment I apply unbalanced force, can you see it is moving? So until I apply unbalanced force, if it is at rest, it will remain at rest. If it is already moving, it likes to continuously move with that same velocity. What are the examples for this? Examples, remember, that is what they will give in your exams. Now let's take, you are in a bus. Bus is moving. If the bus is moving, lamai, we in the bus, we are also moving. We don't feel that, but we are also moving. Harine, you are taking a bus from location A to location B. You are moving from A to B. So inside the bus, you are moving. If the bus is going at 40 km per hour speed, we in the bus are also going at 40 km per hour speed. Even though we don't feel, we feel like we are at rest. No, we are not at rest. If the bus is moving at 40 km per hour, we are also moving at 40 km per hour. Our body is also moving at 40 km per hour. Suddenly, bus uncle applies a brake. You all tell me. We are already moving at 40 km per hour. Ehenang, we like to change the state of that motion, or we like to do that same thing? We like to do that same thing. So if we are moving at 40 km per hour speed, we like to continuously go in that 40 km per hour speed. But driver uncle press the brake there. So once he press the brake, do we like to change the state of motion? No. We like to continuously move with that 40 km per hour speed. Then we fall down. We fall in front. Harine, have you all come across that? When the bus applies a brake, we fall down. We fall front. Why we fall front? Because we don't like to change the state of our motion. We were moving, we like to continuously move. But he applied the brake. He is applying brake, now we have to move forward. That's why we move forward. Same thing, when the bus begins to move, from rest, initially bus is at rest, now it begins to move. Now initially bus is at rest, we are at rest. Then we like to continuously be at rest. Do we like to change the state of our motion? No. But driver uncle there, he is accelerating the vehicle. He's trying to move. We are at rest. We don't like to change our state of motion, but he is trying to move the bus. Then what will happen to us? We fall behind. Because we are at rest, we like to continuously be at rest, not go with the bus. We move behind. So those are examples for Newton's first law. Another example, dust remains in the carpet. A lot of dust is there in the carpet. The dust is at rest. Then it like to continuously be at rest. If you go and remove that, if you apply some force and if you go and tap it and remove, only that dust will come out. Until you tap it, if it is at rest, it will remain at rest. A water bottle on the table. Until you go and move it there, water bottle will be at rest. And have you all come across this? Let's take a cup. We'll take a cup. We'll take this cup. What is it? Cup. Now let's take on this cup, there is a paper. I keep a paper on top of this. Paper is there. I keep a paper on top of this. Magic never, yeah. I keep a paper on top of this. On top of the paper, I keep a coin. A coin is there on top of the paper. If I quickly pull the paper and take, now here I can't do that. Upset gyot hina. If I quickly pull the paper, no, I should quickly pull it. If I quickly pull that paper, what will happen to the coin? Coin will go with the paper, it will fall on the tumbler. Very quickly I have to pull the paper. It will fall. Because I'm holding and doing this. Maybe this say I hold it tender. If I quickly pull it, it falls. So if I quickly pull the paper and take, coin will fall down. Why? Coin was at rest, then it like to continuously be at rest. It doesn't like to go. It doesn't like to go. Harida? It doesn't like to go. Right? So those are all examples. And remember the example, in the exam they'll give example and ask which law in Newton is applied there. So that is Newton's first law. Next, going to Newton's second law. Newton's second law. What is Newton's second law talking about? It is talking about acceleration. First law is talking about object at rest, object that are already moving now, it moves with uniform velocity. Already moving now, that object will continuously move with uniform velocity. So first law talks about object at rest and object that are moving at uniform velocity. Second law only talks about the acceleration. What it tells about acceleration? Acceleration is directly proportional to the unbalanced force. Acceleration is inversely proportional to the mass. What do you mean by directly proportional, indirectly proportional? Directly proportional means when one factor increases, automatically the other factor increase. Indirectly proportional means when one factor increase, other factor will decrease. Indirectly proportional. Newton doesn't need to come and tell. Just think practically. You apply a larger force on an object. What will happen to the acceleration? You apply such a big force. What will happen to the acceleration? Acceleration will increase. Practically think on a certain box or something, you go and become, you give a big force there. Acceleration is high. You give a small force, acceleration is less. So when force is more, acceleration is high. When force is less, acceleration is less. Mass and acceleration. Let's take a 30 big mass. you are pushing. A small mass, you are pushing. Big mass, small mass. Big mass, small mass. When you push the big mass, it will move very slowly. Why? Big mass acceleration is less. Small mass, it will move faster. Why? Small mass acceleration is high. So Newton doesn't need to come and tell. Force and acceleration are directly proportional. One increase, the other increase. Mass and acceleration are indirectly proportional. Why? When mass becomes big, acceleration becomes small. Mass increase, acceleration decrease. And from these two, there's an equation from these things you all know. F equal ma. Force is equal to mass multiplied by acceleration. F equal ma equation comes. Okay. Now what are the examples for this? Let's take two trolleys in the supermarket. A trolley with no anything inside, again mass is less. A trolley with so many things inside, mass is high. Nothing inside, mass is low. So many things inside, mass is high. Nothing, so many things. Nothing trolley will move faster when you apply a force. So many things trolley will move slowly when you apply force. I.e., nothing trolley, mass is less, acceleration is high. Lot of mass trolley, mass is high, acceleration is low. Hurry. Hurry. So that is second law. Third law. What is Newton's third law telling us? What is third law telling us? Every action has an equal and opposite reaction. Every action has an equal and opposite reaction. What does this mean? Now let's say you have a balloon filled with air. When you release it, balloon goes up. Balloon with air, when you release it, it goes up. Why is the balloon going up? Balloon will push the air down. Balloon push the air down on, that is your action. Balloon push the air down, action. Due to that, air will push the balloon up. Air push the balloon up. That is reaction. Balloon push the air down, action. Air push the balloon up, reaction. Another example, a rocket flying skywards. A rocket flying skywards. How does a rocket go skywards? Rocket will push the burnt fuel down. ඕකට තමයි කියන්න ළමයි action. Rocket will push the burnt fuel down. Action. Then burnt fuel will push the rocket up. That is the smoke. Smoke will push the rocket up. That is the reaction. That is what we are talking about, action reaction. Another example. When you are walking, sorry, when you are walking, your beautiful leg is there. Using your feet, I would tell feet. Using your feet, you push the ground behind. Using your feet, you push the ground behind. That is your action. Then ground will push your feet front. Ground will push your feet front. On. That is your reaction. Harini, think about walking. How do you walk? Using your leg, you push the ground behind. That's what you do. Think and see. When you are walking, you keep your legs and push the ground behind. That's what you do. Then ground will push you front. We don't push the ground front, no. We push the ground behind. Ground will push us front. Eva action reaction. Even swimming, how do you swim? Using your hand, you push the water behind. Using your hand, you push the water behind. Your push is behind, that is your action. Then water will push you front, that is your reaction. Rowing a boat, when you're rowing a boat also, you push the water behind, that is your action. Then water will push you front, that's your reaction. Alright? So remember the examples. Examples are important. First law. Until an unbalanced force is applied on an object, bodies at rest remains stationary and bodies in motion continue to move at uniform velocity. Example, when a moving bus stops suddenly, passengers lean forward. A book kept on table remains at rest until it is pushed. Dust comes out of a carpet when it is beaten. A person standing in a bus falls backwards when the bus suddenly starts moving. A coin placed on card, that we have to do with card, not with paper. Otherwise, it will fall down. The activity that I did, it will fall down. It drops straight into the glass when the card is quickly pulled away. Second law. Acceleration of a body is directly proportional to the unbalanced force acting on it, while it is inversely proportional to the mass. Equation F equal ma. Example, an empty shopping cart accelerates more, loaded one accelerates less. Football moves faster when kicked hard. You kick the football harder, it moves faster. A smaller car accelerates more than a heavy truck. Or in a small car accelerates faster, more than a heavy truck for the same engine force. Pushing a trolley with greater force makes it move faster. It is easier to throw a light stone further than a heavy stone. Now that's also a good example. Light stone, you can throw it to a bigger distance. A heavy stone, can you throw it? No. Third law. For every action, there is an equal and opposite reaction. When a person walks, food pushes the ground backwards and the ground pushes him forward. When a gun is fired, now another one. When you're firing gun, gunpowder will burn there. Gunpowder will push the bullet front, which means gun will push the bullet front. Action. When bullet moves front, bullet will push the gun behind. That happens. If you see how the ones who handle the guns use the gun, the moment you shoot from the gun, the bullet goes front. Due to the recoiling effect, gun get pushed behind. That's why you lock it on the arm, you lock it here, and then you what you call shoot. Some people, some guns are there, even the tissues can go behind. Such a force is there. Such a force is there. So bullet goes front, gun comes behind. Yes, sometimes the hand get dislocated. Some soldiers hand get dislocated. That happens, right? Large machine guns even, this get dislocated. And usually in soldier training, STF training wala එහෙම, it is taught how to fix the dislocated hand. අපිට බෑනේ ළමයි. When the hand get dislocated, we directly go to Ayurveda doctor. එහෙම ගිහිල්ලානේ we go and fix. Those people, STF වල එහෙම, they are being taught in case if their hand get dislocated, how to fix it. So once when their hand get dislocated, they will again check where is the dislocation, fix it, and comes back. හරිද? Vijay can do. Right. Vijay can do. He was in STF training. He can do. ඒ වගේ he can fix it. Why? Mainly when they handle those guns, due to recoiling effect, sometimes hand get dislocated. It pains? No, it is very smooth, පුතා. හරි. So when gun is fired, bullet moves forward and the gun recoils backward. A swimmer pushes the water backward and moves forward. When a balloon is released, air rushed out backward and the balloon moves forward. While jumping off a boat, let's say you're on a boat, you jump from the boat. Go tell me, when you jump from the boat, let's say you're jumping front, you jump from the boat, you're jumping front, what will happen to the boat? Boat will also come front, it will go behind. Let's say boat is initially at rest. Boat is initially at rest. Think and tell me. You jump forward, what happens to the boat? Think and tell me. Or even skating boat, let's take skateboard. You jump front, what happens to the skateboard or the boat? It goes behind. Action, reaction. While jumping off a boat, the person moves forward and the boat moves backwards. Rocket launching upward. All those things are example for Newton's third law. Right. Additionally, I want to give you all the graphs of motion. It is not included in the tube, but I wanted to give you all. graphs of motion. Graphs of motion. There are two types of graphs of motion we have to learn. Already in a night class, I taught you all about displacement time graph. I didn't teach you all about velocity time graph. I want to give a summary. There are two types of graph we have to learn. One, displacement versus time. Two, velocity versus time. Displacement versus time and velocity versus time. Going to the first one. Displacement versus time. There are about 5 graphs you need to know. HRI. First graph. Displacement. Usually displacement is symbolized by capital S. Again, I repeat, displacement is symbolized by capital S. On displacement time. First graph. Let's take, you get the graph like this. What does this mean? What does this graph mean? See this. I have already taught in a night session. Time is going, displacement is increasing. Time going, displacement increasing. Time going, displacement increasing. Time going, displacement increasing kiyanne this object is having a velocity. Time is going, displacement is increasing. If displacement is increasing, this object is having a velocity. And can you see that displacement is increasing in a uniform manner? Then uniform non-uniform කියන්නේ මෙහෙම නම් non-uniform. එහෙම නෙවෙයිනේ ළමයි. A uniform manner displacement is increased. එතකොට you tell uniform velocity. And can you see displacement is increased, which means this object is moving forward. So I can tell this object has a uniform velocity forward. It has a uniform velocity forward. Now look at this. Displacement time. Now let's see. You have the graph downwards. What does the downward graph means? Deceleration make a deceleration. Analyze. Displacement. What is happening to the displacement? Displacement is decreasing. Displacement decreasing කියන්නේ that object is going to move backwards. Neither. Displacement is like distance. It's not distance, it's like distance. So if displacement is decreasing, that means that object is kind of moving backwards. So displacement is decreasing with the time, which means that object is moving backwards. If it is moving backwards, it will have a certain velocity. So this object has a velocity. That object has a velocity. Velocity is like speed. When you're moving backwards, in your reverse gear also you will have a speed. No? So in the reverse motion also there will be a velocity. So this object has a velocity. That velocity is in backward direction. That is in backward direction. Uniform than ununiform? Check whether the graph is smooth or not smooth. This is not smooth. This is smooth. Smooth කියන්නේ uniform. There's no any options there. Smooth non-uniform. Like this, if it is crooked, it is non-uniform. All the graphs in our syllabus are uniform. This is uniform velocity forward. This is uniform velocity backward. තව දෙකයි. තව තුනයි. Displacement time graph. Let's take, you have a straight flat graph like that. You get a straight flat graph like that. Go tell me, is the displacement increasing? No. Is the displacement decreasing? Again, no. Displacement not increasing, displacement not decreasing. Object is at rest. Yeah, the object is at rest. Hurry. Next. Only in displacement time graph, only in displacement time graph, we come across curved graphs. Curved graphs are only there in displacement time graph. No any other graphs. Other one is velocity time graph. No, in velocity time graph, you don't have curved graphs. On displacement time graph, if you see a curved graph like that, like that, what does that mean? If you see a curved graph like that, what does that mean? What does that mean? This is how you analyze. Look, okay? This is how you analyze. Look at the starting part of the graph. Can you see starting part of the graph? It is flat. Start is flat. Start is flat. Towards the end, it is almost vertical. Starting is flat. I would tell the gradient is flat. End is almost vertical. Again, a gradient is almost vertical. Now analyze. Flat means at rest. Flat is at rest. So at the beginning, it is flat. It is at rest. So beginning is rest. At the start, there is rest. Towards the end, there is a vertical line. Towards the end, vertical line කියන්නේ what ළමයි? Vertical line කියන්නේ there is a velocity, there is a certain speed. It has a certain speed. A high speed is there. A high velocity is there. Towards the end, there is a high velocity. Towards the end, there is a high velocity. Beginning rest, end is high velocity. Beginning rest, end is high velocity. Beginning at rest, end is high velocity. Now think rest to high velocity. Rest to high velocity what is happening? Rest to high velocity. Velocity is something like speed. From rest, you are going to high speed. What you are doing? Acceleration. You are doing acceleration. Rest to high velocity you are doing an acceleration. So this is acceleration. This is acceleration. What kind of acceleration? What kind of acceleration? Can you see the graph is going smooth? එහෙනම් uniform acceleration. That is uniform acceleration. Okay. එහෙනම් using that knowledge, tell me, what is this graph? What is that graph? And analyze the gradient there. Analyze the gradient. Initially vertical. At the end flat. Initially vertical, end is flat. Initial vertical කියන්නේ high velocity. At the end flat කියන්නේ it has come to rest. එහෙනම් tell me high velocity to rest. High velocity to rest. Acceleration, the deceleration. Deceleration. Uniform deceleration. Uniform deceleration. That is uniform deceleration. Got it? Yes. So all the graphs are given. These are the only graphs we have in our syllabus regarding displacement time. Those are the only graphs we have. Uniform velocity forward, up. Uniform velocity backwards, down. Object at rest. Uniform acceleration. Uniform deceleration. That is displacement time graph. Now going to velocity time graph. Velocity time. Here only 4 graphs are there. HRI. Here only 4 graphs nilamai. What are the 4 graphs? What are the 4 graphs? On the see, what are the 4 graphs? That is V, this is T, that is V again, that is T again, that is V, that is T, that is V again, that is T again, on the C. A vertical line upward. Think vertical line upward. Think now, think now. Time is going. Velocity is increasing. Time going, velocity increasing. Time going, velocity increasing. Time going, velocity increasing monad. A velocity is something like speed. Time going, speed is increasing. Acceleration. 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 What kind of acceleration? This is a smooth graph. What kind of acceleration? Uniform acceleration. Uniform acceleration. So don't get confused with velocity time graph upward and displacement time graph upward. Displacement time graph, this is uniform velocity forward. Velocity time graph, this is uniform acceleration. If that is uniform acceleration, this is uniform deceleration. How? Initially high velocity, with time velocity is decreasing. With time velocity is decreasing. Velocity is something like speed. Speed is decreasing with time now. Guaranteed deceleration on. That is uniform deceleration. Alright. Next. This. Rest kiya this is not rest. Think. See. Velocity. Is it increasing? No. Is it decreasing? No. Velocity not increasing, not decreasing. No, it is having the same velocity. Same velocity. Tell me another proper word for same velocity. Uniform velocity or constant velocity. Uniform velocity or constant velocity. Now, can you tell rest there? Banilamai. See, it has a certain velocity. No, this is the zeroth scale. It has a certain velocity value is there, a certain v value is there, a certain y-axis value is there. So certain velocity is there. It's not increasing, not decreasing. Now uniform velocity. What is going to be object at rest on? This is object at rest graph. Think about that graph. That is the zeroth line. Can you see graph is on the zeroth axis? On the zeroth line? Graph is on the zeroth axis, zeroth line. A object at rest. That is your object at rest. So be careful with velocity time graph. Velocity time graph upward, uniform acceleration. Velocity time graph downwards, uniform deceleration. Straight flat line, uniform velocity. Line on the x-axis, object at rest. Again one more time. Straight line up, uniform acceleration. Straight line down, uniform deceleration. Straight flat line, uniform velocity. Line on the x-axis, object at rest. This is velocity time graph. Displacement time graph. Straight line up, uniform velocity forward. Straight line down, uniform velocity backwards. Straight flat line, object at rest. Flat to straight, uniform acceleration. Straight to flat, uniform deceleration. One by one, tell me. Straight line, displacement time graph. Straight line up, uniform velocity forward. Straight line down, uniform velocity backwards. Straight flat line, object at rest. Flat to vertical, acceleration, uniform acceleration. Vertical to flat, uniform deceleration. Velocity time graph. Straight line up, uniform acceleration. Straight line down, uniform deceleration. Straight flat line, uniform velocity. Line on the x-axis, object at rest. Hurry. shall we write this Senki? I'll add 2 more points and then you'll write. 2 more points and then you'll write. In displacement time graph, what does the gradient of the graph gives us? Gradient gives us the velocity. Remember, gradient always gives us something higher, one step higher. This is displacement time graph. No? What is one step higher than displacement? Velocity. No? One step higher than displacement is velocity. No? So gradient of displacement time graph gives us velocity. What about the gradient of velocity time graph? Gradient of velocity time graph. Now, what is one step higher than velocity? Velocity time graph, what is one step higher than velocity? Acceleration. So gradient gives us acceleration here. What does area under the graph gives us? Remember, area under the graph gives us one step lower. Area gives us one step lower. Gradient gives us one step higher. So area under velocity time graph, what does it give? What is one step lower than velocity? Displacement. Area gives us displacement. Okay. What does the area under displacement time graph gives us? What does the area under displacement time graph gives us? Or a previous one? Remember, area under displacement time graph gives us nothing. It gives us nothing. No information. Harine lamai, is there anything below displacement? Is there anything below displacement? Can I go one step below displacement? Nah. Velocity, below velocity, displacement, above velocity, acceleration. So gradient, yes, it has a value, velocity. But displacement one step lower. Displacement one step lower, there's nothing. No? So it gives us nothing. So area gives us nothing. Under the displacement time graph, area gives us no any data. If you take velocity time graph, velocity one step higher is acceleration. So gradient is acceleration. Velocity one step lower is displacement. Area under the graph is displacement. Understood? Yes? Okay. So simply put in the mind, you have a certain graph, gradient gives us one step higher, area gives us one step lower. That's enough. You don't need to separately memorize that. Now you all write this Senki. Quickly write down. Now this is not art class. Don't slowly draw and wait. Dingala draw. I want you all to draw. Don't just take a screenshot and sit. Otherwise, again, you will fall sleepy. Do something by yourself. Okay. Shall I change to the next one? Oh. Okay. හරිනේ. හරි. With that, that part is also done. Now, you all have a final surprise session. We are going to move on to a very surprise session. I won't tell what it is. My coordinators are going to fully do that. So, over to y'all coordinators.
Once again, thank you, sir. Hello, everyone. Once again, this is Keshavanathan Krishani here. Okay, everyone listen closely because this is the part you'll regret missing. As you all know, this is a surprise. Actually, I'm going to be honest. I asked if I could quit being the announcer so I could play for this reward myself. But they said no. You have to be smart, sharp, active, super speed, 100% energy, and focused. Because today we're gonna have only three winners. They are one of them. And are you one of them or lucky person to obtain that reward? Alright. All you need is to follow my instructions. Ready? Eyes on screen, ears on speakers. You will get a Google Form link in the Zoom chat box, WhatsApp community, and 2024 OL groups. Zoom and YouTube students, please log in into that and enter your name and your number. Fill the Google form and submit as soon as possible to become the winner. Because the first 3% who complete the Google form will be the winners with correct answers. 3 people who can keep their focus, keep their energy, and dominate this game. The unbelievable reward is the 3 winners of today's game aren't just getting a prize, they are getting a golden ticket. Our top 3 champions will earn the free exclusive access for the final seminar, which means you're gonna skip the fee and go straight to the grand final seminar. So, wishing you a very all the best. Your Google Form link will be uploaded in 3, 2, 1 and start. 3, 2, 1, and the time is up. We aren't crowning the winners right now. I can't tell you the winners. My lips are sealed until the very end of the seminar. We are keeping you in a suspense until the very end of the seminar. So meet y'all at the end. We'll see who gonna be the lucky champions to get the free exclusive access to the final seminar. See y'all at the end.
Right. I hope you all have done it, right? They are all questions from past papers, I guess. Yes, past paper questions. Coordinators only made it, right? You'll see, right? I'll see your marks as well. Hurry. So with that, graphs part is also done. Now our last part, I told you how to do any kind of physics question. To do any kind of physics question, Lamai, first of all, you should be thorough with your equation. Physics is mainly ruled by equation. When you're reading the question at the first 10 minutes, sorry, at the first 10 seconds itself, equation should come into your mind. I will summarize all the equations we have in our full syllabus. Full syllabus, all the equations I'm going to give. Now itself, important equation, done with equation, things that maybe you have not touched on. Now put it to the mind with me. What are the equations we have? First lesson that we study is motion in straight line. That is the first physics lesson. Motion in straight line. I'll write it short. Motion in straight line. Under motion in straight line, lot of equations there. What are the equations we have? We have an equation to calculate speed. Speed is equal to distance divided by time. Don't use this in your exams. This equation is given just for us to know the definition of speed. What is speed? Speed is rate of change of distance. Speed is rate of change of distance. That is speed. Just for us to know the definition, this equation is given. Don't use this in calculations. Speed is equal to distance divided by time. Next, velocity. Even velocity, there is an equation like this. Displacement divided by time. Velocity is displacement divided by time. There's the equation. But again, don't use this equation. Why I tell don't use this equation? These equations are valid only for constant velocity and constant speed. Only for constant velocity, constant speed, you can use this equation. All the times you can't use this. Now, for example, in a motion where there is acceleration or in a motion where there is deceleration, velocity is not fixed. If one side is not fixed, how are we going to apply this equation? So don't use this equation unless and otherwise it's a constant velocity, right? This is only for constant velocity. Constant velocity, you use this equation. Otherwise, your answer won't come correct. What's the equation we usually use to calculate velocity? Acceleration equal final velocity minus initial velocity over time. That's the equation. That's the correct equation you can use to calculate velocity. Now, when during these kinds of calculation, they will give the acceleration and the time. Initial velocity, they might tell object is starting from rest. If object is starting from rest, anybody knows initial velocity is 0. You can find the final velocity. This is the usual equation we use to find out velocity. The acceleration. Acceleration also you can find from there. Again, one more time. Speed is equal to distance over time. That is definition wise equation. Velocity is equal to displacement over time, only applicable for constant velocity. Acceleration is equal to velocity, final velocity minus initial velocity divided by time. Acceleration is final velocity minus initial velocity divided by time. Next. Average velocity. Average velocity is equal to total displacement divided by time. Is this equation valid? Yes, this you can use. This equation is valid. Average speed is equal to total distance divided by time. Is this equation valid? Yes, it is valid. Why? Average is something like one single value. Average is a one single value, so it won't change. So when finding average, yes, you can use this equation. But other than that, only when there is constant velocity, you can use this equation. Acceleration equal final minus initial velocity divided by time. These are the equations we have in motion under straight line. I can't give you all a separate time to write. Take a screenshot and keep later write it. Now, whatever I'm going to give, maybe in one single A4 paper, when you're writing, one single A4, I think don't create new pages and start writing. Maybe in one single page, okay. Alright, I'll get aside. Right. Right. Next, Newton's law. Newton's law. Newton's law only one equation. No, two equations are there. Two equations are there. What are the two equations? One or a second law equation. F equal ma. A equation that rules your forces section. මේකත් එක්ක මන් දෙන්න units ටිකක්. What's the SI unit of force? What's the SI unit of force? Newton. What's the fundamental unit of force? What's the fundamental unit of force? Fundamental unit kya the basic unit. Fundamental unit of force is the unit that you get from the equation. Equation of force is F equal ma. Mass unit is kilogram. Acceleration unit is ms to the power minus 2. Mass unit is kilogram. Acceleration unit is ms to the power minus 2. Then the fundamental unit of force is kg ms to the power minus 2. Kg ms to the power minus 2. Other than that, we have the equation for momentum. Momentum is simple p. Simple p is the symbol for momentum. Simple p, momentum. Simple p is equal to mass into velocity. Simple p is equal to mass into velocity. What is simple p stands for? What does simple p stand for? Momentum. Momentum. Simple p is momentum. What's the unit we have? Mass is measured in kilograms. Velocity is measured in ms to the power minus 1. Kg ms to the power minus 1. That's the unit we have. Those are the two equations we have. So acceleration, mass, this is the equation. Mass and velocity, momentum, this is the equation. Take a screenshot. Right. Next physics question. Next physics lesson is friction. Friction, well, there is no any equation, but we learn about three types of friction. What are the three types of friction we have? Static friction, limiting friction, dynamic friction. Static friction, you apply a force, object is not moving, that means there is a friction acting there, static friction. Maximum friction is limiting friction. It's at the verge of motion. When the object is moving, friction acting is dynamic friction. No any equations are there. Next. Resultant force. Resultant force. What is resultant force? One single force that gives the value of all the contributing forces. One single force that gives the value of all the contributing forces. How do you find the resultant force? If the forces are in the same direction. If the forces are in the same direction, you add. When you add, you get your resultant force. If the forces are in the opposite direction, then what you do? Then you subtract. Subtraction gives you the resultant force. That also you subtract the smaller force from larger force. Smaller force from larger force. Small from large. The large will come first, small will come next. Then only you will get a positive value. Those are the two equations we have under resultant force section. Next, turning effect of force. Turning effect of force. Turning effect of force. Turning effect of force is also called moment. Turning effect is also called moment. What is turning effect of force telling us? Let's take you have an object pivoted at one point. When you apply force perpendicular to the object, can you see this force is perpendicular? 90 degrees is formed there. Perpendicularly, when you apply the force, that object will turn. When you apply a force perpendicular to the object, that object will turn. It will rotate. That is called the turning effect of force. Force has the effect to turn an object. Turning effect of force. In simple terms, you call it moment. How do you calculate the moment? Moment is equal to force multiplied by perpendicular distance. Moment is equal to force multiplied by perpendicular distance. Let's take this is the rod pivoted at that point. You are applying a force there at a distance d කියලා ගමුකෝ. එතකොට you multiply the force by the perpendicular distance, you can calculate the moment. Now you all tell me, if the force is applied like this කියන්නේ මේ වගේ force, will this kind of a force contribute for the moment? Will it cause any turning effect? That won't cause any turning effect. It won't contribute for the moment. It don't contribute to the moment. It don't cause any turning effect because it's a parallel force. Harini, you have the object like this. If you apply a parallel force like this, it don't cause any turning. For it to turn, you have to apply a perpendicular force. Only perpendicular force will create a turning, a rotation. Parallel force won't create any rotation. Next, couple of force. Couple of force. What is a couple of force means? Two forces equal in magnitude, opposite in direction, that have two different lines of action. Two forces equal in magnitude, opposite in direction, with two different lines of action. For example, here the force, here the force. Both are equal in magnitude, but they are different in direction. They are opposite in direction with two separate lines of action. It is a couple of force. And remember, their perpendicular distance also become equal. If this is d, that is also d. If this is d, that is also d. Now, how do you calculate the total moment here? Total moment is equal to one force, two force. From two forces, moment will come. This force creates a clockwise moment. Force is F, perpendicular distance to the rotational point is d. Force is F, perpendicular distance is d. So they are FD, clockwise. Here, force is upwards. Even though force is upward, it also creates a moment in what direction? Clockwise. Neither. Practically, this also clockwise, that also clockwise. This also clockwise, that also clockwise. Both are clockwise. So both is clockwise. Here the force is F. Again, the distance is same d. Same force F will come, same distance d will come. Both will come in the same rotational direction, clockwise. Rotational direction, clockwise. So if the rotational directions are clockwise, what you do? You add. So if I add like this, you get moment is equal to 2ft. Can we directly apply moment is equal to 2ft equation for couple? Yes, you can apply. M equal to FD equation directly you can apply for couple. There was a past paper question where I didn't apply this. Without doing that, I did all these things and came. Now remember the shortcut. I couple at that comma, again a couple of force at that comma, directly you apply M equal FD. M equal to FD, right? One side force, one side distance is there, that you multiply by both the sides, you can directly find the couple. You can directly find the couple. I'll make the diagram a bit clear before you all take the screenshot. Take a screenshot and keep. Wait a minute. Here there is a couple, sorry, force. There is no rotation. You want it a bit down. Right. Hopefully you can take now. Right. That is turning effect of force. Resultant force done, turning effect of force done. Next is equilibrium of force. Equilibrium of force, well, there is no any big concept. For an object to be at equilibrium under two forces, both the force should be equal in magnitude, opposite in direction, have the same line of action. Equal in magnitude, opposite in direction, have the same line of action. Two force will be equilibrium. If there are three forces parallel, if there are three forces parallel. If there are three forces parallel acting on an object, let's take, resultant of two forces should be equal to the magnitude of third force. These two resultants should be equal to the magnitude of third force. These two directions should be opposite to the direction of the third force. The direction of two forces opposite in the direction of third force. All three should be coplanar. Again, three parallel force equilibrium, resultant of two force equal to the magnitude of third force, direction of two force opposite to the direction of third force, all three should be coplanar. If the three forces are non-parallel, if the three forces are non-parallel, if the three forces are non-parallel, now what's the logic? Resultant of two force equal to the magnitude of third force. ඒක කොහොමද එන්න ඕනේ? Resultant of two force equal to the magnitude of third force. All three forces lines of action should meet at a single point. All three force line of action should meet at a single point. They should be coplanar. Again one more time. Two force equilibrium, both the force should be equal in magnitude, opposite in direction, have the same line of action. Three parallel force equilibrium, two forces resultant should be equal to the third force. Two forces should be opposite in direction to the third force, all three coplanar. Three non-parallel force equilibrium, resultant of two force equal to the magnitude of third force. All three forces line of action should meet at a single point. All three forces should be coplanar. හරි එච්චරයි ඔතනත් equations නැහැ. Equilibrium section also equations නැහැ. Equilibrium section also equations නැහැ. Next. Directly we go to hydrostatics. Directly we go to hydrostatics. Under hydrostatics, first you learn the equation for pressure. Pressure is equal to force divided by area. Pressure is equal to force divided by area. What are the units we have? What are the units we have? Force divided by area is Newton per square meter, also called as Pascal. That is one equation. Other than that, hydrostatic pressure. Hydrostatic pressure. For hydrostatic pressure, you have separate equation. Hydrostatic pressure is H rho G. H rho G. Hydrostatic pressure is H rho G. Again, unit is same. Most of the students think only these two equations are there in hydrostatics. Nah, another one more equation is there. It comes from Pascal's principle. Let's take let's say you have a hydraulic jack filled with a certain hydraulic fluid. This is one piston. This is one piston. That piston has a certain cross-sectional area. It has a certain cross-sectional area. We'll take it as A1. This piston will have a certain cross-sectional area. We'll take it as A2. A2 is larger than A1. Meanwhile, if you want to lift something, now this is a hydraulic jack. Using hydraulic jack, we try to lift something, a heavy object or something, we try to lift. If you want to lift something, you have to apply a force here, F1. When you apply a force there, you get a force there, F2. Here you apply a force F1, there you get the force F2. Pascal is telling a relationship between F1, A1, F2, A2. Pascal is giving us a relationship. Pascal is giving us a relationship between F1, A1, F2, A2. What's the relationship? F1 divided by A1 is equal to F2 divided by A2. F1 over A1 equal F2 over A2. This side F1, A1, this side F2, A2, their divisions are equal. There's an equation like this, especially for Pascal related questions. You can apply that. You can apply that. Hurry. Right. Next lesson we have there is work, energy, power. Work, energy, power lesson. First, work done. How do you calculate work done? Work done is equal to force multiplied by distance moved in the direction of force. Work done is force multiplied by distance moved in the direction of force. What's the unit there? What's the unit there? Force is measured in Newton. Distance moved in the direction of force is measured in meters. Newton meters. Newton meters is also called as joules. Also called as joules. Second equation. Under energy. Under energy, we have to separately learn about kinetic energy. You symbolized as EK. Kinetic energy is equal to half mv square. Half into mass of the object into velocity square. Velocity square. Half into mass of the object into velocity square gives us kinetic energy. Next, gravitational potential energy. What is gravitational potential energy equation? Mass into gravitational acceleration into height, mgh. Both their units are joules. Any energy unit is joules. Any energy unit is joules. Both their units are joules. All their units are joules. Alright. What is the fundamental unit? What's the fundamental unit of work done? This is how you find the fundamental unit. You find the fundamental unit using the basic equation. What's the basic equation for work done? Work done is equal to force into distance moved. Force. What's the fundamental unit of force? We already wrote it. F equal ma, we found the fundamental unit of force. What's the fundamental unit of force? F equal ma, mass is kilogram, A is ms to the power minus 2. Mass is kilogram, A is ms to the power minus 2 nang. Force is kg ms to the power minus 2. That is multiplied by distance. Distance is meters. When you do the math there, the fundamental unit for work done is kg m into m square s to the power minus 2. Kg m into m squared s to the power minus 2. Kg m squared s to the power minus 2. One person asking what is fundamental unit? Fundamental unit is the basic unit that a certain equation has. You get a certain quantity has. You get that fundamental unit from the basic equation. A basic equation for work done is force into distance moved. Force is kg ms to the power minus 2 multiplied by distance. Distance is meters. So kg m squared s to the power minus 2. Kg m squared s to the power minus 2. That's the fundamental unit. Kg m squared s to the power minus 2. And it's the same fundamental unit for any energy. Ia. Another unit for work done is joules. Another unit for work done is joules. And fundamental unit for work done is kg ms to the power minus 2. Another unit for work done is joules. Fundamental unit of work done is kg ms to the power minus 2. Which means I can tell every quantity that has the unit joules, its fundamental unit is going to be kg ms to the power minus 2. Agree? Every quantity that has the unit joules, its fundamental unit is kg ms to the power minus 2. Ehinang kinetic energy, it has the unit joule, then its fundamental unit is kg ms to the power minus 2. Gravitational potential energy, it has the unit joules, its fundamental unit is kg ms to the power minus 2. So remember, any unit, any quantity that has the unit joules, its fundamental unit is kg m squared s to the power minus 2. Kg m squared s to the power minus 2. Right. Other than this, we have in this lesson law of conservation of energy. According to law of conservation of energy, when you do any work, total initial, here we talk about mechanical energy, total initial mechanical energy, total initial mechanical energy and total final mechanical energy, total final mechanical energy, both become equal. At the start, if you have 2000 joules of mechanical energy when you're doing a work, at the end also you will have 2000 joules of mechanical energy. What is mechanical energy? Mechanical energy is kinetic energy and potential energy together. So at the beginning, kinetic and potential together, if you have 2000 joules, towards the end also kinetic and potential together, you'll have 2000 joules. That is law of conservation of energy. Hurry. Right. Next, power. Make a menu. Power. Power of an power, mechanical power is equal to work done by that object divided by time. Work done divided by time. Put it also into the same this thing. Work done divided by time. What's the main unit of power? Main unit is watt. Unit is watt. Another unit is there. Work done is measured in joules. Time is measured in seconds. So if I divide it, unit is joules per second. That is called as watt. What's the fundamental unit? What's the fundamental unit? Go tell me. Joules is what? Now we know already. Joules is what? Kg m squared s to the power minus 2 divided by second. So if I divide by second, what I will get? Kg m squared s when it goes up, it becomes s to the power minus 1. So I have already s to the power minus 2. When I bring this s up, s to the power minus 1. Altogether I have s to the power minus 3. Fundamental unit Kg m squared s to the power minus 3. Sorry. Next lesson, current electricity. Current electricity. Under current electricity, first equation you learn is voltage. Voltage equals current multiplied by resistance. V equal IR. Kind of one equation that rules the full current electricity lesson. V equal IR. Other than that, we have resistor combination. We have resistor combination. Resistor combination, we have two types of resistor combination. One, series connection. Two, parallel connection. In series connection, let's take about two resistors are there connected one after the other. Resistance here R1, resistance here R2. Now your equivalent resistance is R1 plus R2. Parallel connection. Parallel connection, you branch the resistors and connect like that. You branch the resistors and connect like that. Resistor there R1, resistor there R2. Now how do you calculate the equivalent resistance? Here you calculate the reciprocal of equivalent resistance. You call it 1 over Req. Reciprocal of equivalent resistance. Reciprocal of equivalent resistance is equal to reciprocal of R1 plus reciprocal of R2. Anybody wants the previous slide? I'll show the full previous slide, you know. Horror, right. That's it. Your grade 10 is done from there. Grade 11 වල there is no big equation. හැබැයි heat lesson I have finished today. Electromagnetism lesson I have finished today. What is not done as a big lesson is electronics. ඒක තමයි අනිත් ඒවා නම් ඉතින් එහෙම there is no any big effect there. Others small equations there. I'll give those equations. හැබැයි අර tough lessons වගේ I have finished. I have finished. One kind tough කියන්න බෑ. One logical lesson which is existing in physics for you all now is tronics. එච්චරයි. හරි? In grade 11 first you learn about waves. Waves වල වැඩි equations නෑ. Equation එකයි V equal F lambda. That's the one and only equation you have in waves lesson. V equal F lambda. What does V equal F lambda stands for? Speed of a wave is equal to frequency multiplied by the wavelength. Speed of a wave is equal to speed of wave is equal to frequency multiplied by the wavelength. Sorry. Now sometimes they won't give the frequency. They won't give the frequency here. Instead, they will give something called the periodic time. If they give you the periodic time, you can find frequency. How? Frequency is equal to 1 over periodic time. Sometimes they won't give frequency. Frequency is equal to 1 over periodic time. Next lesson we have is geometrical optics. Under optics, one equation is there. Under your second law of refraction. Under second law of refraction, there's an equation to calculate refractive index. Refractive index is equal to sine value of incident angle divided by sine value of refracted angle. Sine I over sine R gives us the refractive index. Simple N is refractive index. Or you call it the index of refraction. Next is the section that we did today, heat. Heat වල තියෙන ළමයි එකම එක equation එකයි Q equal equation දෙකයි MC theta one equation today we did and tell me capital C equal MC. Capital C equal MC. Capital C is heat capacity, simple C is specific heat capacity. ඊළඟ එකත් කරා. I released you all mainly in your grade 11 tough lessons. Power and energy of electrical appliance. Power and energy of electrical appliances. එතන ආවේ මොනවද ළමයි equations? Power is equal to voltage into current. Power equal VI. Energy is equal to power into time, PT. E equal PT. Also energy is equal to voltage multiplied by current into time. Alright. Tell me for this energy in kilowatt hour. Energy in kilowatt hour is equal to, who can help me? Power in watt. Power in watt divide by 1000 multiplied by number of hours. Perfect. Those are the equations. Sorry. 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 After this, the lessons are not, yeah, after this, the lessons are tronics, no any equations. Electromagnetism, no any equations. So first, make all your equations perfect. Make all the equations perfect. That is very important for physics question. Without equation, you can't do physics question. Other than the equation or equation less lessons, tough lessons I have covered from my end. Right? When I'm writing all this equation, in case if you felt like you don't know what is sir talking about, from which lesson this equation is coming on, that means you have a problem in that physics section. ඔය section එක අනිවාර්යෙන් cover කරන්න ළමයි. That section you cover it by yourself and key. Without that you can't do that section. හරි. Physics වලට අනිවාර්යෙන් do questions as much as possible. Questions as much as possible. This time period, sitting and just studying is not enough. Yes, theory is needed. Just the theory is not enough. Now let's take day before the exam. You memorize all these equation and go. No, that is not enough. For each equation, at least do one question and key. You should know how questions are asked. Now, for example, when I was talking about this lesson, I gave you all the equations and all. Even though I gave you all the equation, once when you go to that teacup question, we felt a bit hot. We felt a bit hot near the last question name, how much is the wastage name? Hinda. Even though you know the equation, do at least 1 or 2 questions and keep from each and every equation in our syllabus. They won't ask sine I over sine or that equation, they won't ask because it is not there in our syllabus. Questions are not there in our syllabus. So they won't ask that. Other than that, all the other equations they can ask. It can come. It can come. Hurry. It can come. Now, if you take your paper, your fourth structured essay. Fourth structured essay is guaranteed physics that I have already told you all in the structured essay practice as well. Fourth structured essay is guaranteed physics from that. And if you take your essay paper, fifth essay comes from biology, usually come from biological process and human body. Sixth essay comes from chemistry. Seventh essay comes from physics. Seventh essay comes from physics. Eighth essay maybe biology and chemistry mix again. Ninth essay again comes from physics. Ninth essay comes from physics, right? Electromagnetism can come for the physics. Ninth essay, electromagnetism. Sometimes they put electrochemistry together. Nothing electromagnetism and tronics together. Last 2-3 years, forget tronics was not at all there. If tronics is not there, yes, there is possibility for the tronics to reappear now. I don't will guarantee tronics will come. There is possibility for the tronics to reappear now. In the tronics අනිවාර්යෙන් ඉවර කරන්න ළමයි. Right? Now, when you start a physics question, when you approach a physics question, treat physics question like a normal general scenario in your life. Because physics is something that is related to our normal life. Whatever we do in our day-to-day activities is only physics. In our day-to-day activities, fully physics is there. So when they make the questions also, they relate it to our day-to-day activity. Now making tea. 4 cups of tea, 8 cups of tea gala දාලා තියෙන්නේ ඒක day to day activities වල. Don't try to look at physics question as if you are going to really sit and do a real physics question. That is what makes it hard. That is what makes it difficult. Don't do that. Sit for a physics question as if you are going to treat something very simple, very easy section you are going to treat. As if something in your daily life you are going to treat. ඒ වගේ තමයි you approach a physics question. Suddenly, when they talk about any calculation part, first 10 seconds wala equation should come into your mind. Otherwise, they will give graphs and talk to you. Graph analysis is very important. Any graph you should be able to analyze. Graph analysis, without graph analysis, you can't do any physics question. Y-axis is there, X-axis is there. a graph like this, what does it tell? When x-axis is increasing, y-axis is also uniformly increasing. When x-axis is increasing, y-axis is also uniformly increasing. That's the meaning of this graph. X is increasing, y is uniformly increasing. Now, for example, if I drew a graph like this for friction versus external force, when I draw a graph like this, decode this graph, what does this graph tells us? When the external force increase, friction is also increasing. External force increasing, friction increasing. Now what friction? External force increasing, friction increasing. Now what should be that friction? Static friction. That is static friction. Again, you should be able to decode. This type of graph means external force, x-axis is increasing, together with that y-axis also increasing. Now, for example, let's take a flat line like this. In a graph, flat line like that. A flat line like that. What does the flat line tells us? What does a flat line in a graph tells us? Analyze it. X-axis is increasing, x-axis is going on, x-axis is increasing. Is the y-axis increasing? Is the y-axis changing? No, y is not changing. Y is constant. Y is constant. Y is not increasing. Sorry. So x-axis is increasing, y is not increasing. That's the meaning of this flat line. Now let's take a line is going down in the graph. Let's take the line is going down in the graph. What does this mean? X-axis is increasing, yes, x is going. With x, what is happening to y? Y-axis is decreasing. X is increasing, y is decreasing. Make a done any graph, you don't need to memorize. Velocity time graph, displacement time graph, you don't need to separately memorize. When you know this logic, you can understand that from the graph, x is increasing, y is decreasing. Altogether, x is there, y is there, x increase, y increase, x increase, y is same, x increase, y decrease, x increase, y decrease, x increase, y increase, y decrease. Now decode it into velocity time graph. Now decode it into velocity time graph. Decode it into velocity time graph. Try to find the nature of the motion. See, time is going, velocity increasing. What is that? Time is going, velocity increasing now, acceleration on. No need to separately memorize. Decode from the graph. Time is going, velocity increasing now, acceleration. Here, time is going, velocity is not increasing, not decreasing, not increasing, not decreasing, a uniform velocity. Here, time is going, velocity is decreasing, velocity is decreasing. What is that? Deceleration. Ehema decode the graph. Right? Another type of graph can come like this. These are famous graphs that comes. Right. This is temperature versus time graph. For a solid, we don't know what is the solid. It can be any solid. For a solid which is at minus 50 degrees Celsius when it is heated. temperature versus time graph, for a solid which is at minus 50 degrees Celsius when it is heated. We'll try to decode. Initially here, it is at minus 50 degrees Celsius. Initially there, it is at minus 50 degrees Celsius. Time is going. X-axis is going. What is happening to the temperature? Can you see temperature is increasing? Or you are heating that. Temperature increasing. So during this time, temperature is increasing. Time is going, temperature increasing. During this time, what is happening? Temperature increasing? Nah. Is temperature decreasing? Again, no. Temperature is same. Temperature is same now. What is happening there? A change of state. Why? Yesterday I taught you. During change of state, is there any change in the temperature? No. So here a certain change in state is happening. What should be the change in state? Solid will undergo first what change in state? Melting. So this should be melting. Here you do the analysis. After all the solid melt and finish, again time is going, temperature is increasing. From melting, after you melt and finish, temperature may be increase. Again there's a flat line. Is the temperature increasing? Is the temperature decreasing? No. Flat line can what? Temperature is same. Again state change. What should be the state change? Most of the time it's boiling. Got it now? Right? So one side, make your equations perfect. On the other side, make your graphs perfect. That's it, physics. Right? Other than that, tough lessons I have finished from my end. Right? Approach your physics question as if you are dealing something with your day-to-day work activity, a day-to-day activity again. That's how questions are also given. That's how your approach also should be taken. What? ඒව ටික තමයි ගැන ෆිසික්ස් ගැන කියන්න තියෙන්නේ. Right? හරි. I think coordinators is the winner selected. Winners, no, 3 winners. Yes, Krisha, you can go on.
Yes, as I said earlier, champions who can trap the free exclusive access for the grand final seminar will be revealed in few seconds. Now the wait is over. The 3 champions who will be joining us at the final seminar for free are Rujan, Amir Ahmad, Muhammad. To repeat, Rujan, Amir Ahmad, and Muhammad are 3 VIPs. While everyone else is checking the calendars, these 3 are already on the guest list for free. Congratulations, boys. Last but not least, deep gratitude to King's Perory Sir for the trust and the opportunity. Seeing Kirtiha and Razin, who provided the activation energy by working throughout the night, who worked tirelessly to ensure everything was perfect. It's been a high yield collaboration. Thank you, both of you. And yeah, wishing you exam success. Go crush those exams. Sending you positive vibes behalf of Team PattaEasy. See you all at the final seminar. This is signing off Krisha. Thank you.
Right. So we have come to the end of tonight's session. Physics night, right? A night session comes as kind of the unique thing for a certain batch. So for you all also it is done. For your batch also it is done. So maybe students predicted that we are going to do bio night. Bio night was in the plan, but the problem is bio night involves only explaining, no any questions or anything, which means somewhere around 12:30 it's hard to keep you all up. You might fall a bit sleep. AK bio night එකක් නැහැ. So we are going with physics night. In between, you saw I gave you all some questions to practice. That is to keep you all up. Whereas at that time you will be sleeping. එතන කැඩෙනවා. හරි ඒකයි this thing. Chemistry night. Not in the plan, but last year chemistry night is there. That recording I have kept it. Right? You can watch that. Again, chemistry night කියලා එකක් කරන්නේ only one night for one batch. That is physics night is over. Now coming to the end, we have 1 month for the exam. That is your final 31 days. As I can remember, starting from today, it's 31 days. Final 31 days of run is there. Just look at yourself today. How much of effort you were into this process. How much of effort you put into this process. Which means you have a potential inside you that can keep you focused into something for a very long time. You have something inside you. You have that potential inside you. Don't lose that potential. You have to bring out that potential. Not every human being gets the chance of showing off what they have inside you. Now it's a chance for you. Every year, a certain batch will get that chance. The ones who show off that go to their maximum in their life. Now it's the time for you. 31 days are there for you to show off who you are. What is your maximum potential inside you? Bring it out. Final 31 days, focus only onto this, nothing else. If the phone is disturbing you, keep the phone aside. If something is coming into the mind and disturbing you, you tell your mind, no, this should not come into my mind. I am focused onto this. You have to control your mind. Otherwise, who else is going to come and control your mind? You have to have the control over your mind. You can't tell to me, sir, when I start studying, I get distracted. I start thinking, you can't tell that. You're big enough now. You're an adult. You're almost an adult now. Now you have to control your mind. You have to keep it in a balanced state. Otherwise, how are you going to go to the next stage? Next stage is your career life. How are you going to enter that life if you can't control your mind? You have to control. You have to keep it focused. Yes, it is stress. Yes, it is very depression is there. Everyone has stress. Everyone has depression. Pressure is there. Under pressure, you have to work. Without letting the mind go off, without starting to shift to some other thing that gives you happiness, maybe using phone or anything. If phone is getting you off the track, keep it away. If something is getting you off the track from your main track here, you keep it away, whatever it is. Be a bit selfish these days. If someone is coming and telling you a work unnecessarily in a time that you are going to work, then tell them, no, I can't do this work. I have to study. I think you don't play there. After telling that, you work there. So you be a bit selfish for your time and allocate the maximum time for you. Every second, every minute, put that work, put that effort into this, because the final reward here is very big reward. That reward is only for you. No one else can use the reward. Yes, maybe parents will tell, mother will tell, father will tell, the relatives, my son got this result, daughter got this result. That will go for a very little time. And maybe teachers will tell that will go for a very little time. After that, it's all your reward. That reward will do good only to you. So you take that reward. You have that potential inside you. 1 month is more than enough. With responsibility, I'm telling. W can be changed into A. I don't tell you, I won't tell you can't. You can. There are people who have done that. But the people, those who have done that, they have discipline on their studies and their work. Now, discipline, don't think cutting the hair, cutting the nails, that is discipline. Discipline, you sit and you focus and you work on something that you want to achieve. That is discipline. Build up that discipline inside you. If you are focused on something, focus and work on that. Build up the discipline inside. That is very important before you go to your career life. Without that, you can't go to your career life. Keep up that spirit. Final 31 days. You give the maximum effort, you put your maximum input into this. Whatever the input you put only, you will get as the output. So give your best into this. You have a best version inside you, bring it out. Now it's the time to bring it out. If you don't bring it out now, when are you going to bring it out? No, we are not going to live for 100 years. No, maximum we can live, our generation can live for 70, I think, 80. So during this time period, almost 15 years of life is over. During this 15 years of life, did you ever bring your best version inside you out? No. And towards the end also, after about 40 years older, you can't bring your best version inside you. So this is the time for you to bring the best version inside you. It's got to work. Give your best. Now give your best. One life you are living. Okay, now we are in the stage where you have to bring your best version. When you are small, yes, you had reasons to tell you can't bring your best version. When you're old, yes, you have again reasons to tell you can't bring your best version. Now you can bring your best version. Don't lose this. Don't lose this chance. If you lose this, you will regret throughout your life. One life. After studying, after you're working onto this for 11 years, if you finish it with regrets, what is for you? Don't finish this with any regrets. 11 years of work was put into this. Don't keep any regrets towards the end. After this journey, when you turn back and see, I have done something good, Kela, you have to think. Don't finish this with any regret. If you have any regret, then now itself stop this. Don't do it. Another 1 month, don't waste into this if you are going to finish it with regrets. Or எப்படியாவது செஞ்சு முடிச்சிருவோம் கோமாரி மேக் இவர் கரும். Don't come into that mindset. If you are into that mindset, stop this. Another 31 days, don't waste into this. Instead, you go and do something else. If you are onto this, give your best and finish. Now, you give your best and you get a low result, at least you can satisfy yourself telling that I gave my best and got this result. You don't give anything and you get a bad result. Think and see. Now, if you give your best, surely you won't result with bad result, because your output equals your input. If you give your best, you can't result with your low result. Very rarely only it happens. Maybe on the day of the exam, you get some huge disease. You can't do that exam. Accident or regrets will be there. Other than that, if you give your best, surely you will end up with a very good result. So give your best during this time, because 11 years something in your life, you have not done anything like this. Doing something for 11 years and finally finishing it. Nothing in your life you have done like this. So now the maximum input should be given. Grinded, work like robots, work like ghosts, finish off everything. If you feel like any lessons that I touched today when I'm writing the equation that is not there in your mind, then you cover it. You have to put it in your mind. You can't keep on complaining. Now it's your turn. You have to cover it. You all have enough resources now to cover. Now you can't still tell reasons. Reasons are not an excuse for you. Don't build excuses. Don't live such a life. It's your life. If you know that such a lesson is there for me, I don't know. Don't make it a reason. Make it a possibility for you to work, give your potential, and try to come out of it. So it's your turn. It's your show. You finish it in the best way. Don't reside with any kind of regret. At the end, when I ask you, when the result comes, are you satisfied with this result? You have to be ready to tell, yes, I'm satisfied with this result. Such a result you have to get. Otherwise, don't do this. If you feel like, no, I can't get such a result, no, I don't do this. No point. If you are not in such a stage of the result, work for it. Work for it and give your best and then get the result. All of you can. I'm telling this with responsibility. I'm talking to people in W result. The W result can, I think all the other upper results can. Give your best. So many people are interested about you. So many people wanted to find out what kind of result you get. In case if you get any low result, so many people want to mock you down, put you down, further stress you. Don't allow those things to happen. And you yourself will end up with your own regret. Don't keep that. Leave all the others aside. At the end, your regret. Until the end of the life, you will have no. Don't keep that. Sorry. We have come to the very end. We have come to the very end. Now you all know what we are going to do. Physics night for 2025/26 O-level batch is done. Physics, all the important sections are done. At the end of this physics night, you all honestly tell me, what do you feel about physics? Letter by letter. There you go. Letter by letter. Start. P. Next. A. Next. T. Next letter. Another T. Another T. Last letter. Last letter. A. A. Next. Next. E. Next. A. Last two. Last two. S. And last letter. Y. PattaEasy. Don't forget the hashtag and the signature. Ehena, we are done with the physics night session. All those who were here, who are here, I don't want you all to sit back with any low result. This is your chance, your challenge, your game. You have to work, you give your best. You have such a spirit inside you, believe in that. Don't keep on constricting that spirit and don't keep on constricting the energy that you have inside you. Bring it out. Now it's the time to bring it out. Now it's the time to put the maximum effort. Now it's the time for you to go for your maximum result you can. Work like robots, work like ghosts, finally end up with a better result. Until then, it's King's Perory signing off. Good morning. Bye.
सांसों के साथ